बैक कर लो स्लाइड में इतना बनना कैमरा रखो ऊपर माउस नहीं ध्यान
Saurabh, ये कर मुझे लैपटॉप से लोड कर लो दो लैपटॉप
So good morning to all. So my name is Dr. Prof. So it's a matter of great pride to welcome the guests who are present here to attend this international symposium. So this symposium is being organized by Department of Chemistry and co-organized by CRSI, local chapter Chandigarh, Amritsar. So it is a memorable occasion and a landmark for all of us to have our worthy Vice Chancellor, Professor Jaspal Singh Sandhu, sir among us today as the chief guest. So on behalf of the organizing committee, I welcome you with greatest reverence and highest admiration. So I also welcome our Dean Academic Affairs, Professor Hardeep Singh, Registrar, Professor K.S. Kalo, Director Research, Professor Renu Bhardwaj, Head of the Department, Professor Supramolecular Singh, for gracing the symposium with their presence. So we are delighted to have the gracious presence of Professor Yoon from Eva Women's University, Korea, Professor J.S. Kim from Korea University, Professor Amitava Das from IISER Kolkata, Professor Iyer from IIT Guwahati, Professor Sankar from IIT Roorkee, Professor Reji from IISER Thiruvananthapuram, Professor J. Murugan from Institute of Nanoscience and Technology, Chandigarh, and Professor Sanjita from IISER Mohali. So warm welcome to all the renowned speakers who took out their valuable time and joined us today to be a part of this symposium. So I also welcome all the faculty members from Chemistry Department and other faculty members of the GNDU family and friends from the press and media on this occasion. I also welcome our students who are participating in this symposium in an online mode as well as in offline mode. So last but not the least, I also welcome our birthday boy, Professor Manoj Kumar. So please join hands and voice with me in wishing happy birthday to a very cool professor. So happy birthday to you, sir. So we are blessed to have a person that so much efforts into research and administration. So this conference with the theme Recent Advances in Self-Assembly Materials and Supramolecular Chemistry is the right platform to bring distinguished speakers under one roof to discuss different facets of supramolecular chemistry. So supramolecular chemistry specializes in non-covalent interaction, and since its conception, it has become a truly interdisciplinary research area spanning across biology, chemistry, nanotechnology, material science, and physics. So this field has earned 2 Nobel Prizes, first in 1987 and second in 2016. So supramolecular chemistry focuses on 2 areas, that is supramolecules and molecular assemblies. So on 50th anniversary of Patterson-Crown ether discovery, Professor Lehen, the Nobel laureate, rightly poses the question, supramolecular chemistry, where from, where to? So the scope is perhaps even broader than advised initially, and this field has tremendously grown. So this symposium, which we hope will reflect the true breadth of the supramolecules of the Professor Manoj Kumar's life. So it's not a hocus pocus, but it's all about a focus. That is, follow one course until successful, and it's truly justified in his case. The teacher-student relationship is symbiotic. Whatever a teacher writes on the blackboard of a student's life can never be erased, and these loving words from students are like a beautiful footprints that have been etched on teachers' hearts and minds forever. So Professor Manoj Kumar secured his MSc degree from Khalsa College. He completed his PhD degree under the supervision of Professor Hardeep Singh in 1988. So he worked as a postdoctoral fellow at Institute de Química Médica, Spain for 2 years. So he joined the Department of Chemistry, GNDU, in 1993 and till date, he has published 210 research papers in different journals. So 16 students have completed their PhD under his supervision. So his research area is focused on synthesis of development of probes for molecular recognition of and bioimaging of biological important analytes, and the development of catalytic and photocatalytic system to carry out some organic reactions. So for his contribution in research, he was awarded with the CRSI Bronze Medal in 2011. He never looked back after this and continued on his successful career path. So he has published 5 papers in Organic Letters journals in 2012 and 9 papers in Dalton Transaction Journal in 2013. He has many papers with citation over 100. So in 2015, he published 9 papers in Chemical Communication Journal, and due to his huge contribution in the same year, the chemistry department was cited in top 1% institute publishing in the RSC journals. So another recognition has been accorded for his contribution in the area of supramolecular chemistry when Indian Academy of Sciences, Bengaluru, apex body of Indian scientists, has elected him as fellow in 2018. So very recently, he also got a position among the best 2% scientists in the world. So we pray that he will continue to work for many years to come. So these are some free moments for him to enjoy when someone, you understand, someone is not around. So thank you all for your attention. So now I would request our HOD to come on the dais and apprise you about the courses run by the department and activities being carried out in our department. So Professor Supramolecular.
Thank you very much. So, I am lucky to be sharing not only department but also the date of birth with Professor Manoj. Not only this, but we were also recruited in this department as assistant professor by the same selection committee. So, thank you, Prof. Thank you very much. Professor Reji from ISER Thiruvananthapuram. Professor Jaya Murugan, Institute of Nanoscience and Technology, Chandigarh. Professor M. Sankar from IIT Roorkee. Professor Kamaljeet. Professor Swapan. Professor Subodh. Professor T.S. Lubhana, Dr. Manoj Singh Batra, Dr. Jitinder Gandhi, Dr. T.S. Banipal, Dr. Parampal, Dr. Paramjeet, Dr. Sumanjit, and all my other fellow colleagues and my students. It's my play and duty to tell regarding the Department of Chemistry. Department of Chemistry is a part of Guru Nanak Dev University. Guru Nanak Dev University was established at Amritsar on November 24th, 1969 by an act of Punjab Legislature Assembly to commemorate the 500th birth anniversary of our first Sikh Guru, Shri Guru Nanak Dev Ji. It boasts 35 academic departments today. It is a multidisciplinary university. Department of Chemistry is amongst these 35 academic departments. Department of Chemistry in its present form started functioning in the year 1971. Before that, it started functioning in the year 1970 from the premises of adjoining Khalsa College, Amritsar. Over a period of time, it has emerged as one of the premier departments, not only within the university campus, but also at the national and the international level, all due to the contribution of its faculty and students. I am really thankful to all of them, my colleagues, my fellow friends, who have done a lot of hard work, starting with my seniors, who had put a lot of effort. Our seniors have been starting their day right at 7 a.m. in the department and sitting in the department late, even up to 6 p.m. and even is maybe sometime devoting a lot of time in the department, which is responsible for all these laurels that we have been able to bring to this department. The department has always been able to receive generous funds from the university administration as well as federal and state funding agencies. The Department of Chemistry was in fact the first to have a nuclear magnetic resonance facility in the region, in whole of the region. We were the first who were able to procure the nuclear magnetic resonance facility. Hard work of the faculty and students of the department has always paid good dividends, and all of its faculty members have been able to receive grants from multiple funding agencies. In fact, even today, we are having more than 18 or around 20 major research projects that are being handled by all our faculty members. Department offers 3 master's courses, 1 5-year integrated course, MSc Chemistry, under the scheme of honor school, and 2 2-year master's programs in and MSc Applied Chemistry. The distinction of these courses is that we, right in the budding state, provide an opportunity to our students to do original research. All of them have to submit a research project toward the end of their master's program to earn a degree. Besides these courses, the department also offers PhD program. The H-index of the department at present is 96 journals that we achieved that feat during the year 2015. But during the year 2013, department ranked 12th in All India ranking for publishing 55 or 60 papers per year during 2013. Presently, we are publishing more than 80, more than 85 papers per year. The research activities of the department focus on various areas of, or you can say in all the areas of chemistry, with like synthetic organic chemistry, supramolecular chemistry, structural inorganic chemistry, drug design, material science, electrochemistry, chemistry of surfactants, chemistry of oils and fats, theoretical chemistry, thermodynamics and analytical chemistry, to name a few. The contribution of the department has been recognized both nationally and internationally, and the faculty has been awarded fellowships of various scientific institutes and various scientific bodies, FNASC, FASC, Fellow Academy of Sciences, CRSI Gold Medal, Silver Medal, as well as Bronze Medals. They have been won by the faculty. Bhagyatara Award has also been won. Professor MS Wadia Award, Brain Pool Fellow Award, Coastal Chemical Society Award, Thomson Reuters Research Excellence India Citation Award, Commonwealth Academic Fellowship Award, DARD Fellowship, JSPS Fellowship, Humboldt Fellowships are a few to name that have been won, that have been received by our faculty. The department, through its university library, receives online publications, online journals from various top publishing houses like Royal Society of Chemistry, American Chemical Society, Elsevier, Taylor and Francis, Kluwer Incorporation, etc. Several faculty members also have exposure to foreign research laboratories in the form of postdoctoral and visiting scientist fellowship program. The department, as we are organizing today, as a matter of fact, during the last 2 years, due to COVID, we could not organize a seminar. We have been organizing national as well as international symposium at various times, and even the last symposium that was organized was under the stewardship of Professor Manoj Kumar, Asian Chip Program. That was again an international seminar. In order to have productive exposure, the department has research collaborations with some elite Indian state universities, IITs, as well as with international laboratories. To name a few, we have active research collaboration with University of California, San Francisco, Rega Institute, Belgium, Chinese Academy of Sciences, Beijing, CNRS, Toulouse, France, as well as our faculty has received grants from British Council. The department has been granted the status of Center for Advanced Studies way back in 2008, and UGC in its first phase gave a grant of 136 lakhs to the department. In the second phase, we received a grant of 300 lakhs. The Department of Science and Technology has also funded us lavishly. We received 256 lakhs under the FISC program during the year 2009, 295 lakhs during the period 2008 to 2022. Additionally, due to the high H factor of the university, in which our department has a considerable contribution, the university has received PERS grant from DST also, which have also given us a ample contribution to improve our facilities in the department. We have also received you can say ample contribution from the university under the University with the Potential for Excellence program as well as RUSA program of the university. The state-of-the-art facilities that we have acquired with all these grants include 2 NMR spectrometers, 400, 1 and 1 500 megahertz machines, X-ray powder as well as single crystal diffractometer, IR with variable temperature facility, fluorescence spectrophotometers, a number of them, HPLC, tensiometer, magnetic susceptibility balance, molecular modeling software, DTA, TGA, differential scanning calorimetry, then isothermal calorimeter, microwave synthesizer, PET, surface area analyzer, dynamic light scattering, UV visible NIR, and recently the machine is yet to be installed. We have procured CD spectrophotometer. We also have atomic force microscopy, and in our common facility that has been created by the university, we also have that confocal microscopy, transmission electron microscopy, scanning electron microscopy, etc. So you name any instrument and we have. Then recently, with the particular interest shown by our worthy Vice Chancellor, our practical labs have been modernized. 4 of the students' labs have been modernized with an investment of 140 lakhs. All the research labs of the department are equipped with modern fume hoods. So keeping the tradition of our forefathers, our seniors, our founders, we not only utilize these facilities at our institution level with other departments, we share these facilities, but we also share these facilities with the neighboring institutes and provide them with the facilities that we have depending upon the running expenditure. We may be charging very minor amount of that is being acquired or received from the users. Even in our university, our students also contribute towards the maintenance of these facilities. I will be failing if I don't tell you about the alumni of this department. The alumni of this department is well established, and they are not only working in the fields related to chemical sciences, but also throughout, you can say, all sort of fields. They are available, they are earning their livelihoods from banking, from policing, from military operations. They are in, even one of our alumni who was our batchmate has after acquiring his master's degree done a course in business communication and has been a journalist with Economic Times of India, Business World, Business Standard, and way back in 2008 was awarded with an honor by President of India. So these are a few things that I could share with you, and I am really thankful to you all for patient ear that you have given to me, and I am really thankful to the organizers of this symposium for giving me an opportunity to tell you about my department. Thank you. Thank you very much.
Thank you very much, sir, for giving such a detailed information about our department. So now we are going to release the abstract book. So I would like to invite Professor Sukhpreet Singh to open or to release the abstract book.
साइड कर लिया मैं
Thank you very much, sir. So now I invite Dr. M.S. Batra and Dr. J.S. Gandhi, a close friend of Professor Manoj Kumar, and Dr. Nagendra Babu, a former student of Professor Manoj Kumar, to present first student of Professor Manoj Kumar to present a personalized book of Professor Manoj Kumar.
Thank you. ਭਾਜੀ ਸਰਦਾਰ ਜੀ ਤੋਂ ਲਾਗੇ ਉਹਨਾਂ ਦੇ ਲਾਗੇ ਚਲੇ ਜਾਣਾ ਹੈ ਮੈਂ ਸਾਈਡ ਤੋਂ ਕਰ ਲੈਣਾ ਫਿਰ ਕੋਈ ਗੱਲ ਨਹੀਂ
So all other students, they can join, the former students. Thank you very much, sir. So I again request Dr. Batra and Dr. Gandhi to present a sampling to Professor Manoj Kumar as a token of gratitude sent by Professor Amitava Das. He was supposed to attend this symposium, but due to some health issue, he could not make it. So thank you very much, sir. So now I request our senior most faculty, Professor Kamaljeet Singh, to present a vote of thanks. Please, sir.
Oof, what a day, huh? So, yeah, it's a great pleasure to actually propose vote of thanks for this function. And before I do so, it's my pleasant duty to congratulate once again my friend Professor Manoj Kumar on the occasion of his 60th birthday. So we were waiting for this day actually, and I always had in mind, and even I shared with Paramjit that there should be some celebration to celebrate his birthday. And it's good that organizers they took initiative and symposium is organized, and as well as we are all participating in this, in congratulating him. If we look at Hinduism, let's say Vedas, then according to Vedas, I hope I'm right, this rate average life cycle of a human being to be 120 years. And that clearly indicates the relevance of 60 years celebration, because when you celebrate 60 years birthday, it means you have already achieved some sort of karma, artha, kama, and what you call the other one, dharma, some content of that. And henceforth, after 60 years,
Hello.
Thank you. Yeah. So when you start your second innings, so main focus.
I cannot hear you.
All right. Can you Okay. Can you hear now? All right. So I think there's some technical, probably sort it out. So I was telling that the second innings, which is more important, in fact, you pay more attention to the family as well as accomplish other jobs, and as well as do research. You can continue doing that also for as long as you wish. So Professor Jaspal Singh, Vice Chancellor, he had to join us due to some reasons. He couldn't join us. So it's my present duty, in fact, to thank him for allowing us to organize this function and his wholehearted support that he rendered to us, for organizing this. And it would have been really great that he was here, but unfortunately he couldn't come. My thanks to all the invited speakers from within India. Some of these are sitting here in the audience, and some joining online. So that because they spared their time and they agreed to present their work during this symposium. And my special thanks to Professor Yoon from South Korea, as well as Professor Kim from South Korea, who have agreed to deliver lectures through online mode. And all the faculty members who participated in the organization of this function, I extend my heartfelt thanks to them also, especially to the students, the present students of the department, the past students, especially of Dr. Manoj Kumar's group. So they have all joined to celebrate this event, and we are really grateful for all their contributions. And as you could see that the old colleagues of Manoj, old friends, Dr. Patra is there, Dr. Gandhi is there, and our own, super innovative colleagues are sitting here. So we are grateful to all of them because they came here to participate in this symposium. Then such functions, they are not complete without the generous contribution in terms of finance in supporting this event. And for that specifically, I would like to place on record thanks to the Wiley for hosting the poster work, then RSC Advances and RSC for supporting the hospitality of this symposium. And special thanks to Mr. Sandeep Singh and Dr. Pupinder Singh for doing all this, online thing here. And finally CRSI, because the local chapter also contributed, so we extend our thanks to them also. And I wish this symposium great success, and so we'll be waiting, subsequently in all the sessions and start the process. Thank you so much.
So thank you very much, sir, for your best wishes. So dear colleagues and friends, we are going to start our first technical session of this symposium. So this session will be having 3 lectures. So this session would be chaired by Professor Subodh Kumar. So Professor Subodh Kumar has contributed enormously for the growth of supramolecular chemistry field in our department. He has over 250 publications in the reputed journals. So I invite Professor Subodh Kumar for the next proceeding. So please, sir.
Friends, it's time to sharing moments. In addition to the scientific discussions, probably at this moment the memories of the past are more important. Professor Manoj Kumar and myself were on the adjacent shelves when we did our PhD. that was the time in 80s, early 80s. Much of the facilities which Professor Sukhpreet has elaborated today, they were not available in the department or in the nearby institutions. So the progress was more dependent on the hard work made by the students and the teachers, rather than having the dependence on the facilities. Just to make a memory of those days, our teacher, Professor Harjit Singh, always had been in the department at 7 o'clock. And throughout his life, he never reached late. If his door is not open at 7, that means he is not in Amritsar. Professor Sukhpreet has mentioned about the hard work made by the students, even by the present students. But those were the days no one was looking for when the sun will set. The students had been working in the department. I don't know when they were switching off the lights, because we had to go to our own home, which was 8 kilometers from here. But we really did not know that when the lights were switched off in the department. Once I had to receive his machine and came at 12 o'clock and found that the department is still working, as in the day. Or probably the students were working harder in the nights in comparison to the days. Not only that, we were having a bicycles, Professor Manoj and myself. I should not say late, but it was definitely not in the evening. When we move from the university, we will not be able to see a light on the streets till we reach Ranikabad. The first lights were observed when we reached at Ranikabad. And by that time, we were many times feeling very hungry and have shared jalebis at that stage. So those are the memories when we worked together for hours and hours in the same lab on the adjacent benches. Today I congratulate him for working very hard, getting an equally able partner who could contribute to extensively to his contributions further. I also consider, just like the evening, this moment is just beginning of the evening. One has to moved out of many responsibilities. One has not to attend the many meetings or in the department or in the university. One is getting a more fair time to work on the things. And I hope the second inning of Professor Manoj will be more fruitful, whatever has been the first inning. You can just look into the future, that how it will be, you can see by just looking into the past which you have observed. Not saying much here about Professor Manoj, because I have spent more than 35 years with him. So I just come to the scientific discussions. It's honor to me to introduce the first speaker of today's symposium, Professor J.S. Kim. Again, by his publications, I have read his publications from the last 35 years. He had been working, Professor Yoon and Professor Kim from South Korea. They had been working in supramolecular chemistry, and we had shared many moments through the publications. Professor Kim is presently professor at Korea University, Seoul. Before this, he has worked at a number of other universities. Gyeongnam University, Dankong University, etc. He is an internationally renowned person. He is competing with all the scientists over the world, and he has international collaborations with USA, England, and many other countries too. I just invite Professor J.S. Kim for today's lecture. Professor J.S. Kim, please.
Excuse me?
Yeah.
Okay, hello? Can you hear me? Okay. Okay. Professor Manoj Kumar, can you hear me? Today is a very, very special day for you. The 6th birthday of Professor Manoj Kumar. It is my great honor to give a talk in here to special talk international symposium. This is advanced in self-assembling material in supramolecular chemistry. So also that I'm very happy and delighted to give a first the plenary lecture. So the title that I want to talk about the small molecule based delivery system, and it's bioimaging. Actually, the context that I want to say, so many times in many conferences I've given already. So probably you guys already understand pretty much well. Beforehand, as we look at in here, there's a very handsome guy, that Professor Manoj Kumar. I have known him more than 20 years since we have same research field in supramolecular chemistry and fluorescence sensors. So as I said that, really, I congratulated Professor Manoj Kumar, 60
birthday. Actually, next year I'm just 60 years old. Let me see what happens. I will invite Manoj Kumar next year to give a special talk. The other good memory is that one of my big friend here, Professor Jiyoung Kim, he is another plenary lecturer today, and then we have frequently meet many conferences, especially the chemosensor and drug delivery in the China or Korea and India as well. So the 2019 that Manoj Kumar was the host for the Asian Chip Conference that I and the Professor Jiyoung Myun were invited in the give a talk there in Amritsar, and it is a very fantastic memory. I spent 6 days in Amritsar in India with all my students and other colleagues. I would thank you once again that Manoj Kumar is a wonderful work. And it's also that Professor Jonathan Sessler, then he is also my strong collaborator. And then Wang Chu in China, then he also was the host in the Asian Chip conference that actually he invited Professor Manoj Kumar, me, and John Sessler together. Other than this photo, I do have many photos together we taken with Manoj Kumar, with my very old friend and good friend together. So I want to give a one, very interesting talk, this moment, is because in Guru Nanak University, they send me many very wonderful postdoc to me, and then I do have many nice people with them, Jackson, Angivant, and Cam. They got the PhD from Manoj Kumar and then Kamaljit Singh. So I also, once again, I appreciated their supervision. They sending me the wonderful student to me. Now they got a permanent job in the world, not only in India but the USA and the Canada. So I want to talk about my talk in here. Many years I've been working on the cancer, so developing anti-cancer agent to have it on the selectively treatment of the cancer cell of the normal cell. What are the seriousness is that actually global cancer incidence is for example, America 21% and European 23%, Africa 5.8%, I would say 1.4%. However, I don't know why the Asia is 48.4%. Okay, so the exceptionally very large amount of the cancer incident rate. So probably because of the many different environment, Americas. But anyhow, we have to circumvent this big problem with the cancer situation that we have to solve. So many times I given like this kind of cartoon. That suppose we have a liver cancer, right? Then one of the representative, the anti-cancer agent for the liver cancer is doxorubicin. So the bed injection after that is supposed to go to the liver cancer only. However, unfortunately, this goes everywhere, especially hair root and the mucositis and germ cell, which are very weak cell, proliferative, easy proliferative, the cell. For example, hair root and mucositis and some cell. This is one. Once we have the cancer and the medication, anti-cancer agent, most of the time we see that many people have the hair root out and germ cell hurt. That makes a big problem. So what people say that any people like a chemist and the doctor, they develop and discover new drug which can cure the liver cancer only or cancer only, not the mucositis, hair root, germ cell, so to speak. Very high selectivity. They deserve to get the Nobel Prize. which means that all the world, the doctors and chemists, they are working on and pay attention to develop and discover the drug, but so far it's not very successful. So this is why I just started working on this to develop the new drug, small molecule-based prodrug, which can target the cancer only and working selectively in cancer over the normal cell. So this kind of the concern that I've been working more than 10 years, then making some papers. So as you see that I just listed all the JAX paper we made so far. By the way, from this JAX paper, 4 to 5 papers from Indian postdoc from my lab that came from Manoj Kumar's lab and then Kamalji Singh's lab. So that I just hear and appreciate it very much their wonderful work and the great work. So I want to describe the strategy that we have working on. For example, if you look at the cancer cell, then we, so to speak, the microenvironment targeted DDS, that I hear the list of the 3 things, but more than that, however, the time limited, I just introduced 3 important, the enzyme, the mechanism here. That first of all, glutathione is overexpressed in the cancer cell of the normal cell. So one of the strategy to utilize the GSH-based drug delivery is that we can use the disulfide. And the other one is ROS. For example, the cancer cell, ROS, hydrogen peroxide, is the more expressed than normal cell. Something like that. Not only hydrogen, but singular oxygen, superoxide, whatever. And then the other important thing is the P-glycoprotein, which is responsible for the multi-drug resistance. Which means even if you take a medication, that doesn't work. Why? Because multi-drug resistance. Drug is once it gets into cell, but doesn't work. But however, right after that, then efflux out. So which result in the less effective, the cure of the cancer cell. So we're concerned about those 3 things that I will just describe. 3 things very briefly today. So then, for example, let's go back to 10 years back in the 2012. Then I made one first paper with the drug delivery system using the theranostic the strategy. At the moment, I was happy that we have just cover. The strategy is, for example, like this. We already designed and we made this compound 1. This compound is very interesting, that the composing of the RGD peptide cancer targeting, and then which means that as long as the compound having an RGD peptide, then the whole molecule is going to be guided to the cancer cell over the normal cell, which means the very high selectivity. This is very well known. And then the other one is camptothecin, which is already commercialized in the hospital, not only Korea, United States, even India, in Japan. This is very, very prevalent in the hospital anti-cancer drug. And then the conjugated disulfide, and then this is imaging part of the naphthalene here. So for example, in here, the tumor cell, if you look at the surface, there's many receptor which is integrated. However, if you look at the normal cell, compared to normal cell, the receptor on the surface of tumor cells are overexpressed compared to normal cell. So this receptor is endocytosis, and you see the naphthalene, the fluorescence maxima is 473 nanometers. But after in here, that the cancer cell, the hydrogen peroxide, GSH is more expressed than cancer cell. So GSH triggers the bond between disulfide by SN2 reaction and organic chemistry very simply. And we see the imaging change from the 473 to the 545 because of from the change into this carbamate into just a simple NH2. So the mode of action is that, for example, as I mentioned, this compound design and the GSH in the presence, and then bond between third bond is cleaved out here by the GSH, which is overexpression of the cancer cell, and followed by cyclization. And still we have the 473 nanometers. However, after cyclization, then not only that the active drug CPT camptothecin delivered in the cancer cell, at the same time, then we see the process in the change. I mean, the next change from the 473 to 535, right? So that we call that theranostic, which means that therapy and diagnosis at the same time. You know, I can say that 10 years ago, this is the first example that the theranostic molecule, you know, a small molecule-based theranostics. I mean, this kind of self-emulative, you know, the based process change was reported before I published it. But novelty in this case that we attaching the real drug here. So initially there was the inactive drug, but however, in the case of GSH, which is overexpression cancer cell, then we see that inactive drug during to change the active drug camptothecin, and at the same time the first change, and then I'll see that imaging very easily. Our lab have Rajesh Kumar. He got the PhD from Professor Manoj a long time ago, and he joined my lab in 2012, I guess, as a postdoc. He designed this compound. It looks like very complicated, but sensitive point of view is very simple. And then actually, this is well known that this kind of compound, ethylene bromide, actually this is fluorescent molecule. However, it is not fluorescence if any other substitute is connected in here. But also that this compound also kind of very weak. However, this ethylene bromide is very strong fluorescence only if this molecule is intercalated with the DNA. They're very, very strong fluorescence. This is one of very interesting strategies to see. And then this is the biotin. This is cancer targeting, which is very well known. And then this is hydrogen peroxide triggering. See, in organic chemistry textbook, then they mention carbon borate. The bond is very lipid in the presence of hydrogen peroxide. Likewise, the rearrangement. So then, for example, and this is the 5-deoxy-5 ingredient. This is real drug in the hospital. They all attached in here. So it doesn't seem to be very symmetric. However, in synthetic point of view, it's not very difficult. We made this compound, and then this compound, as I said, in the presence of hydrogen peroxide, bond between carbon and borate is cleaved out and changed OH, and they self-emulate everything and deliver this ethylene bromide and as well as the drug here. So this is cartoon that actually is redrawn like this. This is drug and the apoptotic marker and the targeting unit. This compound is the receptor mediated endocytosis by biotin with very high selectivity of cancer cell and normal cell. It localized in the mitochondria, very interesting. Is it because of ethylene bromide? And then after that get into the mitochondria selectively, and the hydrogen peroxide more expressed in mitochondria is cleaved out the drug, and the end up we observe that the mitochondria apoptosis at the end, and the in vivo test also we have done. So we injected the tail vein with our compound, naming the therapy Z7. Comparing the control, we see that very much decreasing down of the tumor size here. When you use that our compound Z7, compared to 5FU is commercialized in the hospital, we cannot compare that actually. Very dramatically, our compound tumor diameter of the xenograft mouse doesn't grow anymore. Very successful. And then Kumar, the Rajesh Kumar, the group Nana, Delhi University, he came from that. And his first author paper, we made a jazz, but I'm very happy to have a cover like this. We made the cover imaging like this. This compound, as I said, the whole compound the small molecule. Then right after that, in the mitochondria targeting, and then the drug delivery. So Rajesh Kumar, not only jazz, but he made the other very nice Angivante and many other nice paper he published out, and very appreciated. He moved to, I think, in Canada, I think. All right, and then this one that also that they have done by the Amit Sharma, that he got a PhD from Professor Kamarjit Singh a long time ago, and he joined my lab 7 years ago, and then he now returned back to India and they got a permanent job. We made like some very interesting story that actually, as I before said, that drug resistance we have to consider. For example, once you take a medication, the drug comes in the cell, and that automatically sometime later, that drug could be influxed out by ATP. So then, as you know that once drug is influxed out, then the drug efficacy is much diminished, right? So we have to solve that problem. We have to block that drug efflux somehow. Then I want to introduce that the detailed strategy. So the drug resistance is barrier to successful clinical outcome. So this is a cell inside, and this is a cell outside. As I said before, once drug comes in, and that should work, either mitochondrial damage or nuclear damage. However, sometime later, this drug comes out again, so to speak, influx out. So which can make that the drug efficacy is less, right? So one of the mode of action to make it is the P-glycoprotein is developed. So what the mechanism is that this drug comes in and this comes out by the ATP promoter. ATP change into the ATP generate one the phosphoric acid. So we have blocked this way, then we can optimize the drug efficacy, right? We have to make the drug reside very safely inside of the cell to work out very nicely. So the Amit Sharma, the drug resistance poses a serious risk in the 90% of metastatic cancer patients. So Amit Sharma from also that group, Nana University, he made one JAX, one Angivant, and one CAM. I want to introduce CAM paper. He was published in 2018. He designed this compound, and very interestingly that this moiety dichloroacetic acid. So this is pyruvate dehydrogenase kinase inhibitor. Start pyruvate approximate and offer possibility that the drug release. Okay, and then this is doxorubicin, the chemotherapeutic drug, and then this is mitochondria. So triphenylphosphate is very well known, targeting the mitochondria. The whole molecule safely get into the mitochondria, and then by hydrolysis and the TCA will be delivered. And this is block that the mechanism to go to the wobble effect, and then finally that the ATP, total amount of ATP is reduced. So the mechanism that we already found or reported in the paper. So esterase, which is overexpressed in the cancer cell, and then clipped out in here, and then from the cell immolated, and then doxorubicin delivered. Whole mechanism happens in the mitochondria. And then this is time goes by. For instance, enhancement that comes in it tells us that the doxorubicin release, right? And then after drug activation and the CO2 delivered here, and then also the active doxorubicin delivered. So most important thing is that actually initially doxorubicin is delivered into the mitochondria. However, sometime later, the leaking out final destination doxorubicin was found to be in the nucleus. The end up, the cancer cell died. Okay, and then this is, we say that the compound we made as control. This is our compound, and this is control experiment. This is without a mitochondrial targeting, and then here without a dichloride, and here without the cancer targeting here. Then also that without the dichloride in here. So the comparison to everything, the one we know that this company, however, what we know that our compound selectively localized in the mitochondria, and then the first intensity here, that C1, if you look at C1, then here we see that very selectivity in the cancer cell over the nose. So those two, those two, the cell is the normal cell, and those two is the cancer cell, right? So we see that very selectively observed in the case of the C1 or final compound. Okay, right. So and the first intensity as well, that the C1 MCF7 cell, and this one is MCF7 cell, but this is doxorubicin resistant cell. All right. So even in the case of the doxorubicin, the resistant cell, we see the first enhancement. However, in the case of C2, this one without any the cancer mitochondrial targeting, MCF7, the resistant cell, doxorubicin resistant cell, MCF7, we don't see the further intensity here. So we observe that actually here, that in the case of the designed compound C1, shows very selectively, specifically in the doxorubicin, the resistant cell. Because we are now, as I mentioned, that this project is proposing to solve the problem of the drug resistance of the cancer. All right. So this also the selectivity, that the end of time goes by, that the nucleus and mitochondria. Initially, we see that our compound local in mitochondria, and the end of after 36 hours later, the final compound destination is the nucleus. Okay, so this is total, the mechanism here, that actually once the cancer cell from the glucose glycylation, and then the change into pyruvate, if it goes this way, then we call that a Wabel effect to make the lactate in the combination. However, we're going to change by the inhibition of the PDK with the TCA, then our the whole system goes to the normal situation, right? So that we see that they also that the in vivo study, that we see that even the doxorubicin resistant MCF7 general mouse, the time goes by, the tumor size will decrease down like this. Okay, then tumor volume is around even after 40 hours, 40 weeks, 40 days, then no any significant tumor volume enhancement at all. And then final, the topic that I mentioned is the cancer recurrence. Okay, as you mentioned, you notice that recurrence is very, very serious in these days, right? Even the cancer you have, then the cure everything. After 5 years later, you observe that the other, the metastatic cancer or the recurrence. So the cancer recurrence rate of stomach 6, this problem. So what we can do is that we have to concern about the cancer stem cell. Actually, one of the big issues with the cancer stem cell is that cancer stem cell is that, for example, even if you treated the anti-cancer agent, doxorubicin, chemotherapy, whatever, in the hospital, you cannot eliminate cancer stem cell. This is a big problem. Why? Because cancer stem cell is very, very strong. They do have many drug efflux, and then there are many the self-linear characteristics, and then there are many other the strong, aspect that cancer stem cell we cannot eliminate easily. So what we have to do, you have to make a compound and product can target only the cancer stem cell, not only the cancer cell, but also the cancer stem cell. Otherwise, you cannot eliminate cancer at all. Why? Because cancer stem cells later on they grow to the big cancer tumor, and as well as the metastasis, right? So here there's actually the cancer stems are very serious. There are many 1, 2, 3, 4, 5, 6. The factor that manage the cancer stem cell, they are not killed at all. So the cancer stem cell, cancer initial cell is metastatic recurrence capacity. Cancer stems have ability to differentiate the tumors. The cancer stems are highly resistant anti-cancer tumor. So suppose this is tumor and this is cancer stem cell, and the tumor formation. So which means the survival of the cancer stem cell we cannot kill at all. We medication, heavy, the dose, but the tumor and cancer stem cell cannot be died at all. So these survived cancer stem cell developed to the cancer cell metastatic recurrence by survived cancer stem cell. But anyway, our finally eliminate this cancer stem cell anyway. Otherwise, big problem. So suppose we design a compound that cancer stem cell preferentially survive in the hypoxia niche. That is already known. Target cancer stem cell hypoxia niche to activate the drug delivery system. Suppose we design this compound, hypoxia trigger cancer stem cell targeted molecular theranostics. Suppose we deliver it to here. This is the cancer stem cell, and cleaved up by hypoxia. Then not only cancer cell but also cancer stem cell can be eliminated. So that there's no metastatic, no recurrence. So these days, 5 years back, there's very, very hot topic in the world, in the cancer field. So they reported the Nature review. Single cell analysis revealed the stem cell programmed in the human metastatic breast cancer. So we made a JACS paper in the last year as a cover. So we designed this compound, very simply, that we call AZ means acetosamide, and CDF means curcumin. This is curcumin. Curcumin, that curcumin is contains in the curry in the Indian food. Many Indian food. See, one of the component is the curcumin. The difluorine CDF means curcumin difluoride. This compound is connected in here. So hypoxic trigger, this is hypoxy trimethyl nitrothiophane. Suppose we designed this compound. If you look at here, the reduction potential from right to left, this is the highly responsive and required short step. And we used it actually this one with the nitro reductase, the selective, the moiety, but after all, we observed that the 2-nitrothiopane is working nicely and best. And then this is acetosamide. Acetosamide is a cancer cell targeting unit, right? And then because this acetylamide is able to recognize the CA9, the enzyme that overexpressed in the cancer cell, and then this is an anti-cancer stem cell drug. It is known but not the old one. Very simply, the people they develop these anti-cancer stem cell drug. However, this anti-stem cell, the anti-cancer stem cell develop, however, that the people that make the publication, but the selectivity was the problem. So we used this compound, the drug can be delivered very selectively in the cancer stem cell. So we finally made it very lucky to make the Jack's cover. This was first time the cancer stem type in small molecule able to prevent tumorigenesis in the animal. Mode of action is this compound we designed, the synthesis is very successful, and then this is the reference compound with attachment of the naphthalene for the imaging instead of drug in here. So this is like one of the reference without a drug. This is a reference without the targeting cancer stem cell targeting. Right? So, for example, this is inactive on the novoxia, this is active on the hypoxia. So, this one is, for example, in the hypoxia system, that the nitric compound reduced to NH2. Then after central-immolate, like the electron transfer, finally the curcumin delivered as well as the whole other compound delivered, right? So the in vitro result is CD133. This CD133 process cell is the cancer stem cell marker by aging non-dependent agent. So when you treat a compound, the also treated MD-NB231. This is triple breast cancer, and the CD133 plus the cell. We see that a little bit brighter in the fluorescence imaging in the hypoxia in the case of the CD133, which is one of the biomarker of the cancer stem cell. And then if you look at the CD133 negative and the CD133 positive, so we see that more active the change in the cell viability in the hypoxia system. In this case, that the case of the CD133 positives. Alright, it's in vivo, the genital tumor imaging treatment using the AZNAP, and then after that, our compound in the CDF, that after 5 weeks later, then no more and tumor volume of the general mouse enhancement, right? So and then also that we also tested at CD133 breast cancer that see only in our case of the compound showed very the effective in terms of the tumor weight, right? So thank you very much for your kind attention to me. Finally, I just appreciate it here. The many appreciated the research fellow and the graduate student, especially the number of collaborators internationally. So one in here that Manoj Kumar. I'm sorry, I was put in here that her name is missing. The Bandana Bala. He is the very beautiful, the wife of the Manoj Kumar. We also collaborate with him, with her, and then also that the 2 or 3 postdocs that from the Bandana Bala's the lab, and I appreciate her also that sending me that very smart person to me, and then we are very successful in our research. All right, so thank you very much, and then we all appreciate also again, and then congratulations, Manoj Kumar, the 6th birthday. Here I mentioned that so far we have many the student here. There are two the postdoc here that this is Dr. Nam Singh, and then this is Paramish Jangiri, the 2 person came from India, and they are working very hard now. And then recently, the Paramesh Jangili made Angivanti paper this year as the cover, and then Namsing now he's writing a paper in the text. Okay, then finally, once I have to say that congratulate then Professor Manoj Kumar, the celebrating 60th birthday. Thank you very much. Thank you.
Thank you, Professor Chin, for your nice lecture. And also the memories you have with Professor Manoj Kumar. Professor Kim, can you hear me? Hello. Hello. There is one question from the audience. Boron neutron capture therapy is proving helpful for the eliminating the human stem cells. Is it true?
And then also that these conventional drug do not have any targeting stem cell targeting. So in this case, even though you have like outside treatment part, I don't think it works.
Thank you, Professor. Again, and thank you for sharing your time, valuable time with us.
Okay, so I should close the sharing, right?
Yes. Thank you again.
Yeah. Thank you.
So you can see the souvenir on the screen, which will be sent to you. Okay, fine.
Thank you. Thank you.
So for the next speaker for the symposium is Professor
Parmeshwar Krishnan Iyer. He received his PhD from Central Salt Marine Chemical Research Institute. He did his postdoctoral research at Technion University, University of California, and then Western Reserve University, USA. In 2004, he joined as faculty at IIT Guwahati, where he is currently a professor in chemistry. He is also the Public Relations at IIT since July 2019. His research interests include design and development of functional materials and their applications in photovoltaics, LED transistors, memory sensors, etc. He has guided 27 PhD students and several postdocs. He has more than 200 international publications. He is also an associate editor of Natural Scientific Reports, Frontiers in Medical Technology, and also on the editorial board member of ACS Sensors and ACS Applied Nanomaterials, ACS Applied Biomaterials, RSC Material Chemistry Frontiers. He has received several national and international awards and serves as an expert member in various national and international scientific bodies. I invite Professor Iyer.
Thank you.
So today's talk is for 22 minutes and 3 minutes will be for discussion. So I invite again Professor Iyer. Professor Iyer.
Thank you very much. Am I audible?
Yes, yes.
Namaskar. Very good morning. It's a great occasion, and I would like to begin by wishing Professor Manoj Kumar on the 60th happy birthday, and I hope and wish that he has a very healthy and a very long life, and hope to have more interactions with him in the future. So, Professor Manoj Kumar, best wishes from me. Hopefully, we'll be able to meet in person and have a bigger celebration. This is also a great occasion, to celebrate his immense contribution to the field of chemistry and its application. You all know, I don't need to highlight here, but definitely, since I work in quite similar area of development of various functional materials and applications in lot of areas of material science, especially for for the fluorescent sensors, definitely for catalysis, and in multiple areas of supramolecular chemistry. I have been following him for at least close to 2 decades, and a lot of things that we do, a lot of things that their entire group does. It's very fascinating to see how well he has contributed to so many areas. Where being at GNDU, and I definitely cherish reading all his research papers. I'll also be presenting some of this work which have overlap with what he has been contributing, and I really look forward for more interaction. I really feel very fortunate that I have been invited to be part of these celebrations, and I am thankful to the entire GNDU family, Professor Vandana, Professor Prof, who have been writing to me and even calling me to be part of this event. And I really am very fortunate to have been part of this meeting and share a few of our results on how things are moving forward at our end, and also in terms of science and applications to multiple areas. So once again, thank you all for inviting me. So definitely, I look forward to inviting you all from who are there in the meeting, and definitely Professor Manoj Kumar, Madam Vandana, and all my colleagues, my friends, very close friends at GNDU to our campus. Very beautiful. If time permits, I'll be showing some photographs towards the end of my lecture. So as you all can see, we work on multiple areas of organic. We have also moved towards hybrid materials, organic materials, polymers, and hybrid materials. And I was also very fortunate that though I am part of only the chemistry department here, now I have been associated for the past 15 years to the Center for Nanotechnology. And last year IIT Guwahati has opened few schools, and we have now started the School for Health, Science and Technology. It's an offshoot of the Center for Nanotechnology based on some very large projects that we got from various funding agencies. Now, why this is very important? Because being chemists, we all are very good at making molecules,
Now, when we look at some applications, that is where a lot of problems come in. And at Center for Nanotechnology, we have been fortunate to get research scholars, PhD students from various backgrounds, from physics, from electronics, from whichever background we want. And similarly, in the School for Health Science and Technology, we have been able to collaborate, not just collaborate with various doctors, but also get students from biomedical engineering, even medical doctors doing various master's programs and come and work with us. So this interdisciplinary environment has really given us a lot of flexibility to try out the compound that we develop at the chemistry department into multiple areas, making devices and health science or biomedical devices as well. I'll be touching upon few of the topics that we have been working, and as I mentioned, more important today is celebration of Professor Manoj Kumar's 60th birthday. So once again, with this slide, I congratulate him for reaching his milestone and his immense contribution to the areas of both this self-assembled materials, supramolecular chemistry, and their applications to a lot of different allied areas. I move forward. So after joining IIT Guwahati, this has been our journey. We either buy a lot of molecules, we synthesize small molecules, we convert them into conjugated polymers, sometimes even non-conjugated polymers, and various kinds of hybrid materials with these polymers. And we look into applications, various devices for based on LEDs, the photovoltaic devices, thin film transistors, and these various kinds of sensors and memory devices which we have started very recently. And their applications are both in the areas of energy, environment, and other devices. During this journey, we have also been fortunate to develop few technologies, and close to 12 technologies now have been transferred to industries. We are also now involved in startup companies, one with this RR Animal Healthcare, and our own startup, Analytics R&D, where we are now incorporating AI-based technologies for developing a lot of applications in right from hydrology, geology to health sciences, and including finding of defects in these photovoltaic, LED, or transistor devices. So it's coming very handy that we have a lot of images from various techniques like AFM, FESEM, simple confocal microscopy, but sometimes proper analysis and study of these images is very, very important. With the advent of this AI and ML techniques, that is now possible, and even if you have hundreds of images, analyze them and get data out of that and predict results is very important. That is what we are trying to do now with this analytics R&D, and definitely we have been contributing during this COVID also with RR Animal Healthcare. If time permits, so then I will also show you this. We focus a lot in our group on developing conjugated polymers. And just for the young researchers who are there, we focus on this class of platform mainly because they are highly fluorescent, definitely. But we can introduce certain functional group and where we can make them highly sensitive, and their operation is also very, very easy and very, very low concentration. They give out a very high output, and that also results in very high selectivity, very high sensitivity. And by changing the functional group, which I will be showing today, we can get specific selectivity also. We can introduce ionic groups, we can introduce non-ionic groups, neutral groups, and we can control the solubility in either water or organic solvents. And most importantly, we can immobilize them on any membranes, any polymeric membranes. We can make films on any kind of substrates. It can be a silicon substrate, it can be glass, it can be gallium nitride or any other plastic substrate, and we can make films out of that, and that leads to making various kinds of devices. Most importantly, whenever you're using this conjugated polymers, what happens is whenever you're doing the biological studies, you don't need an additional dye to label it. So they themselves are very, very emissive, highly emissive, and that removes one more step, or the dyes sometimes they're very, very expensive to get. You can directly get it from this conjugated polymer. So these are some of the broad positive things about this material. There are definitely scope of improvement. A lot of things can be done, a lot of things can be modified, tuned, and hopefully I'll be able to convince you all that these kind of materials have a very important place in the field of in multiple areas of not just chemistry but also their applications. I start with a very basic example why these molecules are very important. As I mentioned, this is a polyacyclic molecule. They possess this single and a double bond, and this is what leads to most of the properties, the semiconducting behavior. And when we introduce various functionality, not just an aromatic groups, but also heterocyclic molecules, we can tune their band gap. And when we are able to tune this band gap by replacing these functional groups, we can achieve a lot of different applications. And most importantly, the one application that we achieve is called the molecular wire effect. It's very, very useful for the sensors, biosensors or chemical sensors. Is that whenever you have backbone, so this is the conjugated backbone, and whenever you interact with an analyte, and these are the functional groups which are able to bind a specific analyte. Okay, now whenever we have a solution of this conjugated polymer, we add an analyte to this, and what happens is that usually even if it binds to just one or two or even less than that, just one of this functional group, what happens is that there is a signal that goes into this backbone, and more than one of this backbone they get switched off or switched on, and that is the reason why these molecules or these polymers are highly sensitive. For example, if I add to one of these, you can see what happens. Okay, so you don't need that this analyte which is there, it needs to go and bind to all the receptor sites that are there on this polymer. Even if there are a few of them, this is what results. The turn off or the turn on that happens in the fluorescent molecule is very, very remarkable. It can be seen very, very clearly, and that is where the sensitivity of this polymer-based system is much higher than sometimes small molecule-based system. Okay, I'll show you a practical example. This is one of the journey that we started doing very, very early. We can do the synthesis. As I mentioned, we introduce this functional group. We start with a small molecule. We functionalize this with a simple phenyl molecule. We make a copolymer here with a benzene ring. This is a neutral molecule. You deprotect this, and you get an ionic molecule, and an anionic molecule with the sodium salt here. And you can see that it's highly fluorescent in water. You add iron to this. It's very, very selective. This functional group is very selective to iron, and there is a complete quenching of this fluorescence. And this polymer, because it's ionic group, around more than 100 milligram, it's soluble in water. One important thing is that it also is necessary that we control the molecular weight. Okay, so this is a very important factor in this. If it's very, very high, sometimes we lose the solubility aspect. In this case, the molecular weight was a little more than 10,000, and we can control all the properties. So here you can see when we add this, the molecular wire effect can be seen very, very nicely. When you add this, you see the fluorescence quenching, very, very drastic quenching. So around 800 units you have this fluorescence, the height, and the first edition itself, it comes down below 600. Okay, I'll not go into the details of all this thing, but same thing, one question we asked, if the fluorescence can be quenched, what happens if we take out the iron? So this is what we have shown here, and there is in the presence of phosphate, when we add to this phosphate, we get back this fluorescence of this polymer. And this again, you can see the molecular wire effect here. Okay, it's completely quenched. The first addition of the phosphate, you see a big jump or enhancement in the fluorescence. This is one area where Professor Manoj Kumar also has contributed immensely the detection of various kinds of phosphate, and this is some of our contribution where we can detect not just this simple phosphate, inorganic phosphate, but we have taken it to the enzymatic catalysis also. I will not be discussing this about the phosphate part, but I will take this part, the detection of the iron, to the biological work. So we ask this question, if this polymer is so sensitive to detect this iron or the inorganic iron salt, can it also be used to detect iron that's present in various kinds of proteins? Okay, so we have tried out 4 different kinds of proteins or metalloproteins, where iron is deeply buried inside the organic part or in the protein part of the metalloproteins. And what we realized is various kinds of metalloproteins that are there, the cytochrome C, the methemoglobin, or the hemine part which we take out from this metalloproteins, and even this ferritin molecule which has both iron 2 and iron 3. In all the cases we see that when we add this metalloproteins or this hemine part to this polymer, there is a big change in the fluorescence, and you can see from this figure all the 4 metalloproteins, they are able to quench this fluorescence. And what is the significance of detecting these metals or metalloproteins to real biological work? And this is where their application comes directly. A lot of neurodegenerative disorders where you have these proteins which are part of these aggregated peptides, or they themselves can be aggregated, and if we are able to bind this metal and separate them from this aggregated part, definitely we'll be able to influence or control several neurodegenerative disorders. So with this in mind, what we did is, we again took this polymer, and this is how this, APP looks like, the amyloid precursor proteins. And when it interacts with this, you lose the fluorescence. You are able to bind this. You take out the metal or the metal protein part, and you are able to disintegrate or separate out this peptide. And hopefully, if you can remove it from the brain, then we can stop the progression of various diseases. These are some of the indications of this, the presence of metal in these aggregated peptides. You can also do the analysis by the CD spectra. I will not again go into the details of this due to lack of time, but there are a lot of different techniques now, various microscopic techniques, as I told in the beginning, where we are able to utilize them for the detection of these aggregated peptides or these neurodegenerative disorders, especially this Alzheimer's disease. So you all are aware that this disease is now quite severe in the Western countries, but the average age of the human in Indian subcontinent or the Asian subcontinent is also rising, and we are seeing the onset, or we are seeing these Alzheimer's cases rising in our country, and over the next 1 to 2 decades, probably we are going to see a more increase of this. So this is one of the reasons that the disease, although it's considered to be still a Western disease, not very common in India, has to be addressed at a very early stage. And if we are able to even predict that a person, he or she, is likely to have this with the advanced detection methods that we have, definitely we will be able to do to at least stop the progression. And with the techniques that we are having today at hand, definitely that is possible in India at a very, very early age. And as you all are aware, I said there is no cure that is available for Alzheimer's disease, and the best way to stop it is to stop its progression, rather than once a person is affected completely by Alzheimer's, to reverse it. So that seems to be impossible at the present stage. I move forward. This is the same figure as I showed here. So our scheme was you have the amyloid precursor protein, which may have the aggregated peptides and iron or any other metals that are present here. You interact with the polymer. If you can separate, you bind with this polymer, you can see without an additional dye that is changing the fluorescence. And if you can separate it out and restore this, at least partially this precursor protein, I think it will be a great contribution, or it will be helpful in stopping the progression. Traditionally, there are 2 dyes which are used commercially to see the presence of this aggregation in the peptides. One is the Kumar and the thioflavin T. And whenever you add this thioflavin T to the aggregated peptide, the commercial aggregated peptide, or the cerebrospinal fluid, which is the biomarker of the aggregated peptides, and when you add this thioflavin T with the increased aggregation, you see an enhancement in the fluorescence. Okay, so we are very fortunate to work with one of the hospitals in Guwahati Neurological Research Center, and for the last decade we have been getting samples from them. And what we did was, we took the samples, and when we added this dye to it, we saw that there is some aggregation in it. Surprisingly, when we added this to our polymer, we also realized that there is a small amount of iron that is present. You can see that there is not a complete quenching, but very small amount of iron that is present. Okay, and this can also be seen in with the help of concurrent. Whenever you have this aggregated or the A beta fibrils, there is a small shift, red shift in this absorption of the dye. Okay, and when we add our polymer to this dye, you can see that it's coming back, which is a clear indication that there is a breakage of this aggregation in the presence of this polymer. Okay, so we have studied this more in detail, and rather than only the fluorescence and the absorption spectra, we have also done the microscopic study, the polarizable optical microscope, and you can clearly see this a lump that was present in the cerebrospinal fluid, several of them, and the color that you see in the presence of the component, the golden color, and the crimson apple color, the greenish color that you see is the crimson apple color, where you have these very nice apples which are presently imported to India, the greenish color. So this is an indication that there is an aggregation of this peptide, and the component gives a very nice indication in the presence of the aggregation. Now what happens, when we add our polymer, the fluorescent polymer to this, can it take out this metal and can it break this? That was a big challenge, and this is what we did when we add. This is the image I showed 2 slides before this slide. When we add our polymer to this mixture of the aggregated peptide and component, you see there is the restoration of the absorption peak that was there previously. And the same thing happens here. When we add that, this is a combination of close to 180 images. When we add few drops of that over time, what happens that this aggregation, the lump that is there, completely diminishes or it's completely dissolved, and nothing remains. We keep it for a few days, and it doesn't come back and aggregate again. Okay, so it's a very major supramolecular interaction that happens in the brain, or the aggregation that happens in the brain, and reversing this, breaking this, and taking this aggregated peptide out of this brain. It is a challenge. It remains a challenge, and there are a lot of groups across the world which are working to solve this issue. This is a small video of how this happens. Sorry, some of this video is not playing. I move on. So we move on from the simple detection of iron to the detection of copper now. In this case, we have moved on just for the simple breakage of this. In this case, what we have shown is that you have this aggregated peptide, and they interact with various forms of this monomers and oligomers and the toxic fibril stage. And in addition to the simple breaking of this, we also show that whenever there is a metal, there is also a Ross generation. That is where this removal of these metals is very, very important. So what we do is not just show it in the aggregated peptide. In this case, we have also used an animal model. In this case, a wild type mouse. And what we do is we inject this from the tail vein and see what happens to this polymer. But in this case, what happens? We don't use a simple polymer. We convert that into a nanoparticle, and we change the functional group. As I mentioned, this is a neutral polymer here, and these nanoparticles are able to go up to the brains. Definitely in the pathway they also affect, or they also interact with various organs. This is a very important thing. And in addition to the removal of the aggregated peptides, removal of these metals, they also prevent the mitochondrial damage. So this is another study. This itself is a very, very big study, and we have got some very interesting results with this system. And this is the system, and the main the similarity that you see with this motif is that of the thiophylum T. Though there is a sulfur here, we have used two nitrogen atoms here. And surprisingly, what we found is that it looks very similar to this molecule. It found very efficient supramolecular assembly, and we can make a very small system. We call them nanodots of a very small size, and they are able to cross the blood-brain barrier, which is against the Lipinski rule. Again, this molecule, the size is very, very high, and to make it cross the blood-brain barrier, the size is also very, very important. That is where the advent of this nanotechnology is playing a major role. We also found that this polymer is quite selective to one of the aggregated peptide segment, the A-beta 16 to 21, which is very, very surprising. We really are not sure why it is very, very specific to only this segment. There are a lot of other segments also, but it has very strong binding to this specific segment. And that is what we use these as various biological studies. And one of the important aspect of this polymer is as such it bluish in color, but when we start aggregating this polymer, it forms a red and green color, and which can be seen very, very clearly in this confocal microscope. And whenever it interacts with the aggregated peptide, you see this happens over time. We can it loses its color. There are a lot of other studies. Its interaction with various kinds of aggregated peptide, the toxicity and all. I'll be showing you what happens when we inject the tail vein. So what happens is once we do this study, after the 72 hours, we sacrifice the mice, the wild type mice, and we harvest the organs, the brain, the heart, the kidneys, the liver, the spleen, and even the blood. So all these parts are taken, and what we see is this is about the brain segment, and you can see that the polymer is able to cross the blood-brain barrier, and we are able to stay in the brain, which is an indication this polymer, it definitely reaches the brain, and which is also an indication that it can act upon the aggregated peptide that is there. Okay, so this is a very nice indication that this polymer is able to do so, this multiple activity. It can not only interact with this the copper metal and also take it to the brain, or remove it from the brain, but also act with the aggregated peptide. So we have a lot of control experiments, and we are seeing if this amount that reaches the brain is even higher by increasing the time and changing various other parameters. But this definitely is a very good indication that it reaches the brain. So what exactly is happening in this case? These are the control experiment. You don't have much interaction here. With the A-beta treated, you see that there is a breakage here. And after a few hours or a few days, we can see that there is a breakage of this aggregated peptide, and we are able to further see that it doesn't progress further, even if you keep it for a few days and a few weeks. And most important aspect about this is it's not really following the Lipinski rule and going beyond the Lipinski rule, and that's an importance of any organic molecule, not just the polymer. That if you are able to convert them into an appropriate size and shape of this nanoparticle or the nanodots, you can make sure that it reaches the brain or any other organs which are otherwise not very easy to reach by normal ways. I move forward, we have also made similar molecules, again, the functionalization approach. So this hydroxyquinoline has been used very widely in the form of various drugs in a lot of different diseases. This polymer we have used not only for the aggregated peptide treatment, but also for the cancer theranostic. Professor came in the previous talk, has shown very beautiful results on developing a lot of different kinds of molecules for treatment of the cancer or the stem cells. In this case, what we have shown, we not only use it for this aggregated peptide, but we can also form aggregates with this doxorubicin, a very well-known cancer molecule, to again deliver it to the cancer cells. And again, we have shown here again the molecule, the imaging ability that I mentioned, the green and the red color of this system, which helps it to not only take it to the desired location of the disease, but also image it. And here you can see, this is the tumor regression studies in this animal model that we studied. These are untreated tumors, and this is only of the polymer, the doxorubicin. And when we have the assembly of this polymer, the doxorubicin, you see that the cancer regression is even higher with time. So basically, this polymer system are really very simple to develop. You can make, you can use them directly as imaging agents or for drug delivery, but you can also use it not only for doxorubicin as an example, but any other drugs also. Very nice assembly, and take it to the desired site. There are other applications again, that are used for by conjugated polymers. In this case, this is another area where Professor Manoj Kumar has been working and has contributed a lot. The development of aggregation-induced emission molecules, an area which has seen a huge, explosion, in fact, in the last 2 decades. So this can also be, taken to the conjugated polymer system. This is a TP molecule, the tetraphenyl system. We make it as a copolymer in this system. We add this part to keep the color from blue to yellow to orange. Okay, we have also introduced this ionic group here, so that there is an interaction with the ionic part of the human body or the skin, and you have the neutral part interacts with the oils that are there on the skin. So it's a multiple molecule. You can see every segment has a role to play. We have very beautiful fluorescence, but there is a challenge in this system. We have developed an AI system which is now exactly opposite to what is reported in literature. Usually you have a neutral molecule, and you add a few amounts of organic solvent. When you add an anti-solvent like water, you see an enhancement in the fluorescence. Whereas in this case, it's the other way around. You have this is soluble in water, and when we add THF to this, you see there's an enhancement in fluorescent. And one very nice thing is that the enhancement in fluorescence is seen from a very early stage, and almost from around 20% in its highly fluorescent, it remains destroyed. This is a very unique system, and we utilize this for staining the fingerprint. I'm not going to this slide. Directly I'll show you the result. So irrespective of the surface, irrespective of the fingerprints that are available on any surface, the aluminum foil or the glass slide adhesive tape or the coins, you can develop this very, very nicely. And since the quantity of this conjugated polymer that you use is so less, you can see that the black part that you see is a part where usually the raised fingerprint that are there, it doesn't contact the surface. Okay, and moreover, you can also see that this one fingerprint and the circles that you see, we have enlarged this image. And if there are some islands or if there are bifurcations, and if there are regenerating spores or even pores, the sweat pores that are present, everything can be visualized very easily. And as I mentioned in the starting of my lecture, that if you want to compare this with any suspect criminal or anybody, it is necessary that you have proper image processing software. Okay, so that is where the AI comes in. You have multiple suspects, and now you have everything is connected across the country. If you want to do this matching, you need the high quality images and processing of these images, which usually is not available in the synthetic labs. That's where the role of image processing and the AI comes in, and you can use this image directly now to do the matching studies, and probably you can have very good accurate results on fingerprint matching. I will not go into the details of both these images, but even in the presence of blood stain in this forensic side, you can still develop these images. And we also have tried to destroy this image, which is very common. Still, you are able to develop partially this image, and get a decent latent fingerprint image. I move forward to other applications. This is where again Professor Manoj Kumar has contributed a lot to detection of various nerve gas agents and other explosives. Okay, so we have used both small molecules based systems where you have paper strips to detect this nerve gas agent, especially the DCP, the ethyl chlorophosphate. And as we move forward, from the fluorescence images, we have also been developing a lot of devices. Two-terminal devices. Here again is a conjugated polymer. You make a film of that, and we have the vapors of this. When we inject this in the polymer, you can get this very nice device. Somehow I don't know the movies are not playing today. So here we have shown that we are able to detect this the fumes of these nerve gas agents for detecting this on a portable platform. So you injected this, and then you get a light out here and also a sound buzzer. Oh yeah, so this movie is working now. So this is how you have a small device, portable device where you can inject this. So you have the vapors that you can draw from this vial. It's not the liquid. You insert into this, and hopefully you'll also be able to hear the sound. So you have the LED that is light and also the sound. So these are the portable devices that we have developed at our lab for detection of these nerve gas agents. I move forward. I will just try to wind up quickly. So from the two-terminal device, we have also been making this three-terminal device or the transistors in our lab, which we have now extended to detect various kinds of bacteria. We can not only detect bacteria, but we can also distinguish between the gram-positive and the gram-negative bacteria. We can make this device even on a plastic or the flexible substrate, and we have also now transferred this technology to an industry, the RR Animal Healthcare, and we have now with us some of the prototype devices, which probably are undergoing certain kind of tests, and you can see this is a transistor device. This is how it goes into this. You have you can inject your sample from here, and if it's a gram-positive or gram-negative, or if there is bacteria, we can see from this the light that's on the green and the red light here. So we have moved on from the simple lab level development to prototype development, and hopefully we'll be able to see some interesting results with these systems. I don't know if I have time, but I'll just run through this. We also make a lot of photovoltaic devices, and not just with organic materials. So this is a very emerging area, and we have contributed a lot on this metal halide-based hybrid perovskite, as well as organic and polymer-based perovskite, in not only developing various kinds of materials, but also making various kinds of flexible devices and also these large area devices. I'll not go to the details of this, but definitely the role of various layers, the assembly of these organic layers, the hybrid layers, in this architecture is very, very important to make a working device and also improve the stability and the efficiency. So these have been our effort. These are a lot of different kinds of organic conjugated polymers, the donor and the acceptor systems, that are available commercially and also that we develop. We have been also working on developing this perovskite-based materials, and you replace any of the A, B, or X, and we improve the performance with this. This is the general slide where you have the APX3. You can replace this A with any of these cations. You can replace these metals, or you can replace the halides with a lot of other organic molecules. These are the multiple systems that we work on and get decent efficiencies. One example I'll be sharing with you all is about, again, using the conjugated polymer here. We use this MAPPI3. It is spin coated over the device here, and again, it's an anionic system here. It can bind with the lead which is present here, and from a simple, the pristine device of 14%, we can improve the power conversion efficiencies of solar cell to more than 20%. So the ionic polymers, as I mentioned, they have application not just in these sensors, chemical and biological sensors, but they have a prominent role even in the devices. This is the first example of conjugated polymer, ionic polymer to be used in a perovskite based device. And what it does, it improves the stability, the photo stability. You can see that when you have it, it protects it from the UV light. It improves its thermal stability, and it also improves its ambient stability. Okay, so that's very, very important. We can also make large area device, and around 2.5 centimeters square, it can go up to 18%. And this is what happens when you have this polymer on the top. You can see this contact angle; it's very, very high. We have also done further improvements. We have used a smaller molecule, ionic molecule based on that system exactly. And it's not a simple system. We can make a 2D layer over the 3D layer. This is another very, very important development that is happening. This photovoltaics and other devices. The students who are working in this area, developing this 2D layer on this 3D graded structure is very, very important. You deposit this in a specific way, and what we do again is we are able to go from close to 20% to more than 21% of power conversion efficiency with this system. I'll not go into the details, but here again you can see the same effect. All the stability parameters improve, and you have this contact angle which goes to around 87.5 degrees. So we prevent the degradation of this system, and you see very high performances with this kind of materials. These are also got a lot of the media attention. I'll not go into the detail, but we were called by the Niti Aayog, and we are now formulating a policy for the country along with them of how this can replace the existing silicon-based technologies in the country. And towards the end of my talk, this was the contribution that we were in fact dragged into, or we are very fortunate now. I can say that in Northeast we did not have even the basic COVID kits at the beginning of this pandemic, and we were requested to develop the viral transport media, and along with the National Health Mission in Assam, we managed to develop all the 3 kits at IIT Guwahati, and we got the ICMR approval, and we manufactured these kits in our campus IIT Guwahati. So this is the contribution that a scientist can make, and I would say that if you all join hands together, work together with interdisciplinary areas, you are not limited to just one field, but definitely it can have impact to multiple areas. This was also appreciated by our Honorable Prime Minister in the Man Ki Baat program. It was a tweet, and also our Honorable Education Minister at that time and the Ministry of Education had tweeted these results, and we are very fortunate to be part of this development and contribute, even during this time of this pandemic, through our science and technology efforts with my colleagues at IIT Kumar. So with this, I'm going to summary, we have been developing this conjugated polymers definitely, but their applications are not limited to a certain area. There's immense potential to so many different areas, and hopefully, we are able to take it forward to healthcare applications and other wearable devices, which is probably in another decade you will see a major way coming into our daily lives. So with this, I'm really thankful to my research group, the funding agencies, and the departments where I'm affiliated. All these students have contributed immensely. Around 6 of them have graduated now since 2021, and a few of them have joined very recently. Hopefully, we'll be able to, I'll be able to share more of the research work in other meetings that I'll have with you. This is one of the photographs of our campus, but definitely, these are some of the photographs, and the birds have just left the campus. They come here in winter, and it's a beautiful campus. This is a Department of Chemistry. In another week, we are organizing another major conference, the CRSI. Many of you would be aware, and if you all are coming, I'll be happy to interact with you all at our campus. So with these few words, once again, I'm thankful to the organizers for inviting me. I once again wish Professor Manoj Kumar on his 60th birthday, and hopefully, I'll have more opportunities to meet him in person, interact with him, and of course, see the wonderful science that he's been doing. So thank you very much, and I'll be happy to answer any questions from you all. Thank you.
There can be one quick question.
So once again, I thank you, Professor, for your enlightening talk, and see you sometime again here. Thank you.
Yeah, sure.
Sure.
Yeah. Mr. Vijayanath, can you hear me? Yeah. Welcome to the symposium. Yeah. So we are at this moment moving to the offline mode. That is, one of the speakers here is going to deliver the lecture, Dr. Daisy Burkis. So we will like you should continue with us. Thank you, Dr. Nath. So the next speaker for today's symposium is Dr. Reji. He received his PhD with Professor Ajay Ghosh. He has spent a number of years for his postdoctoral positions at Montclair University. He was a Humboldt Fellow. And then he worked with the Hyang group at Arizona State University. His current research focuses on design of DNA nanostructures using the principles of supramolecular chemistry for biomedical and nanotechnology applications. Today he is going to talk on responsive DNA nanostructures for cancer therapy. So with these words, I invite Dr. Burkis for present talk.
Very good morning to everyone, and thank you very much, sir, for your nice words of introduction. And before I start my lecture officially, let me wish happy birthday to sir, and wish you all the very success coming in. I also take this opportunity to thank your chairman. He is also celebrating happy birthday today, so happy birthday to you also, both of you. And I take this opportunity to thank Professor Vandana Balla to bring me here. She is actually brought me here. And also I am so thankful to the department, particularly to Professor Vandana Balla for the excellent hospitality. I must say that it was excellent. And a couple of students were helping me and helping us. It was so nice. Thanks to all of you. We had a wonderful time yesterday. We went to Golden Temple, Wagah Border. It was so nice. First time in Amritsar. And I'm not talking too much about other things. Let me directly come to the topic of my research activities. So myself is coming from myself Thiruvananthapuram, which is the extreme south of India, and it is located in Trivandrum, Kerala. And the research activities we do at ISET Thiruvananthapuram is again related to supramolecular chemistry, but in a slightly different way, which we call it as DNA decorated soft nanostructures. Though my title was little different, which was given earlier, but I will just, do justice to the title if time permits. But I would like to discuss this aspect of the work. If time permits, I will go to the next one. So, coming into the introduction of these DNA nanostructures, for the last 2 decades, if you take, there is an area which is emerging in the literature, which is DNA nanotechnology. So, DNA nanotechnology basically, if you look into the definition, it is you do nanotechnology using DNA as the building block. That's it basically. And the area was actually pioneered by Professor Ned Seaman, who passed away a couple of months back. He's from New York University, United States, and he's the one actually discovered the idea where DNA can be used as a nanomaterial. It was absolutely unknown before his proposal. DNA was known to us, all of us, it is a genetic material, but nobody thought about the possibility that DNA can be a nanomaterial in making nanotechnology application. And he is the one actually brought that idea to the scientific community, and after that the area has emerged like anything. Now, what he proposed is that you all know that DNA has a very unique self-assembly behavior, is sequence-specific self-assembly or sequence-specific hybridization. So, by using the concept of sequence-specific hybridization, you can actually design a lot of DNA-based 2D as well as 3D nanostructures. That was his proposal. And later at the year of 2006, another interesting concept was introduced in this area, which is known as DNA origami. Origami is a Japanese word which you may be familiar, which is nothing but folding of a paper into a particular shape. So that is basically the meaning of origami. But this person from Rockwood, he is absolutely not a chemist, not a physicist, absolutely he is from a computer science engineer. What he did is that he was actually, it was absolutely a breakthrough result in 2006. What he was shown is that if you take a viral DNA, something about long, extremely long viral DNA, that can be folded into any shape or size by using sequence-specific DNA hybridization. And there is another area was introduced, which is nothing but DNA origami. You do what you do. Origami means folding of paper, but DNA origami, you fold the DNA to the shape what of you wanted. And these are the different kind of shape which was developed over the years by different researchers, 2D as well as 3D structures. So you can see that this DNA, the nanostructure is fully made of DNA by simply folding the DNA. But the problem here is that two things are very important here. If you are looking into all these structures are solely made of DNA. There is nothing else. These all are fully DNA-based structures. And second thing is that though this is easy, so what you see here in the structure, everything looks fine. It is not so easy to design this kind of principles. So you basically need a computational support to make this kind of design. So two things, in order to introduce a functionality or a functional domain to this structure is extremely difficult. And second thing is that this you always need a computational support in order to make this kind of structures. So these are the two important, though this nanotechnology offers a great kind of contribution, there are a couple of challenges or concerns that need to be addressed. So what are the challenges? As I told you, the challenges are the extremely complex design and also how to introduce another functional domain, such an organic domain or whatever it is. So that was our idea. So what we thought is that is there any other way one can actually make nanostructures of that kind, that means DNA-based nanostructures, with extremely, in a simple fashion. At the same time, that permits you to incorporate functional domain into the structure without much complicated synthesis or complicated computational programming. So so before going into that particular area, just for the benefit of the student, faculty members definitely I'm sure that aware of what I'm going to say about it. It's a class of small molecule. It is known as amphiphilic molecule. Definitely everybody knows that. So an amphiphile is actually having a hydrophilic unit and a hydrophobic unit. So in another words, a like and a dislike units are joined together in a covalent way or non-covalent way, it doesn't matter. So what you have is that in an amphiphile, a hydrophilic unit which is water loving and a hydrophobic unit water hating, you join them together. So you have two like dislike guys in the same entity. So if you take this amphiphilic system in water, what they do is that in order to this like and dislike behavior, the hydrophilic unit will expose to the water and the hydrophobic unit will bury it inside the nanostructure in such a way that there is only minimum or no interaction with the water. So that is the way it will self-assemble. This is a typical amphiphilic molecule. We all know that phospholipid, which is actually making a cell membrane. So this molecule wherein the phosphate is a hydrophilic unit and this is a hydrocarbon which is hydrophobic, and when self-assembled you will get a cell wall membrane wherein you can see that the phosphate part, which is hydrophilic, is exposed to water, and the hydrophobic part, which is actually buried inside with little or no contact with water. So that is a very basic idea. So what we do here is that if you look into the structure of the DNA, you can see that DNA is consist of adenine, thymine, cytosine and guanine. 4 bases are there. And we know that the pillar of DNA nanotechnology is the sequence specific hybridization. A will bind only to T and C will only bind to G. So that is the pillar of the area known as DNA nanotechnology. The full area DNA nanotechnology was based on this particular thing. Absolutely excellent idea, no doubt about it. But looking into the structure or the backbone of the DNA, what was not really explored is the phosphate backbone. Due to the presence of the phosphate group in the DNA backbone, make it hydrophilic in nature. So this is an anionic backbone, water loving, absolutely love to go to water. So that is the part we are trying to explore. So here you have the alphabets, 4 alphabets are there. In addition to that, you also have an amphiphilic nature associated with DNA. So what we, in order to design the amphiphilic system, we took the DNA as the hydrophilic material. So this is the design principle what we follow in our research laboratory. So you have a DNA is conjugated to a hydrophobic unit. So this particular one, blue in color, is a hydrophobic unit. Is conjugated to DNA which is hydrophilic in nature. So here by doing so you are getting lot of additional advantages. Not only it gives the hydrophilicity, in addition to that you have all the possibility of the alphabet base pairing is also available. How? So when you take this particular amphiphile, allow them to self-assemble in water, you can have different kind of nanostructures as you see in the DNA nanotechnology approach. You can definitely have any kind of nanostructures. That's what I am going to demonstrate in the coming slide. The beauty here is that you are doing the self-assembly in water. Because of the hydrophilic nature of the DNA, in all the nanostructures you can see that your red color is actually on the surface. Why the red color is always on the surface? Because you are having DNA on the structure and the DNA always wanted to expose to water because it is hydrophilic. So that is the structure. In all the structure, for example, you take a lamella or a tube or a vesicle or a micelle or whatever be the shape, doesn't matter. Always you have the hydrophobic domain buried inside with no interaction with the water. And you can see that the hydrophilic DNA is always exposed to the water. So here you are able to make a kind of structures which is decorated with the DNA. That's the reason I put the title as DNA decorated nanostructures. And your hydrophobic domain is having no interaction or minimum interaction with the water. So here you are able to propose a new methodology to make DNA nanostructures. But I must also admit at this point that you will not have that kind of diversity in kind of nanostructures compared to the DNA nanotechnology. That actually gives you all kind of nanostructures. Whatever you think, you can make it. But here there are some limited nanostructures only can be obtained. But the additional plus points are here. The design principle is very simple, and this is scalable to whatever amount you wanted. The other nanostructures which I am talking about, taking from DNA, scalability is it's absolutely an issue. So we are not the first one to introduce the concept of DNA amphiphile into the literature. So when we started the group at ICER about 10 years back, when we look into the literature, what was known in the literature at that time when we started this research work. So this kind of design was already there, and we had a very close look into that. So what we understood is that what was known in the literature, you have a single-stranded DNA attached to a polymeric material. Okay, so this is a polystyrene which was reported by Chad working in 2004, and there are a lot of examples in the literature. And when we study all the literature example, what we found is that one thing is very common. The common thing was that we have a single-stranded DNA which is attached to a flexible polymeric chain. So both these guys are flexible in nature. We always use single-stranded DNA, don't confuse it. So this is a flexible unit and the polymer is also flexible unit. In all the example, we could not find any example where anything else is used instead of the polymer. Whatever polymer you are taking, in all the cases it will be flexible. So two flexible units are joined together, and accordingly in all the cases only one nanostructure was observed, which was simple micelle. So no other nanostructures was reported in the literature when we started this workload. So what we could learn from the literature is that if you are taking a flexible DNA and a flexible polymer, it will always goes to this particular pathway, only one nanostructure, which is DNA myself. Absolutely no issue, and the design was perfect, and according to the design, DNA will be on the outer surface and your hydrophobic domain will be buried inside. So what we thought is that if you are introducing a rigid hydrophobe here, so here the hydrophobe was flexible in nature, and if you are replacing this hydrophobe with a rigid hydrophobe, you can actually tune the self-assembly, because when you are introducing a rigid hydrophobe, it will start to assemble in a lamellar fashion. That I will show you in a minute. So once you have a lamellar assembly, you will have more and more control in tuning the morphology. So that was our idea. And in 2014, we published our first paper in this particular area, that was DNA chromophore amplifier, which is titled, don't look into the title, it's not really important. So what we proposed is that what we synthesized, a series of DNA was synthesized here. Here you can see that the DNA is a very short DNA, which 10 base pair are there. And if you look into the structure, you have a rigid hydrophobic unit here, here, and here. This was synthesized to show that it is a general concept and other things. So here DNA is a hydrophilic unit, and you have a rigid hydrophobic part on here, here as well as there. And we studied the self-assembly. So though I showed that in one slide, my student, my very first student took almost 3 years to just make the molecule. So organic synthesis was a lot there, but I am not going into the details. And we studied the self-assembly behavior, and this is a self-assembly behavior of the molecule in water. And what we found is that from different microscopes, this is AFM and this is TEM, I will come to that. What we found is that there is a formation of vesicular nanostructure here. The vesicle is represented like this. The molecule undergo lamellar assembly. Your hydrophobic unit is buried inside, which is shown with the blue color here. And you have the DNA on the exterior as well as interior. And during that assembly, you can see that your hydrophobic unit, which is assembled in a lamellar fashion, is having no interaction with the water, absolutely a closed structure. The vesicular nature of the structure is further confirmed using transmission electron microscope, wherein you can clearly see the membrane. Membrane means this particular one is very clearly seen. So we concluded that this structure is a vesicular structure, and the structure is assembled via a lamellar packing. And we just extended that particular concept into a variety of hydrophobe which are rigid in nature. For example, porphyrin, harrowsine, many are there. I am not going into the detail. In all the cases, we could see that formation of vesicular nanostructures. So that is the story. So then now we know that, but we know that if we introduce a rigid one, you can actually have the lamellar assembly, right? That much we know that time. And what we thought is that if you are replacing the rigid hydrophobe with a little more bigger molecule. The bigger molecule meaning that this is having a large pi surface, right? This advantage of having large pi surface is that if you permit them to assemble in water, it has a very strong pi-pi stacking tendency. Because it doesn't want to go to water at all, so it will immediately self-assemble through pi-pi stacking interaction. So we thought that if you are introducing this particular one over there, this molecule will tend to aggregate in a lamellar fashion, but it will not undergo the folding. Instead, it will grow in a 2D manner, so that we can really make a 2D sheet. So that was our design. And this is a design what we have. This is in 2017 we published this particular result. And what we synthesized, again, I want to say that this molecule was synthesized, I think it is nearly 4 years, I guess. But studies were done in maybe in 1 month. But synthesis was the main guy here. The DNA synthesis and all those things are really complicated. Anyway, so we synthesized this particular molecule. Molecular graphene was conjugated to DNA in a multi-step organic synthesis. And due to the strong pi-pi stacking interaction of the HPC unit, you can see that this is the way it is assembling. That this is your molecular graphene buried here, and you have the DNA on the surface, either bottom as well as on the top, and it will self-assemble and it will result in the formation of the sheet. So the design principle lies on the principle that this due to the very strong pi-pi stacking interaction, it will not fold into the vesicular structure. So you are allowing them to, or the molecule has a strong tendency to assemble in a 2D fashion. That is because of the large pi surface. And we synthesized a series of molecules. I am just showing 2 representative examples here. And the molecule was fully characterized using HPLC and MALDI analysis. And we studied the aggregation behavior, and we can see that dynamic light scattering, there is an aggregate formation. It doesn't tell you more than that. And we also studied the SAX analysis, which was done in collaboration with Dr. Ashish. And what we could see that in solution it is forming sheet kind of structure. Then obviously we went to the microscopic analysis, and wherein you can clearly see the formation of micrometer size structures are found to be extremely strong. And we can see that even we could actually resort the molecular level packing of this amplifier using high resolution TEM image. And you can clearly see that lamellar assembly of the molecule and the dimension of the assembly was also elucidated from the HRTEM. And based on all these data, we proposed the molecular structure wherein you have a hexabenzopuronic which is assembled in a lamellar fashion with the DNA exposed sheet. Now the question you all are asking, what is the uniqueness of all this structure? I started by saying we know that you have DNA over here and DNA over there. Both are single stranded in nature. And we synthesized a gold nanoparticle, and the surface of the gold nanoparticle is also conjugated with the DNA, again single stranded. And this DNA on the surface of the nanoparticle is complementary to the DNA on the surface of the sheet. So if you do a self-assembly between these two guys, what will happen? Definitely due to the sequence specific hybridization, the nanoparticle will go and sit on the top of the sheet as well as on the bottom. So that is what it is. So this is a zoom out transmission electron microscope wherein you can see that many sheets are decorated with the sheet. A nanoparticle. Let us see what exactly, if you are looking at a zoom in image, wherein you can clearly see that there is a layer of nanoparticle on the top, and you can also see that there is a layer of nanoparticle on the bottom. If you look into this particular nanoparticle versus this particular one, you can see that a layer of particles are having high contrast, and there is another layer of particle which is having less, whereas the particle on the bottom will give you less contrast. That's the reason you see a different contrast here. And again, the beauty of DNA-based systems are you have more and more control on the nanostructures. So in order to prove that, what we have done is that we have synthesized another set of nanoparticles, again conjugated with the DNA in a covalent fashion. The idea was that if you are introducing a DNA which is non-complementary to the DNA on the sheet, you don't expect any self-assembly, right? Because there is no sequence-specific hybridization possible. So that is what is exactly we see. If you take a nanoparticle where the DNA is not complementary, you can see that the sheet is very clearly seen there. There is no assembly as in the previous example, but it is randomly dispersed over on the top. So here this amphiphilosity driven self-assembly, the design principle is very simple. Now we use this particular one, it will self-assemble to the 2D sheet, absolutely fine. So the next idea was that if you are disconnecting this bond, this bond, this bond, this bond, this bond, and that bond. So what do you basically get? You get another class of molecule which is known as hexaphenylbenzene, which I am very sure that Professor and Professor Manoj Kumar are working on that one, and a wonderful review was written by them, and absolutely great review. And if you get this particular molecule, what is the advantage? And as an MSc student, you should know that all these molecules or this class of molecules are known to exhibit heteroisomerism, right? Heteroisomerism is nothing but you will be having a orthogonal arrangement or nearly orthogonal arrangement between the central benzene ring and the benzene ring on the periphery. So the advantage of or the uniqueness is that this molecule can either adopt a clockwise direction or an anti-clockwise twist for the periphery. So this benzene ring can have either a clockwise twist or it can have an anti-clockwise twist. And if you look into the literature, since we know that if you are introducing a chiral center into the molecule, what will happen? One of these particular one can be biased. You can either have a clockwise one or you can have an anti-clockwise one with the introduction of a chiral molecule. So our idea was that if you are introducing a DNA which has multiple chiral center into this molecule, so the advantage is that this molecule is individually can have either of them, but the moment you introduce a chiral entity like a DNA, it can bias one of these conformation. Okay, so if the molecule does that, what will happen is that can induce a twist into the molecular system. When we are talking about a single molecule, when you have an assembly of the molecule, it will induce a twist into the sheet. And in addition to that, when you are making a twisted structure, the self-assembly will become little weaker, not that strong like that. There is a chance that it will not grow to that extent of the sheet. Instead, it will induce a twist and the assembly will become weaker. And this is aggregation studies in the solution state, where you can see that there is some kind of aggregates are formed which are chiral in nature. That is very obvious from solution state studies. And this is the typical fluorescent behavior of this molecule. In the aggregated state it is fluorescent, but when you are increasing the temperature, you can see that there is a decrease in fluorescence because it is becoming more and more monomeric in nature. And we did microscopic analysis and this is the transmission electron microscopic analysis of that particular aggregate which were chiral in solution, and it will be biased only to one direction. As of now, to best of my knowledge, I'm not sure whether it will be possible to predict that this will be to the right handed or to the left handed. You can see many examples give you conflicting results. But at least we can say that there is bias only to one direction. So we don't see any P helix from our microscopic analysis. All the helix were M helix in nature. And you can see that it is thoroughly characterized using all possible microscopic techniques. All nanoparticle, again as in the previous case, with the DNA on the surface, which is complementary to the DNA on the surface of the ribbon, and we do self-assembly. And what we expect the chiral assembly of the nanoparticle should assemble along the chiral template because of the sequence-specific hybridization. In order to prove the concept in a more general fashion, we also synthesized a gold nanorod, which was also synthesized, functionalized with the DNA. Again, this DNA is complementary to the DNA on the surface of the helical ribbon. And in this case, if our strategy, design or the structure, whatever we are proposing is correct, we should get this chiral assembly of the nanoparticle as well as the nanoroad. So that was the thing. And we see DNA, and these two guys are complementary to each other. And this is the transmission electron microscopic image after the assembly with the DNA. You can see that very nicely the nanoparticles are arranged in a helical fashion along the template. And this we have done with the different kinds of nanoparticles in order to just to demonstrate that this is not by coincidence we get these particular structures. So we synthesized gold nanoparticle 10 nanometer in size and 30 nanometer in size, and we can see that a very clear helical assembly of the nanoparticle along the template. And accordingly, if these nanoparticles are arranged in a helical fashion, obviously it should be CD active. And here you can see that there is an emergence of the CD signal in the plasmon absorption region of the nanoparticle because of the chiral assembly. And as you know, DNA hybridization is absolutely temperature dependent, right? If you rise the temperature, DNA will melt, and you can see that when you are increasing the temperature from 20 degrees Celsius to 60 degrees Celsius, melting of the DNA, the nanoparticle will move away from the template, and you can see that the CD signal will completely disappear. So it is clearly indicating that this chiral assembly is indeed due to the hybridization, sequence-specific hybridization, and which is temporary. We also continued with the nanoroad as well, and not just restricted to nanoparticle. And if we did this, we will not be able to say exactly it is in a helical fashion. But the image says that there is some kind of helical assembly. But online, you can see that here it is obvious that we don't have any kind of helical assembly. But we can only say that these nanorods are aligned or arranged along the template. So, though we don't have a clear-cut mechanism why we don't helicity, the only thing we can say is the helical assembly of the template. So that is the thing. And in addition to that, we do see the emergence of the CD signal in the plasmon absorption region of the nanoroad. So it is not fully correct to say that the template is fully flattened. There is some kind of chirality still exists, but it is little bit flattened. That is the kind of thing we are having. And this is a summary of my talk, and we have summarized all these results in the FOB2B accounts. And what we proposed is that we proposed a new class of amphiphilic system where you have single-stranded DNA which is acting as a hydrophilic nature, and you have a rigid pi conjugated system. That is our concept. So when you have a rigid pi conjugated system, it will permit the lamellar assembly like that. Once you have the lamellar assembly, you can have control the nanostructure formation by simply controlling the lamellar hydrophobic unit. So it is this particular unit which dictates what type of nanostructures you get. If you are taking a paraphenylene kind of molecule, you will be able to create a vesicular nanostructures. And if you are taking a hexabenzocoronium which is having a large pi surface wherein a strong pi stacking is possible, leads to nanosheet. If you are taking a molecular system, something like that, which can show twisted geometry like or an acropisomalism, where you can induce this into these nanostructures, thereby you can actually create helical nanostructures. So it is basically we don't, and from our research we learned that the hydrophilic DNA has very little role for this cell assembly. The hydrophobic unit is the guy who actually dictate all these things. I think I'm done. My time is over. We also do this particular one where this is what I have given the title, but I'm sorry about that. Yeah. So these are the directors for their general support, and we have been heavily funded by DBT and of course DSP and the Kerala State Council. This is a funding agency in Kerala, and of course ISAP program. And I thank you all for your attention. So if you are looking into these structures, they are hollow in nature. But the problem is that if you are looking into the air from height, you don't see that the diameter. If it is really hollow like a ball, the diameter as well as the height should be matching. But we don't.
Can you use this as a drug therapy?
Yeah, definitely. We have done. I did not present that data. We have demonstrated that this can be used for delivering both hydrophobic as well as hydrophilic drugs. Because this membrane is hydrophobic, so you can load hydrophobic drug there, but the interior is hydrophilic. So
and in most of the cases, your DNA single stranded remains the same. You have the same DNA in all the assembly, but just changing the chromosome.
Yeah, in all the cases that's what I said. In all these cases, we have only changed the hydrophobic part, but we have also studied that the hydrophilic DNA has basically no really any role in detecting this assembly. Meaning, we have taken 10 mer, 20 mer, and up to 30 mer, different 30 base long DNA. But we don't see any change in the self-assembly pathway. So we concluded that the DNA has little role in dictating, but we don't know if you are taking a 100 base pair long DNA, probably the story will be different.
Maybe some change the base pair.
Yeah, exactly. That part we don't know. But from our own studies, what we know is that the hydrophobic part is the key in dictating all the assembly. Hydrophilic DNA has little influence.
So now we are thinking some other turboprops instead of HBC or.
Yeah, the only problem is that the synthesis.
I think purification will be enough.
Purification is also a terrible. I mean this.
HBC.
Yeah, HBC. This.
Yeah.
Right.
And
Yeah.
getting the characterization is also very difficult.
Characterization we normally do HPLC and MALDI, nothing else. No NMR. No. That is acceptable. I mean, it's absolutely fine in the community. They don't ask for NMR data because we cannot have NMR.
Is it why is that you are getting this kind of survey that the core is hydrophobic and surface is hydrophilic? Now, if you change the solvent, let's say while getting these micelles, you take some non-polar solvent.
Yeah.
Possible that you get the reverse micelle or.
Definitely. So we have done that experiment also. If you permit them to self-assemble in a non-polar solvent, say for example. So most likely we expect that this non-polar unit will be exposed to the outer one and the DNA will be in the inside. But what we found is that we tried that experiment and in all the cases we simply see the precipitation of the DNA. So we did not do. All our experiments were done in aqueous medium, water. Inverse micelles are also possible, but in our case we always see precipitation.
So that means that molecule cleaves in that.
No, not clean. It's because of the very poor solubility, it will precipitate out from the whole. That's it.
To have a cup of tea for just 10 minutes and then come back again for the next technical session. Thank you very much.
यार थोड़ा करना है
सेंड कर लेगा मैं साइड एंगल तो करना
पर कि टाइम से एक दो सेकंड होने बढ़िया जा रहा हूँ ਹੀ ਚੱਲਣਾ।
the image there. After intersystem crossing, there are two types of photosensitizers. Mostly type 2 process, so molecular oxygen can be converted to a single oxygen. And probably more recently, some organic molecules can act as a type 1 photosensitizer, which can generate radical species. And for the PDT, it has a long history, as you know. So I will start with our contribution a few years ago. So Xingshu Li did a key role in this project. So we synthesized phthalocyanine derivative, which has a biotin at the end. So this single molecule can make a nice nanoparticle. In this stage, fluorescence and ROS generation is off. And when it meets proteins such as amidin, then partial deassembly occurs, so we can see the fluorescence, and also ROS generation is on. Still, it is somewhat aggregated form, or we can see the PTT effect, and also we can do the photoacoustic image. So we call this one as a 1-for-all nanomaterial. As you can see, there was a selectivity for the amidin among other various proteins. And when amidin was added, you can see the fluorescence enhancement of the Prof, the amide. And this is the TN nanoparticle image. And again, when amidin was added, you can clearly see the partial deassembly of this nanoparticle. So, based on EPR effect, we can see that tumor delivery of this nanoparticle to the tumor. And this A549 is biotin receptor positive cancer cell. So you can see clearly the difference between the biotin receptor negative cells and biotin receptor positive cells for this nanoparticle. And also for the A549 xenograft mice, so we can see the tumor growth inhibition with this nano-PCTB with the laser irradiation in this case. And next example is another nanoparticle, but in this case we used a partner for the phthalocyanine derivative. So we used MA, which is a well-known anti-cancer drug. So these two components can make a fairly stable nanoparticle. And when it meets nucleic acid or DNA, again, that partial deassembly occurs. So we can see the PDT on and also PTT. And since we used MA, we can see the CHT synergetic effect too in this case. So the size of this nanoparticle was about 100 nanometer, and we can see almost complete fluorescence quenching in this case. And also singlet oxygen generation is almost completely quenched. We can see moderate temperature effect, and when you add nucleic acid, we can see the fluorescence enhancement, and also ROS generation case. Since we used MA as a partner for the phthalocyanine, we observed fairly nice tumor inhibition effect in this case. So when PCS-MA was introduced by IV injection, and when laser was used, then it can make complex with the albumin in situ and can be delivered to the tumor. It showed a nice anti-tumor effect in this case. This is TN image of this nanoparticle. In PBS solution, it shows about 15 nanometer size of nanoparticle in this case. And photostability of this nanoparticle was quite good compared to the indocyanine green and the PCSA, which contains 8 circulate groups. So And when we add BSA to this nanoparticle, we can see the fluorescence enhancement and also ROS generation. And in addition, we observed the size of this nanoparticle is reduced to about 6 nanometer, which corresponds to the size of the algorithm. And Professor Sun Choi's group did a theoretical calculation of this complex, and we can see the flat phthalocyanine zinc being nicely fit into the pocket with the zinc atom, and the oxygen atom of the Y161 residue is coordinating, and also a circulating group of this phthalocyanine forms cyanidic interaction with the K519 in this case. And Professor Nam, P-Tech Nam at Yonsei University, our collaborator, made genetically engineered mice. So of this wide label of fluorescence too. So from this experiment, we can see directly that our phthalocyanine is complexed into this YFP labeled albumin and can be delivered to the tumor in this case. So there are quite a number of cases that albumin was used as a carrier of the drugs or photosensitizers, but this might be the first example of direct evidence of albumin in situ complex to the tumor. Next topic is about heavy atom-free photosensitizers. As you know, that heavy atom was incorporated into the photosensitizers to enhance intersystem crossing, but it can liberate dark toxicity and poor photo stability and potentially high cost of the heavy metals. To address these drawbacks, many groups nowadays try to synthesize or design these heavy atom-free photosensitizers. There are several approaches to make this heavy atom-free photosensitizers. One is using traditional tetrahedral structures, or spin orbital charge transfer into system crossing, or reduced singular triplet energy gap, or thionation of carbonyl group, twisted pi conjugation system, or radically enhanced into system crossing. One of our approach is thionation of carbonyl group in conventional group. So the replacement of oxygen with the sulfur simply to obtain this thiocarbonyl-based photosensitizers. Sulfur atom may be considered as a heavy atom due to the strong spin-orbital coupling effect than that of oxygen. So for this study, we simply introduced this convert carbonyl group to the thio group in this case, and also in addition we introduced a very strong electron donating. This mentions probably through the type 1 mechanism in this case. So we synthesized this naphthalene derivative. For this one, we can push the fluorescence emission to the longer wavelengths. And for the many S, as you can see here, fluorescence is almost completely quenched. So we found out this strong electron donating group at the full position of naphthalene, and also this conversion of oxygen to the sulfur, leading to the nearly unit single oxygen quantum in this case. So spin orbital coupling constant is significantly increased, and single triplet energy gap decreased by on replacing this oxygen by sulfur. So In addition, as I told you, this NES works very well in the, not only the normal shell conditions, but also in the hypoxic conditions. So even very low concentration, it shows very effective photosensitizers. We synthesize series of ODP derivative in this case. So either beta or meso position EDP5 was most effective, which contains the highly twisted structure and the smallest single oxygen, single triplet energy gap in this case. And also it shows aggregation induced far red, almost near infrared emission. And also it can generate fluorescence emission to the longer wavelengths. And finally, this one shows a nice effect to generate ROS, not only to show that near infrared fluorescence emission too. Since this far red TICT emission of EDP5 was greatly enhanced by the restriction of internal rotation in the aggregates, so we can make this nanoparticle using chloronic F127 nanoparticle. So this nanoparticle was actually used for the mouse models to check the anti-tumor effect and also deliver to the tumor selectively. Next topic is about antibacterial work. So as you can read here, gram-positive and gram-negative bacteria, the membrane is different. So of course the latter is more complicated than the former. And so PS penetrate gram-negative bacteria more difficulty than gram-positive bacteria. And single oxygen can directly destroy actually bacteria by damaging the membrane or inner biological molecules because of the high reactivity of single oxygen. However, superoxide radical anion has a moderate reactivity, and it has a difficulty actually directly destroying the bacteria out of membrane. PDT can kill both gram-positive and gram-negative. On the other hand, the superoxide radical generated PDT can kill the gram-positive. So we use this quite famous MBS moiety, which was deposited by Siajun Pang's lab in JAX, Dalian University of Technology, and we introduced this multi-positive charges. So we synthesized NBSN and NBSCN. So NBSN mainly produced this superoxide radical. On the other hand, the NBSCN, selenium derivative, can generate single oxygen, so which can work both positive and negative, from positive and negative. So indeed, as you can see in this slide, you can see the effect of both gram-positive and gram-negative in this case. So this is also the data for this same result. So we used the first probe for the single oxygen and also superoxide radical. So you can see this difference between NBS SN and NBSCN in this case. So in overall, we can selectively design this two different photosensitizers, and we can selectively kill the gram-positive bacteria using this type 1 type photosensitizer. And this is the picture of the sRNAs infected wounds on the mice. So you can see after treatment of this NBSN and with the light, you can clearly see that the wound is mostly recovered in this case. And next couple of examples is about fluorescence probes. Our group worked with fluorescence probes for many years, and some of them are based on this reversible approach of the molecular recognition type, and recently most of them are based on this reaction-based fluorescence probes. So which is irreversible, but still, as you know, the selectivity and sensitivity is usually better than the reversible type. And the target is enzyme in this case. So as you know, most disease biomarkers, enzyme play fundamental and extremely critical role in biosystems. So the first example was done by Idol Lee, who joined Dalian University of Technology last year, as a faculty member. And he synthesized this relatively simple AI moiety, which contains this phosphate group. And this probe contains hydrophobic aniline QM derivative as AI core, and also hydrophilic phosphate groups as ALP recognition unit. So this alkaline phosphate phosphatase is recognized. And this difference is this amphiphilic AI derivative can make a loosely self-assembly structure, which is still fluorescence is severely quantic in vitro. So this makes this can solve one problem of the most AI, which is always on problem. So after ALP cleaves this phosphate groups, then one can see AI inhibition in this case. So this is nanostructure, and also selectivity for the selectivity for the ALP, and you can see the fluorescence enhancement. And this is collaboration work with Seattle Pong's lab, and you can clearly see this HG2 tumor is fluorescent because of this DQM ALP. During the process of this surgery, you can see clearly that fluorescence, strong fluorescence, and this can be removed. And even about 1 millimeter small cancers can be detected and can be removed during this surgery by using this DQM ALP in this case. And next example is also about enzyme for CE. This was first also is the Xiaopeng in this case. As you know, this ester moiety was heavily used for this CE activity, as well as this BCHE or acetylcholine ester. And there is mutual interference in this case. And in addition, this CPT11 is a precursor of anti-cancer drug, which contains this carbamate unit. and can be catalyzed by CE to release this anti-cancer SL38. So based on this findings, we synthesized and we decided to use this carbamate unit. And we first introduced this one as the receptor lupin derivative. And found out this carbamate unit showed high selectivity towards this HCC-related biomarker of CE. And these compounds, after reaction with the CE, then cleavage, followed by 1,6 rearrangement, elimination, to offer this pre-resolute. So based on this finding, we decided to apply this carbamate to another AIE moiety, DC and CE. This CL position was a little bit critical, and we, of course, synthesized other chloride derivative too, but found out this was the best. And we observed a nice selectivity for the CE, especially compared to those two competitors of the enzymes, and also a nice fluorescence enhancement in the red region or about NIR region. And this is a mouse past experiment. So this is the orthotopic liver cancer mouse model treated with this anti-liver cancer drug. So you can follow this effectiveness of the cancer drug using our Prof in this case. So you can see the three-dimensional fluorescence molecular tomography in this case. So you can see this probe is very effective to actually check the CE activity, and so eventually you can see this liver cancer progress of this anti-cancer drug in this case. Okay, so this was recent progress of our fluorescence probe and activatable photosensitizers. Again, thank you so much for kind invitation. Also, congratulations on your 60th birthday, Manoj. Thank you.
Let us thank again Professor. So next speaker is Dr. Sanchita Singh Gupta from ISM College. Dr. Sanchita is assistant professor in the Department of Chemical Sciences at ISM College. Her research interest includes the development of donor acceptable molecular systems for their possible applications in optoelectronic devices. And today she will speak on the multi-stimulate programmable FET light harvesting antenna towards ratio liquid temperature, pH and multiple metal ion sensing. So with this I invite Dr. Singh Gupta to present.
So I would like to congratulate Professor Manoj Kumar on his birthday and wish him good health, and I hope that I can meet him sometime in person soon. So in today's presentation, I will be talking about stimuli responsive materials, and when we talk about stimuli responsive materials, there are several mechanisms which can lead to this kind of stimuli responsiveness, and the most important mechanism that is like relevant to our compounds is FRET, energy transfer. And then I will be talking about some of the systems which we have developed in our lab in Isarmohali recently, and I will present some of the interesting photophysical and energy transfer characteristics of these systems, and followed by that I will be talking about the multistimuli responsiveness and the sensing properties. So when we talk about multistimuli responsive molecules and materials, these molecules and materials can be sensitive to different types of physical stimuli, classes of such kind of materials, which can include small molecules, polymers, composites, self-assembled systems, metal organic frameworks, and so on. Now when we talk about stimuli responsive materials, one of the key strategies which have been used by several groups around the world is to incorporate chromophores in the design. And when we introduce chromophores in the design of stimuli responsive materials, there are various ways by which these chromophores can be incorporated in the design. So this is just one schematic which shows that how we can mix three different chromophores of blue, green and red color. So one strategy is supramolecular mixing, where we just mix the chromophores based on self-assembly, and some of the examples are gels, crystals and polymers. Another important strategy is sequential bonding, where we can do a covalent connection of a red chromophore with a green one, and followed by that its connection with a blue one. So these kind of strategies are available, and there is yet another strategy which is the templated assembly, where one can use this kind of templates to organize the chromophores in a specific way such that we can get some desired function out of these chromophores. So examples include oligonucleotides, peptides, vesicles, micelles, inorganic particles and so on. So one of the important reason why we want to introduce chromophores in our design of multistimuli responsive materials is that because for chromophores it is very easy to do modulation of the optical response, because these chromophores are colored materials. So when we design our systems which contains chromophores, it is very easy to modulate their optical properties by changing either the physical stimuli or the chemical stimuli or both. So that is what I will be talking about. And when it comes to modulation of optical response, there are different mechanisms which can operate, such as photoinduced electron transfer or excitation energy transfer, which includes FRET or Dexter, and many other mechanisms such as TICT or AIE and so on. And the mechanism which I will be talking about today is the excitation energy transfer or the FRET. So most of the audience is familiar with FRET, but still for the benefit of the students who are attending this seminar, I will briefly talk about what is FRET. So FRET is a photophysical phenomenon where you have a donor chromophore and an acceptor chromophore, and there are certain prerequisites which are important for FRET. So there should be spectral overlap of donor emission and acceptor absorption. There should be spatial proximity of donor and acceptor 10 to 100 angstrom. So they should be at this optimal distance in order to show FRET. And there should be optimal orientation of the donor and acceptor transition dipole moment such that FRET can be possible. So this is just a schematic which shows that upon excitation of the donor from the ground state to the excited state, the excitation energy is transferred to the acceptor, which in turn basically it leads to the deactivation of the donor, which manifests as the donor fluorescence quenching, and at the simultaneously it leads to excitation of the acceptor, and then the acceptor fluoresces, giving rise to the acceptor fluorescence. And one important aspect here is when the separation between donor and acceptor is very large, it's actually larger than 10 nanometer, then no FRET is observed. And FRET is a through space process which happens when the chromophores are not connected through conjugation. Whereas there is another type of energy transfer mechanism which is called the Dexter energy transfer mechanism. It's also known as electron exchange, where the donor and acceptor, they are connected through conjugated linkage. But the distance has to be even much smaller. Since it's a through bond interaction, the distance has to be even smaller, less than 1 nanometer. And the mechanism is slightly different from FRET, but the eventual photophysical outcome is the same. So the donor fluorescence basically gets quenched and the acceptor fluorescence is visible. So when we talk about either FRET or Dexter, one important thing that we realize is that basically there are two channels of emission. One is the donor channel, one is the acceptor channel. So them for sensing. And the key here is to be able to modulate the emission in these two channels. So we have a donor emission, we have an acceptor emission. So whether we can modulate these two emissions by using different physical or chemical stimuli such as temperature, other stimuli. That is the most important aspect of utilizing FRET towards sensing energy transfer. So when we photoexcite the blue chromophores which are at the periphery, there is energy transfer from the blue to the green chromophores, and then eventually the green chromophores transfer that energy in form of a cascade to the red chromophore. And it has been studied that this kind of cascade energy transfer are quite efficient, like up to 80% efficiency can be achieved in this kind of dendrimeric systems. So in the early 2000s, several groups such as Mullen's group, Fletcher's group, they have developed this kind of dendrimer based light harvesting systems which consist of blue, green and red chromophores. Then in recent years, some other chromophore containing arrays have also been designed, such as the one shown here. This is by Raymond Zissel's group. So here they have designed BODP derivative, which is connected to another type of BODP which has a different, which is absorbing in the green region. And then finally they are connected with some other BODP which are absorbing in the, these are the blue ones, these are the green and this is the red one. So the color has been used in a slightly different way. So these are some green containing heterotriads that they have combined blue, green and red squaring within the same structure, and they have studied the dynamics of energy transfer in this kind of systems. And also they have some BODP containing multichromophoric system which are solar concentrators have been reported. So here I have selected only few examples, but there are many other covalent multichromophoric light harvesting systems. But the examples shown here, most of them have utilized the concept of blue, green and red, which basically leads to very efficient energy funneling. Now, when we talk about non-covalent multichromophoric light harvesting systems, there are many more examples. So I have just selected 3 representative examples. So the first example shows DNA, where the DNA has been used as a scaffold to design light harvesting complexes. So as you can see here, there are some blue chromophores in this DNA scaffold. So when you photoexcite the blue chromophores, there is energy transfer from this blue to the green chromophore, which is on a different segment of DNA. And finally, that energy porphyrin containing self-assembled supramolecular polymers have been designed, which also show very efficient energy transfer, FRET. And these systems have also been studied for their complexation as well as their photophysical properties. And recently, a group has developed this kind of polymer scaffold, and in these polymers, they have used 3 different types of BODP as pendants. So this is a blue BODP, green BODP and a red BODP. And this type of polymeric networks have been used for, so this contains RGB, red, green, blue chromophores, and this kind of polymers have been used for multicolor imaging, as can be seen here. So these are the different examples of non-covalent multichromophoric light harvesting systems. And very recently, one group has developed this type of multi-stimuli responsive FRET-based red, green, blue polymer luminescent probe. So here what they have done is they have taken a polymer backbone, PMMA, and that has 2 different types of chromophores attached. So one is the naphthalimide derivative and the other one is a rhodamine. And this naphthalimide, it's a metal ion probe, and basically it's the energy donor, and this rhodamine, it is the pH probe and it is the acceptor. So in this system there is a FRET occurring between the donor and the acceptor, and this FRET was found to be tunable by pH and mercury ion. So the fluorescence emission of BNPTU, which is this donor, it changed from green. Earlier it was green, but when this mercury was added, the emission was changed to blue, and the same change in emission color was also observed when pH was varied. So this kind of system was used eventually to generate some electrospun nanofibers, and these nanofibers could be used to obtain blue, green, red, purple and white emission colors depending upon particular pH and mercury concentration in the solution. So these are some examples where this kind of multi-stimuli responsive FRET based materials have been developed, and there are some examples. This is one example where a polymer scaffold has been used, but when we started working in this area, we found that examples of small molecule based RGB FRET systems which can be used as multifunctional sensors were not present in the literature. It was not very well reported, and that was the motivation of our work. So I will start so basically in today's talk I will be presenting two of our recent works. In fact, only this one I will be presenting in detail for the time constraint. So we developed this kind of azabodp and peridine triad systems, and these systems they showed very efficient FRET. So these were FRET cassettes, and based on the FRET, we could use them as temperature sensors, ratiometric temperature sensor. They could be used as multiple metal ion sensor, and these materials also, they are highly electron deficient, so they showed quite reasonable electron mobilities in the solid state. And this work more or less formed the premise for our next work, where we have designed some red, green, blue antenna systems, where we have used azabodp as the red central chromophore, peridine diimide as the green chromophore, and the peripheral blue chromophores were the naphthalamides. And in this work we have also developed the corresponding model compounds, which was the green blue GB, which contains peridine diimide and naphthalamides, and the red blue, which contains the azabodp and the naphthalimide. And we found that these compounds, they showed very efficient energy transfer as well as several types of sensing behavior. So just to summarize the first work in one slide, so this peridine diimide azabodp triads, as we call them, they showed efficient energy transfer as we could observe from steady state fluorescence and excitation spectra, and also fluorescence lifetime and quantum yield. So that was the important thing, that the azabodp and this peridine diimides, they form efficient FRET pairs. Then we could also see that this FRET, which was observed in these compounds, showed a very prominent modulation with temperature. So when we change temperature, this these two compounds, they showed linear behavior, and upon addition of cobalt and iron, basically the azabodp band got depleted because of a redox event. So basically the cobalt converts the azabodp into the azabodp radical anion, which leads to the depletion of azabodp absorption band, and that basically resulted. So when the absorption of azabodp is decreased, that led to a drastic change in the FRET behavior. So the FRET basically increased because this absorption is now decreasing, and using this behavior we could use for cobalt and iron sensing using these two compounds, and eventually these two molecules showed efficient electron mobility in space charge limited. We can use this kind of moiety and further refine our system by analysis. As you can see, the final step included a copper catalyzed azide alkyne click reaction to get the RB6 antenna compound. In a similar way, GB antenna, green blue antenna was synthesized starting from tetrachloroperidine disanhydride. So first we found phenol groups, and eventually we converted the OH into the tosyl and followed by that azide. So in this way the GB compound, the GB antenna was obtained, which is compound number 13. And eventually we synthesized the RGB antenna, which was a quick reaction between compound number 13, which is this compound, and the azabodp containing two triple bonds. So again quick reaction, And finally, we obtained this RGB antenna 1 in reasonable yield, but of course purification and other things was quite challenging in this case, but eventually we obtained these compounds. So as you can see from in this graph, the compound number 1, it has absorption, prominent absorption in the blue, green and red region, and that is the reason we call it as RGB antenna. So RGB signifies the absorption in red, green and blue region. Similarly, compound number 5, which is the azabodp, you can see that it is absorbing predominantly in the red region. 9, the donor absorbs predominantly in the blue region, and so on. And the emission behavior also showed that there was efficient energy transfer. So I am not going into those details. This is the fluorescence excitation spectrum, blue and green blue. In the RGB system, we could see the behavior of the individual chromophores when we did the oxidation and the reduction cycles. And this spectroelectrochemistry manifested itself nicely in terms of color change when we actually took the experiment and we saw how the color was changing. So in the RB6 compound, in the neutral state, it was light green. In the oxidation cycle, it became this kind of olive green. In the reduction cycle, it became this kind of olive green, which was due to the formation of azabodp radical cation and anion. In the case of GB12, earlier it was orangish color, but upon oxidation it became pink, and upon reduction it became this kind of fluorescent green. But eventually it was completely reversible and we could get back the original color. And in case of RGB system, the initial color of this compound is brown in solution. Upon oxidation it turned to purple, it was completely reversible, and upon reduction it turned this kind of fluorescent green, which was again reversible. So we could do this kind of reversible optical switching of these antenna systems by redox changes. So we could say that these compounds are redox, can be used as redox switches. Next thing which we tried was acid-base sensing, and in acid-base sensing again we saw something very interesting. As you have seen, the compound has 3 bands, the blue band, green band and red band. So upon increasing the acid content, like when they are doing a titration with TFA, it was only the blue band which was significantly changed, it was getting quenched, but the green and the red band was not changing significantly, and the same thing was observed in the fluorescence also. Although in fluorescence it was changing to some extent, but in the absorption we could clearly see a color change from brown to purple, and it was reversible when we did the back titration with triethylamine. And similarly for the RB antenna, red-blue antenna, we could again see that when we did a titration with acid, it was only the blue band which was changing significantly, and upon back titrating it was completely recovered. So from these experiments, what we could understand is that this RGB system, one specialty of this RGB system is we could modulate selectively the blue absorption band without doing much significant change in the green and red absorption bands. And what was also interesting is when we did a chromaticity plot, so when we excited the solution of 6 at 396 nanometer, the color changed from green to blue. And at a particular amount of acid, we could get a white light emission which has a coordinate of 0.33, 0.32, 0.33. And similarly, when we did the excitation at 442 nanometer, the emission colors changed from green to yellow. So we could say that using acid and base, we could do a reversible optical switching, that is the RGB system gets converted into RG because the blue band was getting quenched, but it was reversible. So when we add acid, the blue band vanishes or gets depleted. When we add base, it goes back and we get the RGB absorption. Followed by this acid and base sensing, of course we have done some further analysis and we tried it in semi-aqueous medium, but I am not showing those details. Those have been provided in the actual publication. And then we also used this material for trying to sense metals, and we could see that RGB antenna 1, it was responsive to iron 3+ and cobalt, which was characterized by significant depletion of the azabodp band like this. And as the azabodp absorption band was depleted, that directly had a consequence in the energy transfer. So in the energy transfer also, earlier when there was efficient energy transfer, this the donor bands were very small because this emission was quenched. But as we added more and more metal, this band started getting quenched. So as a result, the spectral overlap between donor and acceptor changed, and that is why the the extent of fret also started changing. And this kind of behavior could be used for analyzing we could analyze this kind of data using something known as a Marx model, where we could use this data to calculate the binding affinities and binding constants and all those things. So basically in this study what happens is the azabotype absorption is getting depleted, and that basically reduces the spectral overlap with PDI, and that drastically leads to Fred turnoff. So this is the example of Fred turnoff. So this band goes down, this band goes up, and that could be used for sensing of cobalt and iron. And this kind of metal ion induced modulation, so here what we can say is, in the red green blue system, the blue and the green bands are not influenced by the metal, it's only the red band which was influenced. So this metal ion induced modulation of the red band, and that led to the conversion of this RGB antenna system into a GB antenna. And once this red band was quenched, it was depleted, it was not recovered back. Like during the experiment, it got quenched and it was steady at a particular value. So in this way we can say that the metal ion induces a modulation of the red band, and then that led to the conversion of RGB antenna into GB antenna. So from this study we could say that this Fred antenna which we have developed, the red green blue, the green blue and the red blue. So I am not showing the data for the other two antenna, but we have performed those experiments also. So all of them are responsive to the metals. So therefore we can say that these compounds are multiple metal ion sensors. And here the modulation occurs mostly in the red band. Then finally we made some composites of this antenna along with PMMA, and this is one such study. Was orange color when it is visualized under UV light, but upon TFA exposure it becomes pink, and then with time it recovers. Similarly, when we heated this, the color again changed from orange to lighter color, and with time it got recovered. And we could then say that this antenna PMMA polymer composites, they are reversible, thermoresponsive, acid sensitive and metal ion sensitive fluorescent inks. And the last one is the RGB compound. So the RGB compound was pink. Upon TFA exposure, it gets completely the color changes to almost not visible. And then with time, as the TFA evaporates, it recovers its original color. Similarly, with iron 3+, the color is again changed and it becomes more whitish in color, and with heat also the color is changed, which can be recovered back when with time. So from these studies we can say that this RGB antenna systems, as well as the subchromophoric compounds such as GB and RB, all of this can serve as switchable and tunable fluorescent inks, and this type of applications are very useful when we want to develop some anti-counterfeiting or security encryption kind of materials. So to conclude the work that I have presented today, so we have developed this type of RGB red, green, blue and red, blue antenna systems which can act as multifunctional sensors and optical switches. And first of all, this antenna system showed a very efficient cascade energy transfer from blue to green, green to red. And then based on the 3 absorption bands, when we used acid and base addition, we could selectively modulate the blue band, and that leads to pH sensing behavior. When we are using metal ions, that selectively modulates the red band, and that leads to Fred turnoff and therefore a metal sensor. Apart from this, the molecules also show ratiometric temperature sensing because of the variation of the emission in the different channels. They are also electrochromic sensors because they can show reversible color change upon varying the redox stimuli, and eventually these molecules can serve as reversible fluorescent inks which can be used for security encryption and other applications. So these are the important conclusions of this work. So efficient Fred, 100% from peripheral chromophores to the central azabotype, ratiometric temperature sensing with a sensitivity of 0.4, which is a very accurate sensitivity, and it means that this kind of molecular sensors can be used as ratiometric thermometers when if you want to utilize them for some monitoring of cellular microenvironment or other kind of similar kind of application. They showed distinct solution phase electrochromism. They showed reversible modulation in the blue absorption band and it's a pH sensor which showed this kind of variation. And they could sense cobalt and iron through Fred turn-off mechanism, and in addition to that, it also showed white light emission with CI coordinates of 0.33, 0.32, or the other way around, 0.32, 0.33. And finally, these PMMA polymer composites were utilized as reversible, thermoresponsive, acid-sensitive, metal-ion-sensitive fluorescent inks. So this thermoresponsive and acid-sensitive were reversible, metal-ion-sensitive was irreversible. And we envisage that application of this kind of multifunctional sensors can be used for detection of pH, temperature or metal ions in the cellular microenvironments. So that concludes my talk for today. And before I end, I would like to acknowledge my group. So the work that I have presented today is performed by Kavita, and these are the other students in my group. So I am also thankful to the past BSNS students of my group who worked from 2019 to 21, and the Department of Chemical Sciences, Aisar Mohali and DST. And
yeah, Sanjita, this is Jamal from IST. Yeah, first of all, wonderful talk, very good design of the material. And the observation of RGB, have you tried to utilize for white light emission apart from sensing?
further, because one point is that the white light emission is observed in solution phase. So in order to go for some application, I think it will be preferred if we can get it in thin films, or like in films, if we can get white light emission, then we can probably think for some possible application.
So if there is a first speaker is Dr. Mr. Shankar. Now it's my pleasure to introduce Dr. Shankar, Professor, IIT Roorkee. Thank you, Dr. Shankar, for taking time to be here. We are very grateful to you. So, Professor Shankar, after clearing missions at Israel, France, and Japan, then in 2011 he joined as faculty at IIT Roorkee and professor in 2020. Dr. Shankar managed scholarships, awards, and fellowships into 2011, and then another 2007 to 8. Fellowship from Israel, US Binational Scheme, State Level Scholarship from Tamil Nadu Government. The title of today's talk is...
Thank you, ma'am. Good afternoon to all. It's a lunchtime, it's difficult to talk like so so I'm sure that actually I'll finish by 20 minutes. Like, okay, it's good that actually, like, so if I remember that this is my 5th visit to Amritsar and the 3rd visit to CNDU actually, like, so I'm happy to be here, and it's a good place. Like I learned today that this is a very vibrant department. I also know that, but your chairman has explained well in the morning. So today I will be talking about synthesis of carbon-based supramolecular. Of carbon-based supramolecular systems and their application in solar cells, PTT, anion sensing, catalysis. I have organized my presentation in the following manner. First, I will talk about importance of functionalized porphyrins, basic introduction, and then I will discuss about solar cell application, and then detection of anions. Then third one is that electrocatalytic applications. A little bit about antimicrobial activity. That, as we all know, that tetraploid pigments play an important role in biological system. For example, heme proteins, hemoglobin, thus oxygen cytochromes are important for electron transfer process that is coupled with our respiration. And this chlorophyll plays an important role in photosynthesis. It's having a chlorine ring system. You can see one of the rubber bond is reduced, and then 26 5-membered ring is coupled with the chlorine. Here is a fully conjugated porphyrin ring. This is what we are preparing in the lab, and then utilizing for different applications. Then this is the bacterial chlorophyll, that 2 of the double bonds are reduced. And then vitamin B12, this also tetraploid pigment, it has a chlorine ring system. It is important for DNA synthesis as well as group transfer reactions. Here is cofactor 430. It is important for conversion of organic sediments into methane. The fifth one is that cytochrome P450. This is the heme enzyme. It catalyzes polyaromatic hydrocarbons or all the alkanes into soluble form of alcohols. So the diverse functions of heme protein prompted the laboratory synthesis of porphyrins. This is for the UG PG students. This is the tetrafluoride skeleton called porphin. When there is no substitution, that's called porphin. And then here alpha, beta. So 8 such beta positions are there, and then bridge position called meso position. So this is an example for the meso-substituted porphyrin that called 5-10-15 tetraphenyl porphyrin. So the numbering starts from here, alpha carbon goes in a cyclic manner, and this is an example for beta-substituted porphyrin. So for our understanding, actually porphyrin has a well-defined HOMO, that A1U and A2U contribution from here alpha beta carbon, and then for meso position as well as nitrogen for A2U. Actually you can tune this in energy levels by appending appropriate functionality. Suppose you have electron withdrawing group here, then that will bring down your 5-star level lower. And then if you have electron donating group, that will affect the HOMO, your HOMO will rise. So that if your HOMO rises, it is easy to, HOMO rises 5-star like carbonyl or fullerenes, they are easy to reduce. And also you can tune this band because of the porphyrin macrocycle present in that. Like heme, that it is highly biconjugated, so there is absorption in the red region as well as in the purple region. The combination you will get red color. So here there are lot more applications of porphyrins are known. In the beginning they have used porphyrins for biomimicry studies like oxygen binding. Nowadays people are using for catalytic applications, electrocatalysis and other things. And also they can be used as a sensors, like when you have Lewis acid, you can bind with the ligands, you can act as electronic nose. You can identify amines, alcohols, thiols like that. And also in nature, we have seen cytochrome P450 uses heme. The same synthetic porphyrin can be used as a catalyst. So here, apart from that, they can be used as a sensitizers in solar cells because it has a very good absorption in the visible region. Here we can have a donor and acceptor. Donor by acceptor systems are very good because you will have effective charge transfer, and then it gives very good efficiency of 13% photon to current conversion efficiency. And also they can be used as a sensitizers in photodynamic therapy. Like Professor Hume talked about that. Like this is a very famous molecule called photochlor, and it is actually an approved drug for the photodynamic therapy. And also push-pull porphyrins are utilized in nonlinear optics. Actually, particularly they are useful to have bioimaging. Here, this is the eye of a mouse that we can see here. There is a blood circulation. No blood circulation is there. There is interrupted. Then after the surgery, then they can take the image, and then they can see that very clearly that there is a restoration of blood circulation. So, like this very minute images also can be taken using porphyrin derivatives. Actually, this is for the UG students, like how one can prepare porphyrins. Like everybody thinks porphyrin is difficult to synthesize, but it's very easy to synthesize. You can take pyrrole and then corresponding aldehyde, refluxing propionic acid, you can get porphyrin. And if it is your aldehyde is acid sensitive to acid as well as temperature, you can say like BF3 etherate. It gives porphinogen under organ atmosphere, and then we can add DDQ or parachlorinate. One can get porphyrin in very good yield. Or one can synthesize with the dipyrromethane also, or we can prepare differently substituted porphyrins, taking two different dipyrromethane, the aldehyde and carbinol, and then when we condense we can get porphyrin. No need to get commercially available porphyrins. One can prepare in a lab in a very simpler manner. Actually, these are our recent work in porphyrin lab at IIT Roorkee. Actually, like mainly we work on synthesis of porphyrins and chlorols and chlorines, and we utilize those porphyrins for reduction of toxic ions, catalytic applications and electrocatalytic studies, as well as NRO and photodynamic solar cells applications. Actually, today I will give only 4 examples about sensing, as well as DSSC, like solar cell substitution and electrocatalysis. Actually, this is the energy source in India. Like we mainly focus on renewable energy sources. As of 2018 March 31st, that we invested 20% for the renewable energy, but within 2 years, like our government spent 36%, like encourages to go for renewable energy sources. In the solar, you can see from 7 to 10%, but latest, like up to December 21st, that we are spending, we are utilizing renewable energy sources much, that is about 38%. In that solar energy is about 12%. So solar energy harvesting is very important, that we must utilize it actually. And also they have a lot of advantages that you know about the solar energy. Actually here this is the largest solar power plant. It is there in Badla, Rajasthan. It produces 2250 megawatt solar power. Sorry, through solar power. And it is serves 10% of the state's power usage. And also it is one of the airport, Cochin airport, completely uses solar power, and it is a capacity of 30 megawatts. They got the price also. Like it is good. The entire airport is operated using their own energy source. So here we know about solar cells, like the first generation of materials, then second generation is some more possible. But we are mainly focused on this. When this is the sensitizer, when you shine light on that, it goes to excited state. Then excited state electron transfer takes place. So that electron we need to harvest. Okay. Then there will be a redox mediator that will regenerate the dye. Okay. So this is the well-known dye, YD2CA. It is prepared by actually Chinese group and then replaced by Professor Granger. But the thing is that if you look at the synthesis of this, at least it takes 15 steps to synthesize. Whatever the dye is available in the literature, if you want to synthesize, at least you have to spend 6 months to 1 year time just for synthesis. Then we took that problem, actually why don't we make a simpler synthesis? So what we have done is that we have utilized dipyromethane. This dipyromethane can be prepared, just you take a pyrrole and then acetaldehyde, and in HCl medium you can get 95% of dipyromethane, and then condense with aldehyde you will get porphyrin. Then this porphyrin can be methylated without purification, you will get metal of porphyrin. So in 3 steps we could make, like people are making in 15 steps, then we could make it in 3 steps actually. And also like we could vary the donor groups here. Like for example here phenyl, bromophenyl, thiophenyl, pyrene, like that. First we varied this 5 and then we got up to 4% efficiency. Then we thought that okay, the donor groups plays important role. Then we started tuning from bis-thiophenyl, the diphenylamine, phenothiazine. Phenothiazine we got very good yield, about 7% in a very simplified way, and there is no inert atmosphere we use, all at room temperature, and we exposed for several hours, still the dye was stable and is giving 7% efficiency. Then we thought that we want to tune the donor groups, because when you have donor group phenothiazine, it's giving highest efficiency. We started putting 3 phenothiazine, but unfortunately we didn't go much, it stays there only. And also we thought we have 2 donor and 2 acceptors, this carboxyphenyl. In that case actually like then we faced a solubility problem. After that we co-absorbed with N719 dye. That N719 dye commercially available, that when we mix with that we go up to 9% efficiency. So this is how like we can tune our porphyrin systems for the solar cell applications. Then currently now we are working on this kind of porphyrins, simple porphyrins, utilizing for perovskite solar cells. We are getting good efficiency, about 15 to 20%. Right. When you look at this the data, photovoltaic data of these porphyrins, starting from phenyl to phenothiazine, you can see these photovoltaic parameters like outer circuit voltage and the short circuit current all keep increasing. So this sets a trend that when you have a good donor, you can able to tune your photovoltaic parameter as well as fill factor, then finally your efficiency. So this is the take-home message from this work. And so currently like we are working on porphyrin, Just right. Sorry. Here. Full screen now. Sorry for the interruption. Like, then now we are preparing this cationic porphyrins. Generally, porphyrin is used as a acceptor group. Here we donor groups, but here we made protonated porphyrin. They are used as acceptors and then having hydrogen bonding network. And when we look at the crystal structure, that it is forming nano channels, like you can see that this porphyrin, and then we are able to put donor groups such as that TTF, tetrathiophyllite. It's a well-known donors, and we are able to put at least 10 donors in the nano channel, like hydroquinone and many other derivatives. And when you look at the photovoltaic parameters, then that porphyrin having 4 carboxyl groups, we could able to get about 8% efficiency. Then when we have octacarboxy, we can able to go to 30% efficiency. Still we are working on to improve further. And this is the solar panel which is present in Geneva airport. It's made by Professor Greatjet. When we have efficient dyes and highly stable dyes, one can make use of the solar energy in a very good level. So this is how actually one can make, like this is the e-power stations, like one can go and charge their e-vehicles. So this is how in India yet to come, but if dyes are available, then it is possible for us also. Then it's about the photodynamic therapy. Professor Yawan has given enough introduction, and you know about this also, like that can be a electron transfer or energy transfer. So if this is the path, second path, if it is electron transfer, that is will give you ROS. So here this is the well-known photochloride dye I told that commercially available at Roswell Park Cancer Institute. And what we have done is that these are the we can say that FDA approved photosensitizers. It's available in the market. The problem is that they are very expensive. One has to do extensive synthesis and functionalization, so that it is per treatment is there. We need to spend 20 to 30,000 rupees. What we thought that actually we will make simple photosensitizers. We prepared mononitrophosphates and then reduce it to monoamino group. And what we have done is that we conjugated with CNT. Here, like we have taken SWCNT and then we treated with the nitric acid. We got carboxy abundant CNTs, and then we did DCC coupling with aminoporphyrins. We got porphyrin abundant CNTs. So we characterize by using spectroscopy. This is for the pure porphyrin. This is for the nano conjugates. And fluorescence also switching because CNT is the acceptor, porphyrin is the donor. And you can look at the FESM images. This is for the carboxylic acid. You can see the functionality, like, and then if you look at this, then it is different after functionalization of porphyrin. And it is very clear from the TEM images. So here the TEM image shows that SWCNT has a tubular structure. And then when you look at porphyrin abundant CNTs, you can see that the dark surfaces indicates that porphyrin is accumulated over there. So this is the indication. And then when you look at that thermal analysis, it is stable up to 350 degrees Celsius. And when we do the photodynamic studies, that this is the untreated bacteria that was grown on the surface, and then when we treat with the light, the simple tungsten halogen lamp, and then completely kills bacteria. So that which indicates that this porphyrin appended on CNT acts as a photodynamic agent, the photosensitizer, that it can kill bacteria. And when you look at here with the time scale, that this is the completely grown bacteria. After 10 minutes of exposure, it kills. Then after 60 minutes, completely kills. Then you can see here this graph that the required amount of this porphyrin is 0.08 milligram per ml, very low, as well as within 1 hour 100% of bacteria is killed. So this indicates that actually like porphyrin sensitized systems are good for antibacterial activity, and we are now we have used CNT appended porphyrins. Later what we have done is that we extracted chlorophyll from the plants and then we utilized as a photosensitizer. It's also working very well and water soluble. That work is under progress actually. Then further, like anion sensing, our institute is well known for anion sensing GNDU, and I referred several papers of Professor Manoj and Professor Balla. That's how I come to know 15 years before about anion sensing. When I start my independent career in IIT in 2011, I continuously used to read your papers, and also I am teaching supramolecular chemistry. I used to take examples of this logic gates from GNDU work as well as for the aggregates induced emission. That also I take a lot of papers are there. I used to take some literature and discuss in the class. So you know about the importance of anion sensing. Fluorides are utilized for clinical treatment of osteoporosis, but overexposure gives problem, acute gastric fluorosis and kidney problems. Cyanide also, that they are highly toxic in nature, and when cyanide is there, that stops the respiration by making iron 2 to iron 3 oxidation of cytochrome C, and then that interrupts the blood transportation of oxygen actually. Okay, so this is how cyanide is very important, and it is used by many industries. Accidental release of cyanide will give high toxicity. So like we thought of developing cyanide sensor, these are the literature available. But the thing is that none of them are recyclable and not water soluble. So we thought that we will go for water soluble and recyclable. So this was the first work. We have taken a non-planar porphyrin, tried to interact with the anions, but we got disappointment that this porphyrin interacts with the fluoride, acetate, diadenyl phosphate and cyanide. Then we thought that okay, the mechanism is like this, that there is a porphyrin core and having bulky groups around the periphery, it is non-planar in nature, it will start interacting with basic anions. Then we protected the core, it was very selective for cyanide ion. That's where supramolecular chemistry plays a role, that when you have electron deficient metal center, that then when you have cyanide Lewis base, then they start interacting and forms a charge center complex. We characterize and the LOD comes in the like sub ppm level. And the good thing is that this is recyclable. You use your sensor and with, then with the cyanide it changes its color. You can detect by naked eyes, but you add a trace of TFA, then you can regenerate your sensor. Then you can use it for numerous cycles, and you can also test aqueous as well as non-aqueous solutions by making test strips like a pH paper. And 1 milligram, you will not believe, we can make thousands of strips because porphyrin is having very high molar coefficient. We can dip in the water filter paper and then we can make lot of strips, and it is useful, recyclable also. That after when you add treatment with TFA and then again you treat, then it can be used also. And then there is another system we developed with the dicyanovinyl vinyl. Here the metal center is not electron deficient, then it binds through nucleophilic attack. Even THC plates we can use to sense cyanide ions. And here, sorry, so it's not coming. There was one more. Okay, so here also we can get very low detection limit and very highly sensitive for this. And here we develop further cyanide with the fluoride. So here we kept the functionality, the phenolic group. Then when we add fluoride ion, this oxidizes this phenolic group into phenol. But when we have metal, it forms only the orthodimethane. And then when we don't have metal, it completely oxidizes. In that way we control. When we have metal, it forms orthodimethane, it's blue in color. When we add cyanide, it undergoes nucleophilic substitution, it gives color of purple, so that we can easily distinguish two ions. And this is how they are recyclable actually. Like you can take this free base and then when we have fluoride ion, it forms porphinogen, and then when you wash with water, and you can get this porphinogen and then treat it with ascorbic acid, that is vitamin C. redundancy, you will get back. So that will be for several cycles actually. That. Then we have developed some sensor for picric acid, because picric acid is one of us, then cyanide fluoride, and you will have a vice versa also. You can be able to detect at to sub ppm level. So this is the, you can say, one of the second report on unrestricted indicator display assembly to detect 3 of the anions, that is cyanide, fluoride and picric acid. And the last work is that orphan based catalyst for electrocatalytic applications. You know that electrocatalysis is very important, particularly fuel cells as a component of that. This we put it on the electrode and use it as a catalyst. So that selectively converts. So that's where the supramolecular. So yes, actually in the like we can say that in 2000. Yes, actually, sir. But ruthenium problem is that people discourage using ruthenium because ruthenium complexes are expensive. Second thing is it's not that much available, and a cost factor, and environment, it's not environment friendly. When we take ruthenium complexes in water, then that is toxic to aquatic system actually. So people now say that you go for organic dyes or like water-based organic dyes. Zinc is better because redox inactive. But other cases like cobalt, nickel and all, it undergoes spin coupling. So some loss actually. No, nickel, orphans are not toxic because that is biocompatible. Iron 2 and then oxidizes actually. Later on it oxidizes to iron 2. Then you need the shuttle. Electron transfer should occur. Cytochrome C. If you affect that, respiration will be affected. But many people think that cyanide goes and binds with the hemoglobin. It's not. It actually mainly binds with cytochrome C and that it stops that electron transfer. Actually, it oxidizes the iron. It oxidizes the iron. Oxidizes iron 2 to iron 3. Then that one of the keys. Okay. But that's all they are actually in the standard explanation they give it. But people discourage that it binds with hemoglobin, it doesn't bind with hemoglobin. If it binds also, irreversibly binds. That's yes, sir. Actually, this is a mixture that we can, the single column we can separate it out. But mixture is, this is the one. This is actually.
Second speaker of this session is Dr. Partha, Associate Editor 1 year. Professor Partha has done his Masters in Physics and PhD from USA in modeling electron transport in single metal molecule junctions using AMD-based computational tools. He has done postdoctoral research at University of Michigan, Northwestern, and Pennsylvania Institute. Chemistry lab team in January 2009. Currently, he is at Mumbai and joined his team in 2020.
I'm trying to share my screen. It says host visible attendee screen sharing. Okay, am I visible now? My slides rather. Yes. Okay. Thank you so much for giving me the opportunity to talk in this wonderful symposium. On behalf of YD, I would like to congratulate Professor Manoj Kumar for his 60th birthday, and we wish you many more healthy years ahead. So we had a very nice session of wonderful science, and just a change of gear, I'll briefly talk about want to hold you back for your lunch. So, a student and a postdoc like involved before I joined YD. So this is our team. We started the India office in 2018. Khushbu and I are based out of India. I'm sitting in Mumbai. Khushbu is in Delhi. So most of our journals are associated with societies. One of them is the German Chemical Society. So it was founded back in 1887-88. The journal Angewandte Chemie is, however, published by Wiley Research, which is a subsidiary of Wiley. The other society we work with is Chemistry Europe. It has 16 chemical societies from 15 European countries. Apparently, Austria has 2 chemical societies in Chemistry Europe. And right now, we have around 18 journals for this society. Then there is the Asian Chemical Editorial Society, the Chemical Research Society of India. There is already a local chapter there in Amritsar, so you must all be aware of the society. So it's one of the founding members of the ACES. ACES consists of, as goes by the name, the Chemical Research Societies of some of the Asian countries. The flagship journal of ACES is Chemistry and Asian Journal, and then there are the 2 more topical journals, Asian Journal of Organic Chemistry and Chem Nanomat. So CRSI actually receives royalty if Indian authors publish with the ACES journals, which they can use for any CRSI activities. Now mentioning about CRSI, Khushbu and I both are going to the CRSI conference next week in IIT Guwahati. So we have a lot of Indian connections. Professor CNR Rao was one. We have had earlier career advisory board, and you just heard Dr. Sengupta talk about our research. We are looking into more and more early career researchers to add into our advisory boards. Some of the recent projects which we have done or are still ongoing are the 15 years of ICER Pune and ICER Kolkata. It is an ongoing special collection, so researchers from those institutes have been invited to submit in the Chemistry and Asian Journal. Then this is another ongoing special collection. It's in Campus Chem. There was this theoretical chemistry symposium in December 2021. Initially it was supposed to be held in ICER Kolkata, but then they moved to a virtual format. And these are the 2 recently closed special collections. So our top general chemistry journals are Angewandte Chemie, Chemistry European Journal, and Chemistry and Asian Journal. Some of the topical journals you are already familiar with. They would be the Asian Journal of Organic Chemistry, the European Journal of Organic Chemistry, and Advanced Synthesis and Catalysis. The physical and inorganic chemistry, so we covered those subjects also. I am an editor for ChemAt, which is an ACES journal, and then there is batteries and supercapacitors. It's a Chemistry Europe journal, and then a couple of materials journals which are owned by Wiley. So all of you are probably also aware of the advanced series of journals. It started with advanced materials, and then because of its success, we had more of topical journals like advanced functional materials, small advanced energy materials, and then there is a fully open access advanced science. Some of the interdisciplinary and the multidisciplinary journals are Chem Plus Chem, Chemistry Open, and then there is the Chemistry Select, where we publish any work which is scientifically thorough. So for enhancing the accessibility of our journals, we also have this mobile app, which has all the journals belonging to this group, the Angewandte Chemie, ACES, and the Chemistry European Journal, Chemistry Europe journals. So that's all about, I have to talk about our journals. Now, I'll talk a bit about which we face often. For example, how are the reviewers chosen? So when we receive a manuscript, we do read through it, the cover letter, the abstract, and some parts of the main text. And then if we decide that we are going to send it out for peer review, this is how we choose the reviewers. So they are chosen by their expertise publishing record, which we pull from their websites or even the databases. We do consider author suggestions. We make sure that there is no relationship or conflict of interest with the author, both positive or negative. We do have internal reviewer suggestions, which means I can we do discuss with our colleagues if they suggest someone. We sometimes choose from our editorial board. In most of the cases, I would say the editorial board members we choose when there is a conflict between the author and the reviewer. And then also we have some amount of experience, so we have some names on top of our head. So during conflict of interest, and then the way we ask you to suggest reviewers is who, where, and why. So Professor A, the question we do often face is how to appeal when in the case of rejection. So this is how we suggest. Please write a detailed letter to the editor and include a point-by-point response. Usually we ask you to upload the point-by-point response in the form of a separate Word or a PDF file. Suggest that you consider revising the article in some way to clarify your argument. You do not have to agree with this. Write it out and try to clarify the argument why you do something. Please take time to respond to all the comments because it would save further peer review, which is going to save you a lot of time. So you might spend a couple of hours more for preparing the response letter, but that can save you another 2 to 3 days of time. If we are happy with the responses, we don't send it out for peer review once again, so we accept them right away. And also,
thank you, Manoj, for chairing this session. So now we will take a next break before we move to technical session 4. And before lunch, I request all of you to assemble outside for cake cutting ceremony to celebrate the birthday of Professor Manoj Kumar.
भाजी अगो साइड तो जाओ। ਇਹਨਾਂ ਨੂੰ ਸਾਈਡ ਤੇ ਕਰਾਓ ਇਹਨਾਂ ਨੂੰ
2 ਮਿੰਟ ਬਾਅਦ ਸੈਟਿੰਗ ਕਰ ਲਈਏ
ਇਹਨਾਂ ਨੂੰ ਸਾਈਡ ਤੇ ਕਰਾਓ
ਫਿਰ ਸੈਟਿੰਗ ਕੌਣ ਕਰੂਗਾ
ਮਗਰਲੇ ਪਾਸੇ ਜਾ ਕੇ
वीडियो बनाई जाते बना देते
सीसीटीवी कैमरे भी लगे हैं
लगे
मैं लगा लिया
नहीं लगे वीडियो बनाए
हाँ इन्होंने वीडियो बना रही हाँ नहीं मेरा अकाउंट बना आगे साइड हो जाओ भाई ऑन साइड हो जाओ
भाई इधर भी हो
रो ये यार भाजी आ जाओ मगर आ जाओ भाजी आ जाओ वाइट खिंच लो नहीं सको कैमरे तक आ गए जी मैं नहीं करना हम परे
बोले अगे ले रहा मैं
एक मिनट भाजी बाह आंदी पई मैंने छोट ले रहा दो बाह आंदी पई मैं रिकॉर्डिंग आई हूँ फोटो हाथ तो बड़े अगे आए
पहले क्यों नहीं पाया
ਥੋੜਾ ਜਿਹਾ ਪਿੱਛੇ ਕਰ ਲਓ। ਲਓ ਜੀ
आ जाओ यार मैं कह देना ले आऊँगा पीछे आ जाओ जितना वाइड आवागा उतना सही रहेगा। पिछो करी सारे भाई थोड़ा सा पीछे लो जी ठीक है कोऑपरेशन बहुत हो रही है। ਉਹਨੂੰ ਕਹੀ ਯਤਨ ਨੂੰ ਯਤਨ ਨੂੰ ਫੜਨਾ ਹਾਂ ਹੀ ਮੈਂ ਇਦਾਂ ਕਰਕੇ ਬੇ ਉੱਤੇ ਲਾਈ ਨਹੀਂ ਤੇ ਮੈਂ ਤੇ ਭੰਦ ਰਹਿਣਾ ਇੱਧਰ ਉੱਧਰ ਯਤਨ ਆਏਗਾ ਨਾ आयो मगर आप इधर आ जाओ आप उधर आ जाओ भाई इधर साइड फ्रेम हो ना इधरले पास ले आओ एक दो जन एक और आ जाओ एक और उधर चले जाओ इधर सेंटर फ्रेम रहेगा ना उधर साइड में चल जाता सारा भाई वेट
AI active supramolecular enzyme for detection of creatinine in human blood serum. Here, initially, the first of all, I will introduce for this work, that is for known methods for estimation of creatinine level. Use the harmful picric acids, so that are very harmful for human health. So we designed to find a method that will be eco-friendly and would be a cost effective. So why we choose creatinine, as creatinine is very important renal waste that is needed to be expelled out of the kidneys. So its detection is very important. So here these are few objectives of us to design this probe tree that is based on cyclopentanol derivative. We designed this probe because this core is AI active fluorescent probe, and that is very that it contains yes, when we took our probe, first of all we took our probe in 60-40 ratio of water and DMSO, then we add betaline in that, and that makes the metallic ensemble, and that metallic ensemble we add creatinine from outside, and here are we also use the blood serum, which we yes, we took the samples from estrogen
ऐसे ही ज़्यादा लगते हैं।
ਵਾਈਫਾਈ ਵਿੱਚੋਂ ਬਲਿੰਕ ਮਾਰ ਜਾਂਦਾ ਵਾ ਉਹਦੇ ਤੇ ਜੀਪੀ ਦਾ ਹਾਂ ਵਿੱਚ ਬਲਿੰਕ ਮਾਰ ਜਾਂਦਾ ਇੱਥੇ ਵੀ ਸ਼ੋਕੇ ਰੈੱਡ ਲਾਇਆ ਆ ਜਾਂਦੀ ਲਾਈਨ
नेट
So welcome back after lunch. So good afternoon to all of you. So we are going to start with our technical session 4. So Professor Sapndeep Singh Chimney is going to chair this session. So I invite Professor Chimney to please come on the dais. Please, sir.
Well, thank you, Dr. Prof, for giving me this opportunity to chair the session. We have two speakers in this session, Professor Amitabh Das, who has been waiting for a long time for us, and Professor J. Govindasani. So the first lecture is by Dr. Amitabh Das. So I'll give you a brief introduction about Dr. Das. So he's a graduate and a PhD from Jadavpur University, Kolkata, and he is a recipient of a number of awards and even national fellowships as well. The most recent one is the DST JC Bose National Fellow, which he got in 2017. And he's a fellow of all the three major science academies that we have in India, which is Indian National Science Academy, Fellow of the National Academy of Sciences, Fellow of the Indian Academy of Sciences. He's also a Fellow of the Gujarat Science Academy, and he has been awarded with bronze as well as silver medal by Chemical Research Society of India. So he has a very great career, as you can see. He has many awards to his credit. Then, as far as publications are concerned, he has been very active in publishing. He has an H-index of around 52, and he has around 215 publications. And the important thing is he has patents, and there are 21 patents, either filed or under review. So that's a great achievement on his part. Then he has been director of a CSR laboratory that is called Central Salt and Marine Chemical Research Institute at Bhavnagar, Gujarat. And he has recently completed his tenure there, and now he's joined back as ICER Kolkata, where he was originally a professor, and nowadays he's the Dean Research and Development. And with these few words, I invite Professor Amitabh Das for his talk. Purpose-built molecules and assemblies for imaging or diagnostic applications. Welcome, Dr. Das.
Hello. Am I audible? Okay. So thanks for to organizer for giving me the opportunity to be associated with this conference. And it's a very special conference. At least it was for me, for my this being organized to celebrate the 60th birthday of one of my close friend, Manoj. I wanted to be there personally, but due to some reason, I couldn't make it. So I had left with no option but to participate this one through this conference through this online mode. Anyway, so thanks again for giving me the opportunity to be associated with this special option. So today I am going to talk about the purpose with molecules and assemblies for imaging and theranostic approach. So if I briefly talk about the way I can define my research activity, my group's research activity is basically under the synthetic chemistry. I will not define myself as a synthetic inorganic or organic chemist. I will define rather as a synthetic chemist. But when we try to synthesize a molecule, basically we try to assemble the mononuclear or the components in such a way so that either the supramolecule or the assembly does the work the way that we want that molecule or that assembly to behave. So that is how we the word come in my talk as a purpose-built molecules. That means molecules are assembly that is being built or being synthesized with a purpose, with a definite function to deliver. Okay. So these are some of the recent publication from my research group. But today I will be, to match with the notion of this conference, I will be talking about these three. One in chem science, one is bioconjugate chemistry, and one is a chemical communications, and that we have published in very recent times. So this is just for the benefit of the students. We talk about the nanocapsule. The reason is nanocapsule means our ideology is to entrap that molecule, the drug molecule, inside a polymeric shell structure. So the main purpose is to have that polymeric nanocapsule, synthesize the polymeric nanocapsule in such a way it has a weak link in the periphery of this polymer backbone, so that which can be cleaved in presence of a certain stimuli. It could be light, it could be pH, it could be enzyme, it could be a intracellular species like glutathione. The strong redox, one can term glutathione as a redox stimulus, or it can be called also as a nucleophilic stimulus. So the purpose is, in presence of such stimulus, that the polymeric nanocapsule, the shell will collapse and the drug will be released. One of the major advantage of this drug entrapped in polymeric nanocapsule is if we can take this drug, the entire assembly, to the desired site, and we can rupture that polymeric periphery in presence of certain stimulus. That means we can get the site-specific drug release, and in this way, perhaps we can reduce the possibility of the biodistribution of the drug in the entire physiology of the human physiology, number one. And number two, we can get the active higher concentration of the drug in the desired site. So these are the major reasons why people are interested to trap this drug molecule, the nanostructure material. So the first, as I mentioned, that the way I have planned my talk is that stimuli responsive nanostructured material for drug release, a proof of concept. Second one is also the stimuli responsive drug release is a prodrug concept, but not on a polymeric nanocapsule. It is a simple molecule, but in presence of certain stimulus, I will try to convince you how it can be, such a methodology can be used for design of an efficient prodrug molecule. And the third one will be that it's an ideal example of a demonstration of an inorganic chemistry and the supramolecular chemistry for designing a probe molecule which can be very effective in studying the apoptosis process. Okay, the first one is the stimuli responsive nanocapsule structure. Now the drug that we have chosen to entrap is the metoflosin. Metoflosin is one of the wonder drug. It's considered as one of the wonder drug for treating leishmania. Now, what is leishmania? Leishmania in India is it is well known as a disease called Kala-Azar. It used to be very, very prevalent in early 90s to the late 90s. But since there was a very effective campaign by the government of India, and this has been significantly reduced. This Kala-Azar influence has been significantly reduced in a country like India. But still, there are 4 main states in this country. There are a number of cases they arise due to this infection called leishmaniasis or Kala-Azar or the other variant of the leishmaniasis. And it is considered one of the neglected tropical disease. And the reason is that death rate is less, but that severely limits the way the ability of the people, to live healthily in after they get infected. But so this has been termed as is one of the neglected tropical disease. It has been termed by the WHO. But this is very, very prevalent in the countries like Africa and developing countries like Africa and Africa, Asia, and America. So certain places in America where the people, the lower economic section, they are mostly the people who are exposed to this kind of infections. So, as I mentioned, there are 4 different varieties of leishmaniasis: cutaneous leishmaniasis and visceral leishmaniasis. These are 2 are the most common in a country like India, and this visceral leishmaniasis, which is the most common one, is also known as a Kala-Azar, and sometimes the CL, the cutaneous leishmaniasis, actually starts after the patient recovers from Kala-Azar. Okay. Anyway, let me come back to the point of using methotrexate. This is only recommended oral drugs for treating Kala-Azar, either cutaneous leishmaniasis or the visceral leishmaniasis. Okay. So now, as I mentioned, that we have a plan to entrap this drug molecule in an uncapsulated structure. To trap this one, basically what we have adopted is inverse mini immersion. In the next slide, I am trying to show you what is inverse mini immersion, just to make a cartoon picture. Basically, we have a hydrophilic drug molecule, relatively hydrophilic drug molecule, one has to take a 2-phase system. One is the non-aqueous phase, that relatively hexane, for example, and the aqueous phase. Aqueous phase will be less, hexane will be more. And let me come here the cartoon picture. This is one I try to convince you with the inverse mini immersion technique. And with a very high shear force, that means sonication, you can make a emulsification. You can allow the emulsification to happen, and it forms a vesicle-like structure. What it needs to form a vesicle, you need a surfactant. You need a drug which will be in the water pool, trapped inside the water pool, and the polymeric monomers will be orienting itself along the periphery of this vesicle. Okay, so with this vesicular structure, now if one add this, the other part of the polymer reaction, the monomer of the polymeric reaction, what will happen? The polymer formation will happen at the periphery of this drug. At the periphery of this vesicle, and it will eventually form a nanocapsule structure with a drug will get trapped inside this hollow pore. So this is basically that concept that we have used for synthesis of this reaction. This is exactly what I was trying to tell you. We have adopted in synthesis of this emulsion, sonication, emulsion, the drug gets trapped inside the core. Then we have added the other part of the monomer to form to go for this in the polymeric reaction. Once we allow the certain time, the polymer, the polymer formation will happen at the periphery of the vesicle, and the drug will get trapped. Once it is formed, one has to do a little bit of purification, like dialysis, so that all the small molecules, unreacted molecules, or the oligomers, smaller oligomers, will pass through this dialysis sac, and only those drug molecules that are trapped inside this molecular, this polymeric shell structure, they will be trapped inside the dialysis sac, and that is the is the purified species we'll be using for our studies. As I mentioned, if you look at this diamine functionality having a sulfur-sulfur bond, in between, which is actually weakling. Now, if we allow this reaction with this dicarbonate A and B to react, they form a polymer like this. As I mentioned, the sulfur-sulfur ring is a weakling, and it is susceptible to to get clipped by intracellular species called glutathione. You all know that in glutathione concentration in human physiology is quite high. In certain cases, certain health disorder, this goes as high as a millimolar concentration. So this is basically the concept. We try to synthesize a polymeric backbone with a sulfur-sulfur bond inside, which is a weakling, which can be cleaned with a stimulus called chemical stimulus like glutathione. And when it cleaves, it will be fragmented into several small components, and it will be able to release the drug from the entrapped drug outside. So this is basically the concept that we are trying to use. Now, after telling this one, now it is time for me to convince you that actually we could synthesize the polymeric nanocapsule. You can see there's a typical, this is one of this the 10 structure, about 130 nanometer. This is a dynamic light scattering. You can see that average, the distribution is about 130, 140 nanometer. And this is the same structure. This is a solid state NMR, and this is a IR structure. IR spectra. This is only to convince you that the reaction that we have proposed is actually happening, and it could eventually end up with a polymeric nanocapsule-like structure. But this doesn't talk about the entrapment of the drug molecule inside that nanocapsule. Now here is the one to convince you that actually the drug is inside. So what we did, we took that nanocapsule in a small there is a two parallel reaction we did. This is a control reagent we also synthesize. This is a polymeric nanocapsule we synthesize where there is no sulfur-sulfur link in between. There is no weakling. So this, at least this polymeric nanocapsule will be unreactive towards a species like glutathione. While our main interest is that this nanocapsule will be susceptible to a nucleophilic attack or a redox reaction of the sulfur-sulfur bond cleavage and the drug release. So that exactly we did. We did two parallel reaction. One reaction we have exposed it to glutathione concentration, and so in both the cases we have exposed a certain amount of glutathione concentration. Okay, as you can see, for this molecule there is no drug release. Okay. There is no release of meltophosin, but here there is a slow and sustained release of meltophosin over a period of 6 hours. Now the question is, how we studied the meltophosin release? We studied it by the HPLC. Okay, so we first we studied that that pure meltophosin. Then we have used this nanocapsule exposed to the glutathione concentration. With after certain certain intervals, we kept on measuring the meltophosin concentration build up in the reaction. You can see that it took about 6 hours to get that to achieve the saturation. So if it really works, so in one go we are not only able to prove that it is possible to trap the drug inside this polymeric nanocapsule, which can be cleaved and released in presence of a nucleophile or a redox species like glutathione. And secondly, we can also achieve a slow and sustained drug release over a period of time. Not all the drug will be released at a time. So with this now, it is time to show you whether that entrapment of the drug inside this nanocapsule has improved its efficacy. We took the nanocapsule where there is no drug inside, just to convince you that this nanocapsule is non-toxic to the human cell line. We took the macrophage raw 264.7 cells and to check that how the infection affects these cell lines. We have certain portion of that cell we have exposed it to an infection called Leishmanian Donovani, which is actually induced at the leishmanosis. Now, the first one, there is no it was not exposed to the infection. You took that nanocapsule at a different concentration, and you can see that cell viability doesn't change, which is to establish that the nanocapsule itself is unreactive or has no detrimental influence on human physiological or the cell lines. Okay. Now we have exposed the cell lines to the Leishmanian Donovani, that infection, Leishmanian, the leishmanosis, and you can see the cell viability goes down significantly. Now, when you treat this one with the meltofosine, you can see that the extent of the infection goes down. That means meltofosine as a drug is working to cure from the Leishmanian Donovani infection. Okay, and it's almost, you need to bring it down to almost 35% of this initial infection. One need to use a 10 microgram per ml of this pure meltofosine. And let me tell you, meltofosine is a kind of drug which has a, that is one of the only used drug for the oral administration for the patient who suffer from leishmanosis. But this has a huge side effect. So using a higher concentration of the meltofosine is not desired, but we have no option at this moment. So, but if we use this meltofosine entrapped in the nanocapsule, NC for nanocapsule, you can see the extent of cell leishmanosis, the infection goes down to almost to 10% with only 100 nanogram per ml of this drug, effective drug concentration. That means the effectiveness has significantly improved when the drug is entrapped inside this nanocapsule. So our purpose is actually being served. Looks like this, our purpose is being served. Now this is more about it's a macroscopic scenario of this efficacy of this nanocapsule is a nanocapsule entrapped drug. So to convince you more with that actually what happened with this drug, let me show you. This is a macrophage cell, as I mentioned, which is infected with the Leishmanian Donovani, and it is stained. Leishmanian Donovani is the infection which can be stained with a fluorescent dye called CFSE dye, and when it stains that dye, you can see that the green fluorescence. Okay, so this is a clear proof of the cell that is infected with Leishmanian Donovani. So this is one of the extreme where we have used 100 nanogram of pure meltofosine per ml. You can see that the extent of infection has gone down, but there is still a sizable amount of infection that remains. After a period of 2 hours. Now these are the images which certainly will convince you that the drug is much more effective when it is trapped inside this nanocapsule structure. You can see the 8 nanogram, 20 nanogram, 40 nanogram and 100 nanogram of this drug, meltofosine, entrapped inside this nanocapsule structure. You can see that it has almost decreased to a minimum infection. So this is to convince you at the cellular level that this drug entrapped inside that nanocapsule is much more effective as compared to the pure drug. Now, if you look at this Leishmanian Donovani infection, there are a few markers which gets downregulated during the process of infection. Some of them are RAF5, RAF7, and RAF9. There are other markers also, but what we are trying to tell you, these are the markers which gets downregulated during the infection process. So, and the beauty of these things, these are the markers which can be visualized in presence of certain dye. That is why we are trying to study this process of the efficacy of this nanocapsule drug by studying the marker, appearance of this marker, which gets downregulated when it is fully infected. So you can see this is a control. You can see this RAF7 is downregulated here. Okay, this is a concentration has gone down. This is a control. You can see that RAF7. This when it is not infected. When it is infected, the RAF7 marker has gone down significantly. When we have treated with meltofosine 8 microgram, you can see it is started coming back. That means the downregulation of somehow being slowed down by this drug. The drug has started working as well. Now, here is a pure meltophosin, and you can see this is a meltophosin entrapped in the nanocapsule. And with that 20 nanograms, a much lower concentration, you can see there is a significant upregulation of this. And please excuse me, there is a difference in the intensity. It cannot be more than this, and you can understand these images were recorded at a different time, and so they come with a different intensity. And we prefer not to play with the original intensity plot. So it looks like, but this is to convince you that infection level is actually being put a halt by this much more effectively by this meltophosin entrapped in the nanocapsule. And this is one with the 40 nanogram. So these all are we have been trying to convince you that these markers, down regulation is put on hold by this much more effective by this drug when it's trapped inside this nanocapsule. Now this is other marker that I mentioned, that RAV5, catechin B, RAV9. You can see these are all down regulation, and they almost disappear when they are infected, and in presence of this nanocapsule. When we have used, they were able to hold this, the down regulation much more effectively as compared to the pure meltophosin. So these are all to convince you the drug trapped inside this nanocapsule are much more effective in treating Leishmanian Donaghani infection rather than a pure drug molecule. So this work was done in collaboration with Sumit. Sumit was my associate at CSM CRI. And Dr. Krishna Das Shaha, she is the biology basically was done in collaboration with Dr. Das Shaha. He is from CSR IICD, Kolkata. So here I will move to my second topic of my lecture. Here we'll talk about the design of a prodrug for improving the drug efficacy, decreasing the systematic cellular toxicity of this drug, and the site-specific drug release. That means better efficacy. With one of the major aims is the sustained drug release. So with this aim, we made a molecule. This is a product structure that we are trying to, I will be discussing in the next slide. So this is a martacin. Martacin is a natural product and is considered to be one of the wonder drug. It was thought to be one of the wonder drug for treating cancer. So, but the martacin has a very high systematic toxicity. It lacks a sensible therapeutic window due to the high systematic toxicity, and phase 2 clinical trial proved disappointing. And to counter this one, basically this is just for the student, what is therapeutic window is basically the concentration over which the drug can be utilized for treatment. So this is a subtherapeutic. Below this concentration, drug is not effective. Above this drug concentration, drug become a toxic, and so this is the and this is the time duration for which drug remains active. So this is called a therapeutic window for this. But unfortunately, therapeutic window for this martacin was very, very thin, and it has a very high systematic toxicity. So to get around this problem, so there is a huge effort from the different research group globally to combine this martacin with an antibody, with a select antibody, which will go and bind to some antigen which upregulates in a cancer cell. So basically, it is the idea is to this martacin and take an antibody, conjugate them, and take it directly to the antigen on a cancer cell where the counter antigen gets upregulated. It binds there, internalized, get the drug release. So this is a lot of efforts are there, and you can see some of the prominent journals, prominent reports are in this direction. So we thought that can we have a different approach of a product? So just to tell you, martacin, it is also known that martacin actually is a microtubule inhibitor, and it works much better. And as it is a microtubule inhibitor, it works much better if the drug can be released in mitochondria. Apart from that, one of the very recent reports also says that we normally think that carbon monoxide is not is detrimental for human health, but carbon monoxide is a detrimental to human health beyond, when it exceeds the threshold value. Below the threshold value, it is actually, now the recent report shows that it is actually beneficial for human health. And actually, it acts as an immunoprotective and homeostatic molecule, and mitochondria have been proposed to be the major site of action for carbon monoxide. So our interest was, if we can release this martensine along with carbon monoxide in the mitochondria. With this, with this ideology, we synthesize this molecule. This is will be abbreviated as a pro-DC and pro-drug. Basically, you can see this is a martensine. It has been linked to this body-by moiety, which is a fluorescent marker, through this thioester linkage. Okay, the reason for thioester I will explain in my next slide, and it is also substituted with the triphenylphosphoniamide. The reason for triphenylphosphoniamide is explained here. We all know that mitochondria has a negative membrane potential, and the species which has a cationic charge, that has there's a high possibility that this the molecule with the cationic charge will pass through this membrane and will be able to take the entire product to the mitochondria. So that is why we deliberately kept this triphenylphosphoniamide in this molecule. Number one. Number two, I'm trying to explain you the design aspect in this molecule. Now, this part, the thioester linkage gets clipped when it is exposed to the 400 nanometer laser source. It is also reported in the literature. We just adopted that particular syntone and integrated this in our design aspect. So if we can irradiate this one with the 400 nanometer laser light, we can get the martensine release, and not only martensine release, the carbon monoxide also can get released. Now, as this entire molecule, this product goes to the mitochondria, due to this triphenylphosphoniamide, on radiation, we expect this both martensine and carbon monoxide to get released in the mitochondria. This is the entire design aspect of this molecule. So what we did, first to show you that our ideology is working. Let me tell you, before that, let me tell you, this body-by moiety, if you, those who works with the body-by moiety, they know that ester function here, when it exists, the body it quenches that luminescence of the body-by moiety. So, body-by moiety, here, there is a fluorescent marker, but it is in the fluorescent off state when it is in that product state. But when it is getting released, it is no more ester. This shows a fluorescence on response. So this is exactly what we have done. We have taken this product in a fluorescent tube and irradiated with the 400 nanometer irradiation. As you can see, this is over a period of time, there is a typical characteristic luminescence from this and the fluorescent marker has come up. That means it shows that this molecule is actually releasing this fluorescent marker on irradiation at 400 nanometer laser source. And if there is no irradiation in the dark, there is no release of this fluorescent marker. So our ideology is to study the drug release simply by looking at the fluorescence of this fluorescent marker. That is the reason why we integrated or kept that fluorescent marker in this molecular structure. Now, this is the part to convince you, apart from fluorescence, this is a simple HPLC studies. We could after irradiation, we could detect each and every component of this molecule, martensine, the other two components. Okay, only component which cannot be established or cannot be shown with the HPLC was the carbon monoxide. So that what we have done an indirect proof of this reaction. We all know that phosphomolybdic acid, in presence of a certain reductant, it forms a mixed valence complex. And in the mixed valence complex, it shows a very strong blue color. So that exactly we have done. We have taken the solution. We have soaked this filter paper with the phosphomolybdic acid, and this is our product. Now it was irradiated inside the bottle with a 400 nanometer light, and as you can see, the carbon monoxide was generated, and it could react with this phosphomolybdic acid soaked inside this filter paper and shows this blue color. We have used this actually the reaction, the concept we took from the analytical chemistry. There's a report from somebody else. Okay. Now now we have been able to convince you that carbon monoxide is getting released, that martensine is getting released, and on irradiation with 400 nanometer laser light. Now this is a time to convince you is actually goes to the mitochondria. For the reason we kept the diphenylphosphonium there. So now you can see this is a before irradiation, 10 minutes irradiation, 30 minutes irradiation, and 60 minutes irradiation. You can see the buildup of this fluorescent marker of this body by moiety at the mitochondria. Now this is again to convince you, this is a mitotracker rate, this is a commercial mitotracker rate, and this is our reagent. You can see there's a Pearson coefficient is very high. This is enough. I think this is enough to convince you. So about the design aspect of this molecule, which on irradiation will release martensine at the mitochondria, and this release study can be studied simply by looking at the fluorescence that comes out of this fluorescent marker when it is in the fluorescent on state. Now, so we have been able to convince you with the design of this product, which will disintegrate in presence of a irradiation. Now, let us check whether it is really effective, that the product is as compared to the pure drug, or it is less effective. Now, this is a control molecule that we are using, but there is no triphenylphosphonium. This is actually the precursor of before synthesizing triphenylphosphonium. Okay, so this one we have used, as you can see, as there is no cation, there will be biodistribution will be everywhere, the entire cell line, and here it is simply localized on mitochondria. As you can see, the efficacy of this drug when it is in the dark, cell viability in the dark, cell viability is a program we see in the dark. You can the cell viability is almost it is non-toxic to the cell line. That means by conjugating it with this through this highest linkage, we have been able to reduce the systematic toxicity of this drug called martensine. The reason is martensine is known to be toxic due to this free thiol function. As we have blocked it, so we could reduce its toxicity. Now is the time to show you this is more effective. Not only is it more effective than martensine, and the pure martensine, it is even more effective than this control reagent. As you can see, this is the drug with light. The toxicity of this drug is much better in killing the cell than this control reagent. So altogether, now we have been able to convince you by conjugating martensine to this through a thyroster linkage to a mitochondria specific component, we have been able to improve the efficacy of the drug, not only in terms of the effectiveness, but also in terms of its reducing its systematic toxicity. So, as I mentioned, this is light induced seizure of this thyroster linkage, release of the martensine in the mitochondria, release of carbon monoxide in the mitochondria. But one question it still remain unanswered is that what would be the effect if carbon monoxide not released there? That answer we don't have. So perhaps it is a composite influence of this martensine as well as the carbon monoxide release at mitochondria. And the entire process and the release process in mitochondria we could visualize due to the presence of this that body pipe, fluorescent marker body pipe. And this work, as you can understand, there is quite a bit of organic synthesis involved. And obviously, I'm not that good organic synthetic chemist. So I took help from Dr. Santosh Mashke. He is a scientist at National Chemical Laboratory in Pune, and of course, this was in collaboration with Sunil, my associate at CSMCRI. Now I have come to the last part of my talk. Here is a demonstration of the inorganic chemistry, supramolecular chemistry for designing a molecule for which can be effectively utilized for studying the cell apoptosis. So, if you look at that human lipid layer structure in the human cell line, there is a asymmetric distribution of the certain markers. It's called phosphodietyl and phosphodietyl. Phosphodietyl is basically remains in the outer leaflet of a human, the bilipid structure. while phosphodiesyl serine, it remains in the inner leaflet of the human cell line, so in a bilipid structure in the human cell line. To convince you better, I think I have copied this one from a YouTube video, and I have referred this reference here. You can see this is typically there's a bilipid layer structure. The inside, the green one is a phosphodiesyl serine, is a negatively charged, and the outer leaflet doesn't have any. For a healthy cell line with the bilipid structure, bilipid layer, there is absolutely no distribution or no presence of PS or phosphodiesyl serine in the outer leaflet. So what happened when a cell undergoes apoptosis, phosphodiesyl serine moves from the inner leaflet to the outer leaflet. And this is one of the way to understand the cell apoptosis has happened. If we can understand the distribution of the concentration of the phosphodiesyl serine in the outer leaflet of a bilipid structure. So this is conventionally one of the prominent way of studying the cell apoptosis, even in the diagnostic lab. This is again a cartoon. So what the diagnostic lab people they do, this is a cartoon, this is a phosphodiesyl choline and phosphodiesyl serine, the inner leaflet. Cell apoptosis happens, phosphodiesyl serine moves from the inner leaflet to the outer leaflet. The moment it moves to the outer leaflet, this is a conventional methodology. There is a dye used. The dye is used to map this phosphodiesyl serine in the outer leaflet in annexation 5. Annexation 5, what it does, it in presence of calcium, and this test has to be done with a high concentration of calcium. Calcium goes and binds to this anionic phosphodiesyl serine. The moment it binds, the phosphodiesyl annexin V comes and binds itself to the calcium to show a fluorescence on response. And simply by looking at the fluorescence on, that phosphodiesyl distribution of the phosphodiesyl serine in the outer leaflet is being studied conventionally, and that has been one of the most popular way of studying the cell apoptosis in any diagnostic lab. Okay. Now there are actually 4 different methodology. There is a monitoring the caspase activation, monitoring the DNA fragmentation, or monitoring the activity of the mitochondria, and the 4th one is monitoring changes in the lipid organization and the outer membrane leaflet. That is exactly what I am trying to do, and this is the most popular method for, more prominent method for studying the cell apoptosis process. But there is an issue. This binding with this calcium with the phosphodiesyl serine is typically a very slow process, and it takes, the incubation time is quite high. It is in hours, basically 3 to 4 hours incubation minimum time is required for that, for calcium to go and bind to the phosphodiesyl serine, and then it will annexin V will come and bind to this calcium to show this fluorescence on response. So this to get away with this, people are working. There is a lot of interest in synthesizing molecule that can study that distribution of the phosphodiesyl serine in the outer leaflet or the cell apoptosis process in a much faster way. So for this, what we have done, we have synthesized a molecule like this. This is a diazine complex. This is a diazine complex. This is supposed to do the job what calcium is doing. And this is the other part of the molecule, interesting part of the molecule. It is having a body pipe. Those who are familiar with the body pipe, they know that having a methyl group here and not having a methyl group here, that makes a lot of difference. As there is no methyl group here, this is an unsubstituted body pipe. It acts as a molecular rotor. The reason is this is a free carbon-carbon bond rotation. Even at this kinetic energy this rotational energy barrier is very low, and there is a free rotation about this carbon-carbon bond. As this carbon-carbon bond rotation happens, that actually deactivates the fluorescence, that activated state, the excited state of the body pipe. That means when you excite an electron from the body pipe molecule S0 state to the S1 state, due to the presence of so many rotational levels, it allows the deactivation from the excited state to the ground state simply through some rotational energy levels and vibrational energy levels, and this is a non-radiative pathway. So that molecules becomes non-fluorescent. So this molecule has a 2 component. One is a cationic molecule, and we hope that this will the dicing center will bind to that phosphodiesyl negatively charged phosphodiesyl serine, and we bring this rotor part, which is also hydrophobic, very close to the lipid layer structure. The moment it comes to the lipid layer structure, it will embed itself in the lipid layer, and that will rigidize the rotation, and this part of the molecule will become frozen. This is a design concept that we have used for this reaction. With this, let's see what is molecule actually does. This molecule was taken in a solvent which has a very little viscosity. Then we kept on slowly increasing the viscosity of the medium, and you can see there is a buildup of the typical characteristic body bifluorescence. That means our ideology that this molecule acts as a molecular rotor part is actually working. Now it is the time to convince you the other part of the molecule. So as I said, that the dicing cationic part is supposed to bind to the electron rich, the phosphodiesyl serine part. Okay. So what we did all the other major component that exist in the lipid bilayer structure, the ESA, cholesterol, all these the different components, major components we took, and we could see there is a buildup of fluorescence only in presence of phosphodiesyl serine. Okay. So and as we go on increasing the phosphodiesyl serine concentration, there is a buildup of emission, which clearly shows that our reagent, that the dicing compound, goes and has some selectivity towards phosphodiesyl serine. Now we have been able to demonstrate the efficacy of both the components, the cation part, which is expected to bind the phosphodiesyl serine, and the rotor part, which is expected which will be frozen if we can restrict its carbon-carbon bond rotation in presence of, if we can rigidize its carbon-carbon bond rotation. Okay, so we took a HeLa cell and we induced the cell apoptosis using a drug called streptosporin. It is well documented in the literature that when the cell lines, healthy cell lines will be exposed to the drug called streptosporin, it will induce a cell apoptosis. And this is the middle one, the red one. As you can see, this is an image with a commercial reagent called annexin 5, and this is an image, and the apoptosis process was imaged with using our body pi molecule. Only the process here, the incubation time is in hours, not in 1-2. It's almost 4 hours. I think we got this result, and this is just a few minutes. Within 3 minutes, you can get this image. And this is a overlay. As you can see, there is a very good extent of overlap of the emissions. Okay. So with this, we have been able to convince you with this design of the molecule. This dicing cationic part was able to bind itself to that phosphodiesyl serine on the outer leaflet, which was induced by the cell apoptosis, and in a process, this molecular rotor part was embedding itself into the lipid structure for the fluorescence on response, and this fluorescence on response was actually was used or studied to understand the cell apoptosis process. I think with this, I have come to the end of my presentation. Basically, if I summarize my presentation today, the stimuli responsive nanostructured material and drug release, a proof of concept, the nanocapsule structure. The second one was not a nanocapsule, is a program, is a stimulus. We have used the light, and is a site-specific or organelle-specific drug release. We are trying to convince you that with that ideology, we could reduce its systematic toxicity as well as the drug efficacy. And the third one is a demonstration of the inorganic chemistry, supramolecular chemistry, for designing a molecular force for studying cell apoptosis process. And the work that I have discussed here is basically the contribution from Anil, Harvinder was a GNU student. Incidentally, and Rajeshwari, Shumit, and Karishma, they are contributed. Karishma also has spent some time at GNU, and as you know that I spent most of my career time in my professional time in CSM Sarai, then was in NCL for 3 years, then I moved back to CSM Sarai at present, and I at Kolkata. So I'm grateful to all these organizations who has helped me in carrying out my research and allowing me to study, discuss things that I have discussed. And I have mentioned that some of the work that I have mentioned, the images were done by Srijesh. He is now because he was in Oxford as a postdoc. Now he got a faculty at Derby. Now my collaborators, I mentioned that Sumit, I mentioned repeatedly Jim Thomas. With Srijesh, he has done that imaging studies with me. Santosh, some help with this organic synthesis. Andre, that the cell apoptosis work, the biology was done with him. And Krishna Sharma, as I mentioned, her contribution in the elastomeric work. And I have been blessed during my entire career with the funding from different funding agencies. Without their help, I would not been able to do the research that I have done during the years. And thanks again for giving me the opportunity to be here. And happy birthday to Manoj. And I wish him a very, very active years ahead. It's not the end. I think it's a new beginning for him. And thanks again for having me with you in this special occasion. And thanks for your attention. And I will be happy to address your questions.
For his great lecture, describing 3 of his projects, and he just summed it up into 3 projects in one lecture. That's great, and thank you very much for being with us. Hello, Professor Das, can you hear me? Yeah. Okay, great. Okay, so. Well, I would say Dr. Manoj is the youngest senior citizen. So he's young at 60, And yeah, thank you. And they are displaying something on the screen which will be sent to you as a memento for your participation in this program. Yeah, welcome. Welcome. Yeah, great, sir. Thank you very much. All right, then I move on to the second speaker of this session. Second speaker of this session is Jaya Murugan Govindaswamy. Dr. Jaya Murugan Govindaswamy is associate professor, and he comes from the Energy and Environment Unit of Institute of Nanoscience and Technology, which is in Mohali. He has been working there as a senior scientist since 2015. Regarding his earlier education, he has his PhD from Indian Institute of Science, Bangalore, and then he was at University of Cambridge, and then ETH Zurich, Switzerland for his postdoctoral studies. As far as his research interests are concerned, he's interested in functional organic nanomaterials for a variety of applications ranging from catalysis to drug delivery. And he has published a number of papers in high-ranked journals, and he's also reviewed a number of journals as well. Important thing is that he has been bestowed with Ramanuja Fellowship and earlier Career Research Awards, and he's also got some research grants from industry. So he's an active researcher. Let's hear to him. So welcome, Dr. Govindaswamy. So floor is handed over to you.
ਵਧੀਆ ਤੂੰ ਸੁਣਾ। ਮੈਂ ਯੂਨੀਵਰਸਿਟੀ ਨਹੀਂ ਕੰਮ ਹੈ। ਮੈਨੂੰ ਪਤਾ ਨਹੀਂ ਪਾਪਾ ਨੂੰ ਫੋਨ ਕਰ ਰਿਹਾ, ਪਾਪਾ ਹੈਗਾ ਸਿਮਾ ਜਿੰਦੇ ਹੀ ਉਹ ਤਾਂ ਇਹਨਾਂ ਨੂੰ ਪੁੱਛ, ਨਹੀਂ ਤਾਂ ਬੰਦੇ ਨੂੰ ਫੋਨ ਕਰਕੇ ਪੁੱਛਣਗੇ ਪਾਪਾ। ਇੱਥੇ ਫੇਸ ਟੂ ਫੇਸ ਸਿਮ ਚਾਲੂ ਨਹੀਂ ਜ਼ਰੂਰੀ ਨਹੀਂ ਯਾਰ। ਹਾਂ ਠੀਕ। नेट लो जी फिर बैठना अगली सीट पे इधर मैं बैठना अगली
Today I will be presenting the talk which is entitled Innovating Self-Assembled Nanomaterials and Supramolecular Chemistry based on nanotechnology. So, and I'm also feeling really great to be here at this conference because this is being celebrated on the occasion of Prof. Manoj Kumar's birthday. I'm really indeed pleased to be here. So before starting with presentation, I'd like to give a very common acknowledgement. Without these people, I would not be here standing here and presenting the work I'm going to present. So these are my group PhD students. Out of 9 students, 3 students are completed, and these are the postdocs work with me. And today's presentation mainly I will be focusing on Dr. Arifah and Shaifali Shatanga and one Dr. Gauri Jitendran. She is also present here. So these 3 persons who are kind of presenting today. And of course, I do have collaboration with a number of people who are expert in other areas like cancer therapy, biological background, and computational background and electrophysics background. So I also like to thank the funding agency for the attendance and Axel from SARP and TPT. So this is for the people attending online. So I come from Chandigarh, which is also belongs to the state of Punjab, which is very close, 232 kilometers. So this is our campus, Institute of Nanoscience and Technology, which is just right adjacent to Aizen Mogali. We share border here. This land is Aizen Mogali, and this is the original concept, and this is actual main building. This is the building. So this has come really nice. One of the beautiful campus, small campus, but beautiful and state of the art facilities, including students come hostel, faculty quarters, guest house, director bungalow, again other activities. So it's a nice place to do science, interdisciplinary science especially, because nanoscience belongs to all disciplines like chemistry, physics, biology. So we do have expertise from all these 3 people, and they are sitting in the same roof. So we do collaborate with each other and get the work done. So our students register in Aizen Mogali for PhD graduation, and we do have only a PhD program apart from some internship program. So in my laboratory I call it as functional organic nanomaterials. So I'm basically from organic synthetic organic chemist. I'm trained in different disciplines. So now as an additional area, I entered into nanoscience and technology. And I'm sure, at the end of the talk, I believe that I'll be able to convince you that, I do kind of work on nanoscience and technology. So the application we are basically focused on 3 different areas: energy, environment, and health. So these students are working in this area. So basically, my research area belongs to 3 different categories, 3 different areas. Sorry, I forgot to explain. One is customized polymeric nanoformulation. another one is nanocatalysis, and third one is push to force. The customer cinema polymer, I do have to thank INST because we do have facility from chemistry, physics, biology. Because they are under one roof, we can able to work in interdisciplinary. We were able to show that we can able to deliver drug to the cancer cell and especially cycle targeting of cancer cell without affecting other cell. And then we do publish basis application where we make hybrid nanoparticle and organic nanoparticle. The studies of hybrid and organic nanoparticle have been extensively studied by other people. So what we here addressed is that, well, among the two techniques, which technique is better? So there's a systematic study required. Also, in the polymer, biocompatible biopolymers, which polymer is best in terms of cellular drug uptake and sustained release. So we found the starch was the best biopolymer, and organic nanopolymer itself can be able to deliver better. So that was recently published in nanotechnology. And then another question again we asked was, you know, we all studied several drug polymers. If you want to make a drug polymer, take a drug monomer, take some non-drug unit, and then polymerize it. People make many drug polymer. So we asked the question again: what if you make 100% drug polymer? Obviously, the non-drug part in the drug polymer is not useful. Then the amount of drug you will take is going to increase. So if you take 100% drug polymer, then the amount of drug you will take may be reduced. And indeed, we were able to demonstrate that by self-polymerizing cyproprocessing antibiotic, which is widely used antibiotic, without any monomer, just self-condensation by heating or by tinosyl chloride acid chloride conversion. We were able to polymerize a new type of polymeric biocide, which without any spacer in it. Also, as a control study, we made different spacer in it with a smaller chain and longer chain, and we were able to demonstrate that the space without spacer length, that polymer showed highest antibacterial activity, and including very good coating application because of the viscosity of the applied polymer. So we were able to show that increased activity for the polymer without spacers. And another example where we worked on supramolecular chemistry based nanocarrier. So what this everyone knows, any students, if you take an ambivalent polymer, put it in water, it forms directly attached by a covalent interaction, whereas here it is supramolecular interaction. So we were able to combine covalent interaction and supramolecular interaction to obtain. And so what happens when you mix with this? We did not observe any micelle. The ambivalent polymer could not tend to aggregate themselves. That is called narcissistic self-sorting. We say narcissistic self-sorting means it aggregates on its own. Whereas social self-sorting means these two interact with each other to form interconnected nanocarrier structure, wherein the hydrophobic part is slightly denser than the hydrophobic part. So that means that we were able to achieve higher drug loading because of the higher hydrophobic effect. Also the sustained release because of the again higher interaction. So this work was recently communicated. If you time permits, I will present that work in detail. Otherwise, I will present only one work. So this is another area apart from polymeric formulation, nanocatalysis. So here I am really thankful to Professor Manoj Kumar. When I started my career in 2016, Dr. Shanjit Kaur also joined with me as a LPTF candidate. She was a student of Professor Manoj Kumar, and she really very bright student, exceptional talent. I just gave her idea that let's do this, and she implemented it. The idea was that we work on both fundamental science development as well as application. So one of the application fundamental science I was looking at is laser coupling. In laser coupling, it's nothing but a dial CC bond formed between two alkynes. When you treat any copper catalyst with a TMD organic base or something, then CC bond formation occurs between two alkynes. Basically, you get a dialkynes. So if you mix two different alkynes, Obviously, there is possibility for homo coupling as well as hetero coupling. There are 3 products are possible. 2 homo products, 1 hetero products. If you can be able to achieve 100% hetero product, then that means it is a very good orthogonal reaction, can be used for bioconjugation, as similar to copper, the famous copper copper reaction, clean chemistry. But though this laser coupling is 150 years old, this is not that famous because of this reason that it is not highly selective. So people normally change the catalyst just by replacing chemical reactivity of the catalyst or the substrate, they achieve selectivity, and that is not achieved more than 70% so far. So one of the as a proof of concept, we decided that since if you look at these 3 products, we have 3 different polarities because you have 2 hydroxyl groups here. Here you have 2 phenyl. Here you have 1 hydroxyl. So that means the number of hydrogen bonding interaction is different in this product. So by playing the copper oxide nanoparticle action catalyst and then the backbone, the polymer backbone, you vary the number of amine nitrogen content in it. For example, in this case we made trisamine. If you take another catalyst we made with ethylene diamine, another catalyst as a control, no amines, and then see whether selectivity can be changed. And indeed we were able to observe that this catalyst was more suitable for forming heterocoupling product with very good selectivity of 80%. And we were also able to show in detail with the control studies that's including computational studies that the backbone interaction with the substrate is the reason for the selectivity. This work was published in Chemicom 2020. And then the same catalyst we also applied for the famous click chemistry reaction to make triazole products, and it works flawlessly in just in water. The most highest activity was observed in only water. And then as an application, we were also looking at any industrial development application we can show. So there is a drug called grofenamide drug, which is a triazole product. It is a difluorobenzyl azide and then methyl propionate alkyne. You react these two, you get the triazole product. And this, so it is a 3-step synthesis, out of which the click chemistry step is the challenging one because of the regioisomer product. 1,4 regioisomer is the drug molecule, 1,4 is not a drug molecule. But the conventional catalyst, copper, ascorbic acid copper catalyst, are not effective enough, and the temperature, solvent, are organic. So here, with using water as a solvent, at room temperature, only 1/4 selectivity, 100% we could be able to see from H+C, and we could be able to do it in a large scale synthesis also. In one reaction, 10 gram scale we have done at laboratory scale. It works, so we have made a patent also on this, and we published this work in Asian Journal of Publication. So, and then as I said, now the recent activity in research community is the addressing energy crisis. So sustainable energy project is again very active. In that line, so utilization of biomass is one of the promising strategy to achieve sustainable energy actually. Even in fact, it's superior than solar energy. So that means we have enough biomass in the earth that can be used to convert either fine chemical or value addition to get to meet the energy related issues. So in that sense, carbon dot recently is another one of the allotrope. In addition to fullerene, carbon nanotube, graphene, now carbon dot is another recent addition into that. Carbon dot is nothing but carbon allotrope, amorphous anti-acidic structure within the size of 5 to 10 nanometer. That carbon dot one can synthesize from various precursors, bioprecursors like citric acid or various fine chemicals. So in this case, for example, we choose citric acid, carboxylic acid functionalized carbon dot, and then carbon dot used in censoring catalysis in various studies have been performed. What again we ask the question: what if you polymerize the carbon dot as a polymeric monomer unit? Can we have a platform which can support palladium nanoparticle in order to utilize the synergistic effect between carbon dot semiconducting nature as well as the palladium metal activity. So indeed, you can see this is the TM image. The homogeneous palladium nanoparticle was coated on the polymer, carbon dot polymer, and we were able to demonstrate that this catalyst can generate rhodamine B dye in just for 5 minutes under atmospheric without any light in dark. So we were also done systematic mechanistic study to prove that single oxygen generation like supramolecular ion is the reason for this reaction. And then this one carbon dot work, and then another carbon dot work again to synthesize cellulose obtained from lignocellulose from bio-based product is a major abundant material in the world. So again, the conversion of cellulose to glucose, from glucose to fine chemical, such as HMF, hydroxymethylfurfural or linoleic acid is one of the hot topic. So we also were interested to demonstrate whether can improve this conversion. So the idea was that for this step, conversion from glucose to HMF or linoleic acid, typically mineral acids are used, or highly strong acid like sulfuric acid are used. One example recently was reported that we take graphene and do sulfuric acid treatment, get sulfuric acid oxide graphene, and that was used for this one. So we were thinking why to use concentrated acid that is not right industrially viable. Can we take benchtop commercially available cheap paraffinic sulfuric acid and do hydrothermal method just in 180 degrees Celsius in water? We get the carbon dot, which is concentrated sulfuric acid. Then let's try that reaction. As indeed it works. Conversion of glucose to HMO with very high selectivity, 80%. Also the esterification of linoleic acid with ethanol, ethyl dominated in 90%. These two are considered as biofuels. Now this nanocatalysis, I'm just showing what are the type of work we are doing. But in detail today, I'd like to emphasize on this one, that is supramolecular chemistry based approach to develop fluorescent non-planar push-pull for energy, remote and health applications. So when I say non-planar push-pull I did not mean that typically you take benzene, attach a nitro and amine group, it's a donor acceptor. That's a planar push-pull. Typically we prefer non-planar because when you have planar chromophore, they tend to aggregate. Because of aggregation, they are not insoluble in the solvents, or the solubility of the smoke temperature also increases. That is not good for making organic application. So if you have a non-planar push-pull chromophore, then they don't tend to aggregate, hence they are very good soluble and sublimation temperature also low. That's one thing. And the other thing, by engineering the molecular structure by synthesis, like putting varying the donor and acceptor groups, number of donor and acceptor groups, strength of donor and acceptor group, we can be able to tune the photophysical property remarkably. So by combining non-planar as well as the chemical engineering, we could be able to demonstrate that we can come up with a candidate which is very promising for organic electronic devices or sensing type of application. So that's the reaction I'm talking about is this reaction 2+2 cyclation reaction. So this is the alkyne which is attached with the atom donating group. Typically atom donating groups are metal halides or ferrozine or aniline, azulene, thiophene, etc. And the olefin double bond attached with the cyanide group. In organic chemistry, the electron withdrawing function groups are limited, and among the electron withdrawing groups, cyanide is the strongest one. Of course, nitro too, but nitro is typically not used for various reasons. So the strongest next available group is cyano. And if you have one cyano, it's fine, but you have two cyano in one double bond, that means it's the maximum strong electron withdrawing group one can reach. And then here you have 3, 4 also you can have. So that means tetracycline is the strongest acceptor. And then you treat this with this, and it undergoes 2+2 cyclation thermally, not photochemically, because of the its non-concentrated mechanism. And then upon retroelectrization, you obtain tetracycline system. Here the single bond, you have to notice the theta is 36 to 86 degree. That means it's a non-planar. They are like this. The two double bonds are like this, not like this. So why that is interesting? Because that is two-state by system, and that means, however, the donor and acceptor is directly pi conjugated. That is, these two, the donor and acceptor is planar, whereas there are two of this. Those two are non-planar. Because of this planar pi conjugation, they are highly charge transfer. Intramolecular charge transfer band is there. That's why they are highly colorful. and also because of the donor and acceptor, they are reversibly relaxed behavior ratio, reduction loss ratio. So the mechanism goes like this, stepwise mechanism. So this was published in 1981. After that, people have synthesized many different, explored different donors and acceptor in the system. For example, acceptor can be tetrasynophenotype as well, instead of dicyclovir. One of the curiosity-driven work we have conducted was mostly they are tetrasynophene or TCNQ as acceptor. What if we have a tetrasynophene oxide which doesn't have any double bond? That means we cannot have no process attraction. But then still, if you treat with this, will you get TCBD? That's the question. TCBD means tetrasynophenotype. So we ask this question because when the lone pair is there, the lone pair can migrate and this alkane can attack here to generate dipole here, and then again the dipole cyclation will lead to 5-member ring, and then again this lone pair migration, ring opening happens, and that oxygen will attack another molecule of tetrasynophene oxide, and then elimination of this oxytocin compound gives it as a TCBD moiety. So this mechanism was proved by IR and ICMS that this intermediate was forming through this pathway, but not this pathway. This was published in Chemistry recently. This is out of curiosity, but this away from the focus, that is, can we develop fluorescent non-planar push pull? Why fluorescent? Why fluorescent? Because there are systematically from last since 1984, 40 years, there are so many different types of TCP have been synthesized for various organic applications, as you can see. But if you look at closely, none of them show emission property. They all show excellent absorption property. The charge transfer exchange coefficient goes till 40,000, 60,000, but then they are zero emission almost. So recently, two more papers have been appeared. So one approach to get emission was you include fluorofluor like triphenylate or pyridine to the TCPD. They got 7.8% in exchange as a solvent. And another approach, again the central pi system, as a which can undergo self-assembly and leads to vesicle-like structure. Due to that, you get the emission quantum of 8.5% exchange. So when we started the program in 2015, I was asking, so this is the limitation. This is the internal property, this is good, but limitation closes off. So that means you cannot use it for sensing application, especially, or biological imaging application. And another limitation was no functional modification can be possible through the existing method. So then we designed, what if you use instead of N-dimethyl aniline, urea as a donor, and then make a TCP. Why urea? Because it has iron bonding moiety 2NH that can be used for sensing and important analytes. And second, it has unique electron bonding ability, that is not only through space, but through bond, also through space. Typically, if it is N-dimethyl, that is only through one electron donation happens. So this leads to interesting property as expected. So in order to demonstrate that the urea can act as a donor, that may sound crazy, because urea is typically compared with amide electron with right nature. I will explain why we thought we can act as a donor. The reason is you have two NH lone pair. If one NH is attached with the alkyl group, because of plus effect, that lone pair will delocalize with the carbonate. Then the another donor will be free, and that can make the alkyl electron rich. That is one. Second, it has a unique. It doesn't follow Hammett constant behavior. Unlike other methoxy, they follow Hammett constant behavior. Here we can explain through field effect. Field effect is nothing but a combination of mesomeric effect, electric effect, steric effect, all this steric effect. Typically, Hammett constant is based on mesomeric effect. So, as a proof of concept, we have synthesized various urea substituted alkyl and then treated with TCNE. Indeed, we were able to isolate the TCNE product in liquid. And in fact, the reactivity for N-dimethyl is the strongest so far. N-dimethyl itself works at room temperature, but this works at low temperature itself. So this is the N-dimethyl as a control study to make this compound. And then compare that to photovoltaic property. And the compound 4 is the green one, which is having this exchange coefficient than the urea derivatives. Also, most interestingly, the emission spectra shows that the control compound does not have any emission, whereas urea shows emission. And this we expect to field effect that why urea is a donor. And to prove that charge transfer is indeed exists, intramolecular charge transfer, you add along in the chromophore you add trichloroacetic acid, it protects the urea, then charge transfer carbon. Again you add triethylene neutralize it, the carbon transfer. That means protonation on the base is the result. So the urea is here due to this electric dipole moment generation through space effect transfer through bond effect is the reason for generation of fluorescence characteristic. So after demonstrating fluorescence behavior, as I said initially that the urea was important for sensing application as well. So we were thinking to demonstrate application in sensing of one of the important analytes, fluoride. Dr. Sankar also mentioned that fluoride is very important indeed, because if it is less than 1 ppm, in drinking water usually fluoride is present. If the fluoride content is less than 1 ppm and if you drink longer time, then dental fluorosis will occur. But if it is more than 2 ppm, then skeletal fluorosis will occur. That means the bones get fractured, bent, and they becomes handicapped in their life. So however, if it is 1 ppm, if you every day, then it's a good for bone. You never get dental fluorosis as well as skeletal fluorosis. So that means optimal level of fluoride content is very important. How do we know that drinking water contains 1 ppm of fluoride? So that means we cannot send it to some analytical lab and wait for the result, especially from rural area where this problem is prevalent. So that means the need of the hour is to come up with the colorimetric based direction, that is maybe paper strip, that you put your sensing molecule and then put it in water and it shows that it's how much concentration of fluoride. That's the need of the hour. To demonstrate that, this is one example. We, after a series of molecules synthesized, we identified that the bisubstrate TCP with the urea here, and when you have R here, H, or when you have N dimethyl here, so there's a huge, remarkable effect in the property. The one with N dimethyl does not show colorimetric sensing, whereas without N dimethyl we could be able to show colorimetric sensing. So as you can see, the one with hydrogen, you can see the clear color change upon titration with fluoride. And then this is through UV. In emission also, internal emission was observed. This is a compound without fluoride, it's compound with fluoride. And then as a practical application, we also demonstrated that putting it in a simple tissue paper, this compound was drop clustered. And then in one water gave us 1:1 ratio, we don't see any color change. But then with the 3 ppm, you can see clear color change. Even with 1 ppm, light color change was observed. So this was published in Journal of Photochemistry and Biology. This was also covered as a documentary in India's STM channel. It's available on YouTube also. One can watch. So we also patented this work. Now soon there are many companies also approached us for implementing this work. A chromophore, which is a green blue, that with 3 different chromophores. But getting a white adaptation from single chromophore is a challenge. Not a single example is reported. So this is the chromophore we use actually, this TCP here, it's a chain. Typically mixed with that this compound. So maybe 80% solution of polystyrene, 20% weight of this one. Then we made a nanofiber using the atom spinning method. So you take this solution and then inject through a dye with it, and immediately the solution becomes solvent evaporates and the solution becomes red, green, blue, green application. So we also studied for first time biocompatibility of this kind of class of compound. This TCP-based compound not used for any biological application. So we studied and we have found it biocompatible. In fact, cancer cell lining were dead, adverse death rather than normal cell if you use the construction. So this was published in the magazine. In the last work, I will show you that how we can further fine-tune the photophysical property of this compound, TCP compound, utilizing another nanotechnology approach, that is using nanomeric. So the PF127 is a tri-block copolymer. It has hydrophilic part here, hydrophobic part here, hydrophilic part here. So when you mix PF127 in water, it forms a vesicle nanomeric with the size range of around 80 nanometer by 80 mm. And then if you are doing this synthesis, if you have this compound also in water, so basically take this in acetone soluble and then take this compound in water and then inject them to slow stirring and then solvent evaporation, then you get the compound gets into the nanomicelle. So basically it aggregates inside the nanomicelle. When it aggregates, the property of this compound goes from here to here. This is the emission spectrum of this compound in molecular form. It's around 420 nanometer. After aggregation in the nanomicelle, the emission shifted from almost 250 nanometer from molecular form to nanomicelle. Stroke shift. That's huge stroke shift. And this emission was utilized for both bioimaging and photodynamic therapy. So using bioimaging, you can see red and green emission because of the other emission shift. And then using using photosensor basis of light, laser light, we could be able to show that the cancer cell is undergoes death, whereas without light it doesn't undergo death. So this is photodynamic therapy. Also, the photosensitizing mechanism was proven to be a single oxygen generation. Its ability to generate single oxygen was studied using in vitro study, using new technique, using diatas and as a probe. We found it is able to sensitize there is no change in the morphology of the tissue cells. That means, and also they excrete very well. They don't stay in the body for a long time. So this we are going to communicate soon with this. So in ongoing future plan, that 2+2 reaction in lungs, can you do it in water? That is another work we are currently doing. And if when you do it in water, whether the reactivity of 2+2 remain the same or new reactivity observed. So in this currently unpublished work, soon we will be able to publish. And then we can also extend TCNE to TCNQ derivatives. That will be even more longer NARH emission we can get absorption. And the non-linear properties also we can study further. So my time is over? Okay, fine. Then I conclude.
भाई इधर देखो इधर बस बात क्यों कर रहे हैं
But it is very long, but application to junction.
Maybe you can check, it may be through space aggregation and use function.
That is also possible.
That is possible.
Yes.
It is more than 100 and
yes.
That is very
yes.
Thanks for the nice talk. I have a small clarification lecture regarding your fluoride sensor.
Yeah.
What is the mechanism of sensor?
Yes. I didn't show you the detail of the work because of the time constraint. And forms H2F. Then this anion generated here delocalizes here. So now the charge transfer property highly changed. Because of that, you see the color change.
So did you see a signal in the
yes, NMR, we see the signal. This proton remains the same. This proton is here, and then HF2 minus B.
You the position of that also change. The position of that also change.
Yes, a little bit.
So there is no change in the measurement. Is it not that basic?
So what happens? This chart, the color you are seeing is due to urea as a donor and this disulfide factor. So what happens? There is a lone pair and this lone pair delocalized till here. So there is a delta minus here, delta plus here. Okay. Now that because of that you see this color. Okay. Now you add trichromatic acid. Now this avoid NH potential. It becomes NH2 plus. Now this electron lone pair delocalization does not occur. When there is no delocalization here, you don't have color. And then, pH is acidic because H2 we are adding, right? We are adding excess, really excess. Excess.
It's very less amine. It's not that basic amine. Due to integration.
No, it is due to the field effect I told you, right? Because of that, it's almost combined with the amine. That's what I showed you here. You can see this is amine, Eden dimethyl. Eden dimethyl coefficient is here, the charge transfer. Whereas the urea, they are ion exchange, so that means they are very good donor.
what happens here, when we are what are the trifluoroacetic acid, that is neutralized, it becomes trifluoroacetic acid ammonium salt. Now there is no acid to protonate, that's why you see that same pattern starting. It's a reversible process.
Dr. Kamanjit to chair the last technical session.
So dear friends, this brings us to the last technical session of this symposium. And it's perhaps more important part of the symposium because Dr. Kumar will speak and will take us through the academic journey he has so far, starting from his career. And I have decided not to read his biodata because we all know him very well, and in part his biodata has already been spoken earlier. And the second reason for not reading his biodata is that my association with him is as long as the start of his career, because we started doing PhD almost in a difference of 1 year, and since then we have known to each other in a much better way. And I can even claim that I know him better than Vandan does because because my association with him is much older, So Dr. Manoj did BSc from Hindu College and then did MSc from Khalsa College, Amritsar. In 1985, I joined my MSc Honor School. At that time, 1 year MSc Honor School after BSc Honor School. And Manoj had already joined PhD. Yeah, he joined PhD in 1985. So after, I was doing project in the same lab. So obviously we knew each other, and I also learned the kind of work he was doing because our guide was same, Professor Rajiv Singh. And then, after MSc, I was offered PhD, and I joined obviously PhD instantly, almost instantly. And by then he had already completed 1 year. So I just tried to bring on some movement. Maybe the picture quality is not very good, but I thought I must show these just a kind of reminder to everybody who knows us since then. So this is a picture we took in 1985, I think probably October 1985. And Professor Rajiv Singh, the great man, is standing here. That's me. This is young Manoj. And Dr. Chimney is standing here. And Dr. Sreen, he is no more, unfortunately, he died a few years back. And Professor Paramjit Singh has... So anyway, in the meantime, let me tell you that we both started working together. And I would normally discuss chemistry with him because he was my senior that way by 1 year and would like to learn about Professor G. Singh's way of working. Although I had also spent 1 year, but during MSc you don't interact with your guide as much as you do with PhD. So I will ask him that what kind of questions he asks when he calls me in his room, and how we are going to answer those questions, and what kind of chemistry we need to discuss. Does he ask for the mechanisms or not? So that way we used to share in the evenings mostly when everybody was gone. So we'll be sitting in the laboratory and taking tea at 6 o'clock, 7 o'clock, and we'll have these informal discussions. Because during daytime it was not possible. So this picture is from that time, 1985. So this is a picture which shows that Professor Paramjit Singh had decided to go to Canada, to Australia, and we bid farewell to him in guest house. And he is Professor Kumar, you can see him, and you can see, he is not much changed now. And Dr. Kumar used to be very, fond of wearing ties and and people like me would be, without any special kind of attire. And so that's the picture of that time. And this is another, one picture in the guest house after the lunch we took. So Anupa is in US and Subodh is standing here. Dr. Paramjit, his wife. So Manoj was very tall, but when I would stand with him, then he was not as tall. So that's the time when we got the degree. I had to work very hard. I had to work very hard because I told him that we'll take degree together, the convocation. So the day came, in 1989 we got degree in the university convocation. And Paramjit got 1 year after, she just is posing with us. And we got the new coats stitched and ties and all those, with a good attire so that.
And just see the type in.
Yeah, type in. And these are MSc students of that time. So this is outside the pandal, we never had this kind of auditorium at that time. So it was done in open tents. So we were just standing outside, and that was, I think, the rehearsal day. Or the same day, I think we got degree probably. Yeah. So that's when we are rubbing shoulders with then Governor Shankar Ray, the Governor of Punjab at that time, and at home, because there was a tradition that the degree holders, the medal holders, they will be invited by the governor in the university guest house to a cup of tea, and the photo session will certainly be there. So that's what we are doing right now. So he was the Vice Chancellor Randhawa Sahib, and Manoj, Shankar Ray, and myself, and other people who try to, just get into frame. So that's what, at the end of the day, I was very contented here because I'm standing in this row, and Manoj, my friend, is getting degree, and I'm also getting degree. So we got degrees together, and it was a good photo after the degree was given to us. All right, so then comes the time of my marriage.
Yeah. He was telling me, just dance, just dance.
And I knew that Manoj is fond of dancing. And I had very simple marriage, not very too much important. And yeah, of course, my partner as well, right? So he is shaking the leg, outside that marriage palace. We are just to enter inside for the ceremony, etc. So you can see how happy he is. I never write out the Kori, Okay, so we had a promise actually. We made promise to each other that if I got postdoc first, then I will call him, and if he gets postdoc prior to me, then he will call me. That was the agreement we had done. So that we both do postdoc together. So he got postdoc in Spain, in a very reputed institute, Institute of Química Médica of CSIC. CSIC is Consejo Superior de Investigaciones in Madrid, and he joined in probably 92, I think, 91. So he went there and applied for me also. I also got, and I joined him in 92, in December 92 to be precise. And that was the first day of our meeting there in that apartment that we shared for 1 year. And we cooked together, we ate together, and we had 2 beds to sleep. And we roamed about, in the whole Spain together until Paramjit joined in 93. Then I had another year with her. So we are celebrating, togetherness once again in Spain. So that's the institute where we had the postdoc. Manoj laboratory was somewhere here on the 3rd floor. That was the Química Médica Institute, and the National Institute of Organic Chemistry was here. So my laboratory was somewhere here. So during lunchtime we'll be together, we'll come together, go together. And that was the first weekend when I arrived there. I was very healthy, that time, 98 kilograms weight and all those. And so he took me to the department, to the institute, to show me the place where I'm going to start working the day after. And we took a picture outside on Sunday, probably. It was Sunday or Saturday, I don't remember that day. So we used to buy clothes together, the same clothes. And we'll wear the same clothes on all the occasions. And the second thing that we used to do was we'll buy the clothes, come back to the apartment, wear the clothes, take a pic, and then again declothe and
return to the store.
So that was the ideal, spot at the entrance, a small gully where we used to take the pictures. And I have several pictures with him also, with Paramjit also, because, afterwards. So we thought, why not to try bathrobes, And we were so excited. For the first time in the life, we saw a bathrobe actually. And in pictures, we used to see that the person wearing bathrobe will come down the stairs, walking and adjusting hair. And for 2-3 days, we did that job, Adjusted the bathrobe here and there, just to show that we are wearing it. And I still have that bathrobe in my house, yes. I still have that. So that's again you can see the tracksuits wearing, same tracksuit and everything. So after the, time at institutes, we come back. So he was a Bengali with us, who joined us later, very good cook. And he was in university, we were in National Institute, so obviously we spent more time in the institute, and he would stay for less time and come back. And when he come back, we'll see from the outside, the kitchen window, that he's preparing something. Tarchi chalti thi uski. And we will feel relaxed that something is there to eat, and we simply eat that. So that way he used to feed us very well actually. Very good cook and very good friend as well. And this is the car where you can see the red plate. It's a diplomatic plate actually. We had a common friend in embassy, Indian embassy at Madrid. Dr. Batra was also there earlier, so we were common friends that way. And he had this Mercedes, and we got the opportunity to sit in Mercedes for the first time in Spain only. We had only heard about this kind of car, but sitting in that car was a real pleasure, especially with a red plate, because no one is going to check you, stop you. It was diplomatic car going, and we were sitting there, enjoying. And so whenever we had to go for some visit, so he will come and pick us up and take us in his car, and we used to celebrate together that way. So that's again one of the pictures. And that's the window I'm talking about. And that's the 69 Calle Cedros, where we stayed for 2 years, as a postdoc, our apartment there. So this is the visit to one of the railway stations, Chamartin, I suppose, Chamartin. I don't know why I didn't go there, we just went there and for the first time I drank through Coke, this can. That was in 92. In India, cans came way after, So that was my first experience with the Coke can, and we took a pic there. As typical Indians, we'll carry our food stuff with us when we go out and drink the cans and burgers and all those things. We'll take together. And that's what I think we went to Navasrada probably for a picnic kind of thing. And the Bengali was very happy because his wife had already joined. And we were like, Hadi in Kebab. But we'll tell him that we'll make you a movie, that's what took us with him and his wife. Yeah, that's again one of the pictures of that visit only. So we had a good time in Spain. We saw almost the whole Spain, north to south. And we had experience of swimming also at Santander beach, if you recall. And the first time we jumped into sea and we had a little swim on the shore. And with the fear that the shark might come and bite us. So very careful we were at that time. Okay, this is one picture of our common friend Upendra Pandit, was professor in University of Amsterdam. And her wife Gerda was with her. They visited us, through a common friend of theirs, Magdalena. She was a librarian at CSIC, and she used to love us a lot. Actually, she was an old lady, and would try to extend all kind of help that we required. But the reason was that she could speak English, and we could communicate to her, and she will always help us. Very nice lady. And Pandit and his wife, we went together, to see Madrid, and there are some not very good incidents associated with that visit. Seoul is the center of Spain actually, Madrid, sorry, and is a plaza where everybody celebrates, the whole city goes there when there is some occasion. But at the same time, it is one region where people don't like to go. The reason is that it's dominated by the blacks and Philippine people, so who will murder you up and try to rob you. And that's why the police surveillance is very strong in that area. So we very fondly took Pandit and his wife to Seoul to have a pint of beer. And unfortunately, we couldn't carry our ID cards with us because we were so confident in Madrid at that time that we never needed any kind of that kind of identity card or something like that. Police caught us. They said, "Show us your identity cards or passports."
Caught us, caught you.
If I am caught, then everybody is caught. So they just stuffed us into their car, took us to the police station without hearing us. To the embarrassment that Pandit was with us and he was visiting us and we were supposed to give him a good time, we landed, in the police station. And police station, the police inspector was very cruel because he had seen sick for the first time. At that time, there was no sick in Madrid, not even Spain, I suppose. 1 or 2 sick at the most. Yeah, before that. Before that. So when I was there was no sick in Spain. People didn't know that there is somebody sick. They will look at us as Arabs, that they are Arab people and something like this. And they had some sort of hatred towards Arabs. So anyway,
ਉਸ ਤੋਂ ਬਾਅਦ 2 ਆਈਜ਼ ਐਮਬੈਸੀ ਜਾਵੇ
yeah, afterwards then investigation. So we convinced them that we are scientists here doing postdoctorate. So we are working in National Institute of Organic Chemistry, Medicinal Chemistry. And my guide was a big guy actually. He was president of CSIC, Professor Manuel Martin. And I said we should, call him and let him tell who we are. Then anyhow, we managed to get the call, and then the police said, okay, so you can go. Sorry for this thing. So that was one incident, which shook us actually. Had it been Punjab police, we could have been roughed up also. But luckily it was Spanish police, more civilized, so nothing happened, that way. So anyhow, so these are some memories which I wanted to just bring here. Yesterday only I prepared these because I didn't know what kind of system will be here. So after PhD and postdoc, Dr. Manoj joined back to the department as lecturer. And prior to that, he was in DAV College of Sharpur. He came back from Spain and got selected in this department as lecturer. And then, propagated through Riga and eventually professor. And during this period, he also had a stint of another postdoc in Germany, I suppose, and went to Japan also, South Korea, all these academic assignments he got that we normally, look for. And he has been a prolific worker, very good work he did, work of very high quality, and that is clearly vindicated by the kind of publications he has. And he started, Supramolecular chemistry was started in 1983-84 by Dr. Harjeet Singh actually. But he was the first student who actually embarked on supramolecular chemistry. And at that time, I remember the main theme was to synthesize macrocyclic compounds and study the transport behavior of those, metal ion transport and all those. Molecular recognition, that these words had just started at that time. They were not really being experienced anywhere actually. So gradually, then we saw each other growing, and he turned out to be, a real excellent chemist. Did great work, and so this is how the journey has been so far. And I suppose this is not end of the journey, academic journey. He's free from several responsibilities now, and probably will continue for many years to come, contributing more and more in chemical research. And also enthuse the youngsters, the way we should, right? So we all wish him best of luck and our best wishes for the best of health, and let him be happy, and we keep on meeting and keep on discussing all these old associations and try to reinforce the old association into a much more stronger association for the future. So with these words, I request Dr. Batra to come here for a brief talk here, and then please come.
I just take 2-3 minutes, don't worry. More. Thank you, Dr. Kamalji, Dr. Manoj. So it's nice to be here because I'm here since morning, and very good environment, I would say that. My association with Manoj are longer than anybody sitting here, and I think time is 42 years, 32 years? 42 years, because I met him first in 1980. So it's 42 years, and that too in Khalsa College, because he was there to seek admission in MSc Chemistry, and he was inquiring about the course, and I just completed my course over there. So Dr. Sahab ने एक सवाल थे पूछ रहे वैसे मैनू, तो मैंने लगा कि तो नया के एडिशन दे आए ने कॉलेज. So first time I met a person with so many queries कि teaching कितना दी हैगी है, placement कितना दी हैगी है, सारा कितना दा हैगा. It was in lab. So after that, in 80, I joined PhD over here with Professor Hardeep Singh. Then he came here in 1982 for MPhil, and then after that he joined PhD. I completed my PhD in 1984, and after that I think Dr. Kamalji joined in the same research group. I joined Khalsa College in 1984. Paramjit was my student at that time, if he remembers. Then Palvinder was also there in 84, 85. I don't remember the time. And then in 83, 84, we were in the same lab, working in the same organic lab. And then after that, I joined Khalsa College Amritsar, and then after he completed his PhD and joined Hoshiarpur. Then I went to Spain in 1990, and when I got my PDF from a college, working in Khalsa College Amritsar, everyone was in the university was saying, "Keda share chale tusi kedi country chalu hai, America country hai." I said, "Okay, don't worry," because that fellowship was great and it was from Spain.
It is. So during those days, I wrote an email to Professor Kim, the lecturer whose lecture you have heard this morning, because with the pace, and I must admit that at times I used to be very tough with my students. Normally I'm very impatient. If I need something, I will tell my students, "Abhi karo, aaj hi karo, pame raat lage karna hai, kaam karna hai." And they used to bear with me, and I'm sorry kise baithe ne beche the, but that used to do. And then let me admit one more thing. I learned with the professor in the evening. Professor told me that, "Manoj, they used to come to me with very good ideas, and I never discouraged them. I told them to come out with the ideas. This work on chemical logic gates, Abhimanyu Veer, I must say, he came out with the idea when we performed some experiments, fluorescence experiments. He said, 'Sir, this can karna hai.' ਇਹਨਾਂ ਨੇ ਮੈਨੂੰ ਪਹਿਲੀ ਵਾਰੀ ਕਿਹਾ, ਇੱਕ ਤੇ ਬਗੈਰ ਕਹਿੰਦੇ ਵੱਡੇ ਜਨਰਲ ਚ ਵੀ ਛੱਡਤਾ ਸੀ, ਉਹ ਸਾਰਾ ਦਾ ਸਾਰਾ ਕੰਮ ਹੈ ਉੱਥੇ ਡਿਸਟਰੋਏ ਹੋ ਗਿਆ। ਇੱਕ ਦੋ ਬੱਚੇ ਮੇਰੇ ਨਾਲ ਕੰਮ ਕਰਦੇ ਸੀ, ਉਹ ਵੀ ਛੱਡ ਕੇ ਭੱਜ ਗਏ। ਤੇ then again I started from scratch in 2000 to get an MSc. That at times I used to be very tough with my students.
From Wiley, I think 500 rupees each. For Rajit Sharma, Karandeep Grover, then Supriti Sood. I repeat once.
There are two small gifts from MKBB Group, and the first gift is Prit Singh. So this is a small token of thanks. Second one is for Hitakshi. Beautiful Rangoli. She sketched the organic letter which has 239 citations. So now over to you.
So I would like to thanks to our team involving Professor